Organizers asked for another probably couple of minutes actually to wait before we start. I'm very sorry about this, but okay, so let's wait for another 3 to 5 minutes, and right after that we will start the session. Thanks.
Можно петь.
Я сказал. 3. Well, if you are participants or speakers mostly actually concerned about some delay I have to notify you that we have few cancellations, so we can be quite flexible with this agenda actually. The only milestones which constrain our work are the coffee breaks and lunch, which are served actually exactly in the time which is shown in the agenda.
Содержание презентации чуть-чуть то подкорректировано. Куда ее можно сбросить?
Сереж, смотри, пожалуйста. Значит, Гулев, Зимов, Елисеев, Гельфан. Потом Гельфан, Грицу, Школьник.
Вот Школьник хочет апдейтнуть свою презентацию.
Блин, нет.
Вот он.
Здрасте, нет.
У меня там... А там изменения, там, существенно есть изменения. Но название не поменялось.
Говоришь, что существенно. Антон, а чего вы садитесь где-то?
Сейчас я найду, да.
Okay, again, very good morning. Take seats on the floor, please. There are for you seats available actually over there. Okay. Very good morning again, ladies and gentlemen. I'm Sergey Gulev. I'm your chairperson for today's session. And the title of our session is Climate Change Implications for Sustainable Development. And we hold this session in this very nice facility, the pavilion of Russian Federation. And may I ask you to down a little bit your talks actually around the floor? Thank you. Thank you. Yeah, and so this Science Day will be focused on, actually, as I said, on climate change implications for sustainable development. And I guess for this event, it's an important thing, actually, for COP28 in general and for the Russian agenda at COP28 in particular. Well, before to start, I have actually introductory statements from our co-sponsors, because the session has been sponsored by 3 parties, in fact, by Ministry of Science and Higher Education of Russian Federation, represented here by Anton Shashkin, and by Russian Met Office, represented by Tatiana. Could not see her, unfortunately. She's over there, okay, managing. And also our third sponsor is Andrei Melnichenko and his foundation of his name, which deals with many aspects actually of human being, but also with climate change and with particular natural solutions for climate change based on nature capability. I ask now representatives of Ministry of Science and Higher Education and Russian Met Office to say some words actually, to welcome us. Anton? Okay, I will translate, not in parallel, but okay, statement by statement.
Всем доброе утро. Мы рады, в общем-то, вас всех видеть в этом павильоне, в российском павильоне, где будут представлены, где будут представлены российские научные результаты в области изучения климата, так называемого проекта «Карбоновые полигоны» Российской Федерации. Но в целом мы будем говорить, естественно, о климате, о его изменении.
We are happy to welcome you this session actually in Russian pavilion of Russian Federation. I'm happy to welcome you and say that we will present scientific talks here along with actually a specific session dedicated to Russian carbon supersites.
Сегодня с нами здесь будут ведущие российские ученые, такие как Сергей Гулев, Александр Ольчев и многие другие.
There will be several Russian climate scientists, climate researchers. Actually, Alexander Olchev's name was mentioned, my name as well, but also actually all people are equally important here.
Спасибо большое.
Thank you very much. Thank you very much, Anton. Tatiana, I just saw her, but Tatiana, may I ask you to say some words from so Tatiana declined actually to welcome you from Russian Met Office, but Russian Met Office contributes quite a lot to the organization of this session, and we have to thank actually the leadership of Russian Met Office, chair of Russian Meteorological Service and his vice chair, and personally Tatiana, who personally invested quite a lot of time and effort actually in organization of this session. Now at this particular point, I invite Andrei Igorovich Melnichenko to also make an introductory statement on climate change and sustainable development. You are very welcome. It's your turn.
Okay. Firstly, welcome everyone who found the time to visit this very small, very, let's say, home kind of the event. Science become not major things perhaps on the COP. So when we are going to the big events which is dedicated to the finance, to the interesting economic development, we can see much more people. So science events attract less people now, what is of course unfortunate. And Russia science event attract even less people, what is even more unfortunate. But nevertheless, here we are, and let's try to spend this time with some sense. I represent here Russian Union of Industrial Entrepreneurs, and one of the missions of our union is basically to represent interest of Russian entrepreneurs on behalf of the government and behalf of the international community in the matter which is important for Russian economy and things like this. So now we are meeting during the COP28. The main question which we can hear if we are walking around, it's how basically humanity not able to achieve what was planned to be achieved by the Paris Agreement. So we can see that average temperature of our planet it's already 1.1 degree higher than it used to be during pre-industrial time. So we are well above the track which should be contained in case we remain with a target 1.5–2 degrees, which was the goal of the agreement. So we are doing something, but results are still not there. What we achieved really so far? So the growth of the emission become a little bit slower. So it was 2.1%, let's say, per annum till 2009. Now we are on the track more like 1.1–1.3% per annum. So we are spending a lot of resources, we are spending a lot of money, we are compromising other goals which is stand in front of the humanity. But, but at the same time, emissions are not going down, concentration of the greenhouse gases in atmosphere not going down, so just speed of developments a little bit deaccelerated. So what leads us to the question? Maybe we are doing something wrong. Maybe we should look for solutions which can help us to move back on the track, to achieve what is need to be achieved. What we need to look for? So where is the search for these basically solutions should be concentrated. So that is a basic question which need to be raised in case if you are thinking how to address this question. Okay, so where is the solutions? For now, human emissions, anthropogene emissions reported by participants of the Paris Agreement stand at about 56 gigatons per annum. And if you look carefully on the basically action which is taken by the countries, by the companies, by the economies of these countries, normally we will see solutions concentrated on reduction anthropogene emissions. That is no surprise, because that is very well fit with the business model, which is basically main driver of economy of the most active participant of this process. What do I mean? So if you're a company, if you're an industrial company, and your business is to do something industrial, maybe it's, I don't know, production of electricity or production of, or providing of some transportation solutions. So you're naturally looking in the area which is known to you. So you're trying to reduce emissions based on your activity. So you wanted to use less fossil fuel or move to something new, to another sources of energy, or you wanted to make energy efficiency higher. So naturally, everyone does what he knows to do. So you are active in particular sector of economy, then solution which you provide also will be naturally concentrated on your expertise. But maybe that's exactly a reason of the problem. Maybe we are just not looking on some solutions which is not fit in today, let's say, competence of the main participant of this market. What do I mean? I mean nature. So total amount of the emission coming from the surface of our planet, it's about 860 gigatons of the greenhouse gases. Humans, like I can repeat, it's 56. So Is it not surprise that when we are trying to resolve issue of the concentration of greenhouse gases in the atmosphere, and when we are concentrating just on 6%, we are somehow not achieving a result because other 94% are not touched. Is it not surprise? For me, what else can be expected? Of course, it cannot be achieved. You touch just 6%, you don't touch 94%, and you expect to reduce total amount. How it's possible? I think it's nonsense. So what leads us to the next question? What does it mean? Is it really anything can be done with the nature, with this 94%? What exactly can be done? And most important, basically what steps need to be taken to lead us there? So today we are meeting during Science Day. So for my understanding, that's a question of the science. So to look, to understand, to learn, and to propose. That's why I think it's a right place to talk about it. Why Russian science? Why this event? I think regardless of our very small environment, regardless of all of this feeling of isolation in this small space, why I think it's important? For simple reason. Nature is something proportional to the surface, proportional to the national territory. Russia, it's a big part of the surface of the planet. Russia, it's, 60% of the world permafrost. Russia, it's 25% of the world forest. So in case when all of this basically dust will settle, dust I mean noise, but no solution with the greenhouse gases emission, real reduction, then humanity will naturally start to look on the natural-based solution. And when you start to look on the natural-based solutions, where this process will start? It will start in the places where the biggest land mass is, where the biggest ocean area connected with this land mass is, where is a more interesting landscape who are changing their basically emissions or stocks capacity now during this process located. So I think Russia will be in the center of the place just because we are geographically so big and so much located. And that brings questions, very important question to the Russian science. So do we really know about our territory? Do we really understand what basically happening there in terms of the natural emissions? So I don't think so. We are trying to collect basically this knowledge in one place, and surprisingly, we see that this knowledge is not consolidated. Exist pieces. Some professionals working in one field, some professionals working in another field, but comprehensive picture simply not there. So our government started to understand this issue. So last year, basically in October, quite big process started. We start to develop a countrywide system for monitoring of the active substances, for the active substances which affect basically climate, different greenhouse gases, not only methane, not only CO2, but others. So that is a big job, and it will give a real base for Russian science to base their basically search on the real numbers. I think it's a fundamental and very important step forward. What will come next? Next will come a wave of the different specialized professionals. Professionals specialized in oceans, professionals specialized on the permafrost, professionals specialized in the forest, because all of this huge data need to be processed, interpreted, some conclusion need to be drawn from this. And that is exactly where time for the science will come. So we heard enough of science, which is basically doing a job, making panic around people. So we are listening about theses which is usually saying like, okay, something will be dangerous here, something will be dangerous there, something will be like this. It's very good for the marketing. So if you wanted to sell some solutions which bring business to the companies which, I don't know, deal in the new sectors of the economy, renewable, etc., that extremely well organized campaign. That's very good. But if our idea is not to sell particular industrial solutions for the customers, which will need to buy it in order to comply with the national regulation, but if our job is really to try to concentrate on the issue to reduce greenhouse gases emissions, we need to come back and start with the basic. We need to research what this 94% is. What is going out, what is coming in, what is the stocks located where. That's a real job. So, of course, we are living in the very strange world. We are living in the postmodern, when real science becoming like less important. Important is what's written in the paper, important some news which is, I don't know, actual today, important the news which lead to some business result. But science, it's not about this. Science, it's about reality, truth, facts, checking, peer review. So that's what we really need from the Russian science now. We need to concentrate on the national territory, we need to understand and to learn what exists there, and then coming next stage. Can we do something about it? Do we have solutions which can basically affect this natural flow of greenhouse gases? I think we can. That calls NBS, natural-based solutions. And potential of the solution looks very big. So there are different estimates done by the different international bodies, by the different bodies with proper expertise like United Nations Environment Programme, like by other institutes, and numbers which they're showing are very big. So I think future is there, But this future a little bit distant from the today. So we need to work on the scientific level now. We need to understand what can be addressed and how to be addressed. And then next stage will come. So if molecule is the same, market forces will find a way to commercialize a result which is done on the nature, same like they found a way to monetize solutions done on the anthropogen landscape. So one more time, welcome everyone for the Russian Science Day, and let's come back to the science. Thank you.
Thanks so much, Andrei. It's a very nice statement, actually, very nice introductory statement. I particularly like your point, actually, that it's importance on the importance of the natural science, because actually on climate conferences, not only on COPs but also on the other climate conferences, there's more and more engagement of political, social scientists and so forth. So the natural science seems to be, which is actually the core of climate change science, starts to be a little bit downgraded in this respect, and thank you very much. Thanks. Now I have to take the floor myself, and I will speak mostly about observed and projected climate change, primarily based on, my talk will be primarily based on the results of IR6, IPCC assessment report number 6. You see, we have very noisy neighbors from the country of Chad. I don't know if it's possible to communicate with them somehow. I will try, but I think it's weird to some extent. Okay, may I ask you to launch my presentation, please? Yeah. So as I said, so I will. No, it does not. I will speak on observed and projected climate change, the mechanism and reliability of estimates, and how does it? So how does it go? Oh yes, okay. Yeah, well, as I said, my talk will be primarily based on the 6 assessment report results, on which I was one of coordinating lead authors, particularly for Chapter 2, which is present state of climate system. By the way, you can take your seats actually somewhere. It's not necessary to stay here on the stage. And IR6, compared to IR5 and IR4, came with a couple of important messages. And one of these messages that unprecedented warming over the last 2,000 years, actually, which is shown here. And most importantly is that we finally stated that the dominating cause of the observed changes is a human influence. On this slide, you can see the observed global air temperature, surface air temperature, which has grown up by 1.1 degrees compared to pre-industrial during the last 150 years. And the model solutions actually in this range, which demonstrates that models, if they account for human and natural factors, they perfectly fit to observations. And if they don't account for human activity and human impact on climate, but only on natural solar and volcanic forcing, in short-term variability is well simulated, but it does not simulate the trend. many people actually, this is a big problem of climate change studies. Many people say that whether it's a critical 1.1 degree for mean air temperature, whether it's important, it is in fact, and some people may say that, okay, there were temperatures which were higher by 15 degrees, for instance, in an optimum shown here, or there were temperatures which were lower, and there were very difficult conditions, for instance, here on European, not here, but on the European continent where we live. There were glaciations and deglaciations, but changes, these dramatic changes, they have never been occurring actually so fast as they do now, which is shown on this slide. And you can see that even on this corrupted scale, to show 150 years about which we speak, on the scale of 60 millions, you need to be cared actually, you need to care about the width of the line, because it's impossible to show here. I will skip some slides actually, because just okay, prepared this presentation for a longer time. What is important about this 1.1 degree, that first, land is warming faster than continents, faster than the oceans, and it's 1.5, even a little bit more than 1.5 for the land, and just 0.9 for the ocean. The second thing, that high and mid latitudes are warming faster than tropics and subtropics, and especially southern hemisphere. It's also important that the warming is inhomogeneous, not only between land and ocean, but also through the latitudes. The third thing, which is also important, that warming is accelerating, and you see here the trends over period 1900, 1980, and 1981, 2020, and you see that trends here are dramatically stronger than those for the previous decades. Okay, why does it happen? Why it's happening? What is human influence? Human influence is a greenhouse gas signal, greenhouse gas emissions, and we have to speak about at least 3 major greenhouse gases, which are CO2, CH4, which is methane, and also neutrons, ozone neutrons, and also halogens. We know this number is outdated already. It's 409. It was in 2018, 2019 early, and we agreed finally, since it was precisely estimated number, we agreed in IR6 actually to leave exactly this number, but now we are already over 420, and you see that concentrations of greenhouse gases, particularly for CO2, they were jumping, actually growing up during the last 5 decades actually, as fast as they have never been changing, growing during the last 800,000 years. And on this diagram, you can see the impact of CO2, the impact of all other well-mixed gases, CH4, N2O, and all halogens. You can see the impact of ozone, which is also works for warming, and aerosols, which are working for cooling, because they're making screens for shortwave radiation coming into the atmosphere. This 3 actually, they work with long-wave radiation, except for ozone, which works in a different way. If you sum up all this, you get this impact of about close to 3 watts per square meters, equivalent of this 1 degree, compared to 1750. And you see that the total consolidated impact is warming. It's this warming mostly done by greenhouse gases. And compared to this signal, solar signals and orbital signals, they are important only on a very long term. On this time scale, from 1750 to 2019, they are not as important. They're considerably smaller than the signal associated with greenhouse gases. This was what I mentioned actually in my previous slide. And here, the so-called effective radiative forcing. This is exactly this 3 watts per square meter. And you see that these peaks associated with volcanoes, which actually provide instantaneous and quite serious cooling for the climate system, but it's integrated and it may have an impact over 1, 2, 3, sometimes years, with oceanic signals in this game actually being probably sometimes up to 4 years. But nevertheless, the trend is such as it's shown here. By components of climate system, if we go by components of climate system, what is important? First, where is this excessive heat which comes to the top of the atmosphere due to imbalance between short and long wave radiation? Where does it go? Surprisingly enough, we are always concerned about the atmospheric changes, but in fact, 92% of this excessive heat goes to the ocean, and ocean accumulates, as I said, 92.3% of this excessive heat associated with global warming, with human influence on climate. And this is why we already in IR5, not in IR6, we said that global warming is ocean warming, in fact. And on this diagram, these 3 blue, actually belts, 3 blue areas are associated with the ocean, upper ocean, mid-ocean, and deep ocean, and they all together accumulate this 92%, and the rest is shared between the ice, land, and the atmosphere, and you see how small fraction of direct heat in zettajoules actually associated, accumulated by the atmosphere. So next thing is how we were speaking about the temperatures, how the water cycle, how the hydrological cycle responds to climate. Precipitation does not show, in fact, global precipitation, does not show, in fact, very pronounced trends. So water in the atmosphere, and water is a fuel, water vapor is a fuel of the atmosphere on all time scales, even on weather time scales. Water works in a different way. And what we have that we see actually positive changes, upward trends in precipitation in the regions which are wet already, where precipitation is at max. And we have downward trends mostly in the regions like here in deserts and in relatively dry regions. And this is why we generated such a also message that wet gets wetter and dry gets drier. This is how precipitation changes actually over the globe. Cryosphere, changes in the cryosphere are also important because they have direct direct implications actually for economy and for the human being. Not a big surprise that changes, that ice sheets are melting, and particularly Greenland is melting faster, of course, than Antarctica. Antarctica, it's a more complicated system, but nevertheless, during the last 25, 30 years, where we have highly accurate, precise satellite observations, we see that changes are quite dramatic, actually, in the ice mass of the ice sheets. Snow boundary, actually, snow margin, starts to go northward, leaving actually more and more thousands of square kilometers over Eurasia and over American continent out of snow over the whole year, and also even in winter. And of course, sea ice, we lost during the last 3.5 decades about 30% of summer sea ice in the Arctic. And you can see here in this plot, and here it's a million square kilometers, that in late 70s and early 80s, we started with 6.5 actually million square kilometers of sea ice cover, and now we are at the level of 4. This is also important for climate predictions, and particularly for transportation and potential use of Northern Sea Route for transportation. But this is not an easy problem, because actually you see that over this global trend there are oscillations, interannual variability, and it may not necessarily be that actually dropping, going down sea ice coverage, if it approaches the record-breaking actually level of 2012, will necessarily be every year after that. It may change. Also sea level. Sea level is another example, and another very important example of climate change. And this is what we call, we use the term unequivocal, because this is what you can observe, what you can really see. And this 3 millimeters per year starting from early 90s, when we have actually very highly accurate satellites observing sea level. This is absolutely true, and sea level, mean sea level rise by about 9.8 centimeters actually over the last 34 years. And this is really a challenge, because it's probably less a problem for Russian Federation, for instance, but for many tropical islands in the Pacific, which have elevations of about several tenths of centimeters. For them, the signal is critically important. It's also critically important for Singapore, which has an airport, one of the biggest in Asia, Airport Changi, which is elevated by just 67 centimeters over mean sea level, and this is really an important thing for them. Finally, we come to climate predictions, because knowing how climate is changing, we can try to predict it. But what climate scientists always say when they are claimed with inaccurate climate predictions, that it's a problem of scenarios. We cannot predict anything with climate actually if we don't know according to which scenario we make this prediction. When I say scenario, it's emission scenarios. And emission scenarios, it's not a duty actually of climate scientists or physical scientists. It's a duty of economists, which provide us with these climate scenarios. And here you can see 5 scenarios which were used. And some are excluded actually. There were more in IR6, and this is business as usual scenario. This is, for instance, okay, we live as we do now actually, and this is also a little bit unrealistic, 1.9, if we start to immediately and fast reduce actually emissions of greenhouse gases. Importantly, also this has a connotation to the statement by Andrei Melnichenko before me. If you go this way, in 2100, ocean and land will cope with about 38% of greenhouse gas emissions, and we, all community, we will need actually to act with the remaining 62%. If you go this way, ocean and land sharing actually the capability of accumulating greenhouse gases will be able to cope with 70%, and what remains for us is 30%, which is much more favorable than 62, which we have actually in this case. So this is a range. This is more or less a case range, and this is an uncertainty of our predictions. And I can skip this now. A second thing which makes our predictions, we will have 2 talks on this, so I will be very short. A second thing which makes our predictions inaccurate, besides the uncertain scenarios is a setup and the performance of our models, climate models, which we use. Here I show you kind of very schematic view of how the models were developed from mid-70s to IR5. This is previous report. On IR6, it's more or less okay, the same. You see that atmospheric branch, model, climate models, they start with atmospheric model, of course. And the resolution has changed from about 200, sometimes 250 kilometers now to about 50, 40 kilometers. And this is a huge step. And you see how Europe looks like actually in resolution 90 kilometers and 30 kilometers. It's already, you can at least recognize here quite a lot of things which you cannot recognize on the top. But ocean, which requires actually even higher resolution, is still unresolved actually, because with 60 or even 40 kilometers, which we have now, we cannot resolve in the ocean very small areas actually, which are critically important for generating intrinsic modes of variability, which make our predictions also inaccurate. And also over this history actually, models were enriched. They started to include atmospheric chemistry. They started to include land, ice, mass, vegetation, carbon cycle, aerosols, because first model started just with ocean, atmosphere, and some simplified land models. As I said, there will be a talk on this, 2 talks even on regional and global. And here's a sketch of climate predictions done by IR6. And you see that according to different scenarios, our temperatures may get to 2100 from 1.5 is unreachable. It's absolutely likely from 2 degrees to nearly 5.6, 5.8 degrees. Global land precipitation will start to increase, will increase slowly, and sea ice will decline. Sea ice will decline. And for instance, okay, you see here it's 2050. Under some scenarios, we say Arctic free of ice, but it means you have to read the reports carefully. It means that, okay, we have 1, 2, up to 3 years time slots continuous with ice-free Arctic. That does not mean that after 2050, actually, Arctic will be free of ice, even under this very aggressive scenario. Mean sea level growing up from 30 centimeters to 75 centimeters. And this is also a challenge, as I said, for countries like Singapore and small tropical islands in the Pacific. And this pattern with northern latitudes and mid-latitudes growing, warming faster than tropics and subtropics will still remain also in the future. And the thing which we really have to be careful now, and which comes faster even than our feeling of what this 1.1 degree or even sometimes 3 degrees in the Arctic, it's extreme events. Extreme events, the system is, this is dynamical system. Dynamical system is very non-linear. Even small change of the mean state of the dynamical system results in the change of actually occurrence of extreme events, extreme weather and climate events in the system. Famous Russian climatologist, actually atmospheric physicist, academician Nobokhov, even 40 years ago, he said that the climate becomes more nervous with warming. And this is true. And you see that coastal extreme water levels will increase everywhere. Heat waves will increase, occurrence and magnitude of heat waves will increase everywhere. And heavy precipitation events and magnitude of this heavy precipitation will also be going up everywhere. So that I will stop somewhere here, and I will normally stop with this slide, which is very interesting. When we were working on IR6 and we finalized at IR6 during the pandemic time, and there was an idea actually to estimate somehow if we can actually to account for with our scientific knowledge, with our models, if we can to somehow estimate what was the impact of pandemic with all emissions going down, because air traffic was down actually, car traffic was down, the industry, many industries were down. Can we estimate the impact of this? The answer was no. There were several ensemble simulations, and the result was that these are well mixed and very long living gases. And in fact, the drop in the emissions really did not have any impact on the warming. Moreover, the warming has intensified. It was a very small signal, but it has intensified. And it has intensified for the reason that together with greenhouse gas emissions, what was dropped actually, emissions of sulfate aerosols, and the sulfate aerosols which are present actually in the stratosphere, the concentrations became smaller. The capacity actually to accumulate shortwave radiation, no, not long wave, but shortwave radiation, also became smaller, and the warming very insignificantly from a statistical viewpoint, but nevertheless, okay, we saw the signal. So at this particular point, I stop. We need, what do we need? What do I expect actually from this section? We need a better prediction. So we need improving climate models. We need improve our observations to validate these models. And also, we will have a couple of talks actually by the end, concentrated on mitigation and adaptation. And this is not my area, this is the area of economists, but questions, do we need this, in fact? Do we need to respond to climate change? Likely yes. How fast do we need, and in which area should we go much or less, and how much does it cost? I hope our economists will say something about this. Thank you very much indeed. So if there are no questions, so we can leave questions actually to the personal communications during coffee breaks and the other breaks. I can give a floor to Nikita Zimov, if he is available here. And Nikita will present us actually climate impacts on biosphere and implications for permafrost, with some emphasis particularly on some projects he develops in Siberia. You can use
I need the pointer. Thank you. Yeah, I will use this one. I don't need this. Okay, thanks everyone, and thanks for the invitation. I will start with explaining the problem. So yeah, climate is getting warmer, and it's getting warmer in the Arctic 3 times faster than the rest of the world. And our permafrost is unfortunately not so perma, and I'm afraid in the near future will become not so frost. And another thing, that permafrost is not uniform. There are different areas, and here with the blue shaded areas, you can see the territory which have a specific permafrost which is called Yedma, or ice complex. And one of the main characteristics of it is that it contains a lot of ice. And once degradation of this permafrost is happening, it's leading to a so-called abrupt thaw. At this, the sediments can collapse by several meters over the course of the months or years. And definitely that leads to degradation of all the ecosystems on this place, and infrastructure and everything that's built on there. And another problem, that these sediments contain enormous amounts of organic matter, which is now frozen in the permafrost, and once degraded, it starts to decay, microbes convert to greenhouse gas. And the problem that it's not only CO2, but also methane, a very strong greenhouse gas. And you know, it's often discussed. I think pretty much now everybody knows that permafrost have lots of carbon, but it's rarely discussed how this carbon got there. And for that, we'll have to go back in time a little bit. And let's say just 20,000 years ago, the world's largest ecosystem was called the Mama Steppe ecosystem. And at that time, on these vast plains was roaming million-sized herds of big herbivores. And these ecosystems, kind of now you can see such productivity only in few national parks in Africa. And that's pretty much the number of animals which used to live in this landscape just 20,000 years ago on each square kilometer. So this was a combination of many herbivores, productive grasses, herbs, shrubs, and fertile soils with deep roots. And at that same time, there was sedimentation happening in that place. It was quite dusty. And on every year, about 1 millimeter of sediments was forming on the surface, so enduring the ground underneath. And in such matter, over the course of, let's say, 40,000 of years, there was formed these sediments. And if you zoom in, you see that they contain lots of roots of grasses. And that's the grass which mammals ate, I don't know, 20, 30,000 years ago. And that's what happened. Then, when Pleistocene was over, Holocene became, climate got warmer, and humans entered the Arctic. And this quickly led to decline in number of animals. And without animals, grasses and herbs quickly lose their competitive advantage against mostly shrubs and trees. And already several centuries later, the Arctic began to look like that. Very low productive ecosystems with little to no animals. And right now, this ecosystem doesn't carry any profits neither to humans nor to animals. And the only creatures there in big numbers are mosquitoes, which doesn't really make me happy. Okay, now coming to the solution. If in the past humans managed to destroy this ecosystem by reducing the number of animals and keeping it low for extended period of time, we will do the opposite. We will artificially increase number of animals and support those animals long enough for them to establish high productive pastures once again. And that's pretty much what we do. Back in 1996, Yakutian government provided us with a relatively big territory. Partially we fenced this territory and started to bring animals in. So first we started with animals we could find locally, like moose, Yakutian horses, and reindeer. And for other animals, we had to go into some complicated expeditions, and I will show just some slides of some of the expeditions. And we already did 3 expeditions to bring bison, American steppe bison, to the Pleistocene Park. And we were picking them up at the lovely bison farm in Denmark, where they kept for meat. In Europe, they were going on the fancy truck. There they are. Then in Russia, at the Smolensk, at the border, we were shifting them to our local transportation, which we specially designed for the long distances, because, you know, to get to the Pleistocene Park, it usually takes around 30 days in travel, and you have to take care of animals properly at the time, so they have to have enough food, forage, it has to be clean, enough air, and they can move. And so all that is required. Also, as you go east of Russia, you know, the quality of roads is getting down, and you have to take ferries sometimes and go along the mountain ridges and gravel roads. And finally, kind of the final road destination in our case, it's a little river port, Simchan, in the very east of Russia in Magadan region. And it's the very upper stream of the Kolyma River, where these animals are getting put on a small barge. And the last 1,500 kilometers, the animals are transported along the river and getting straight to the Pleistocene Park inside the fenced area, where animals are released. And here's one of the herds when they just got released, and there is some of the animals already a couple years after living in our place. I want to say that bison actually one of the most successful animals in the Arctic of the ones we introduced. So we already did 3 expeditions, and the very first herd we brought already given kids for 3 years in a row, and we are very happy about that. Then this year we did 1 expedition to bring muskox to the Pleistocene Park. That's a picture taken in Yamal. There is a national park, and in exchange we brought them bison, and they allowed us to get some muskox from them. And muskox we get in the different route, so we were taking them by the truck to Arkhangelsk. That's a river port in White Sea. And from there, animals was going along the Arctic Ocean all the way to the Pleistocene Park. And September this year, we successfully released them in the park, and they are happily roaming there right now. So, as I said, the idea that animals are doing, so we are bringing animals and they are doing the job of creation pastures for themselves. That's kind of a rather interesting pictures of the same location and how the animals shape the landscape in just 8 years. Okay, but what's the reason for us to do that? Of course, it's nice to have rich nature. It's nice to restore what is what's once. It's might give profits to humans. But our main idea is that we show that this ecosystem, same as like in the past when Mama Steppe was a large ecosystem and did play a role in the world climate, now we can restore this ecosystem and they can play a role in the modern climate as well. And there is 4 reasons for that. First of all, as we discussed, permafrost is a huge threat right now. And we want to stop permafrost from degrading. And one of the ways to do that is by getting rid of the snow in that landscape. Because snow is acting as a good heat insulator, which doesn't allow soils and permafrost to freeze more. And there is no easy ways, it seems, to get rid of snow on the big landscape, unless you have pastures underneath. And if there are animals, they will come to that place and they will dig through the snow and they will compact the snow and making it dense, and at that, snow lose most of its heat insulating abilities. And permafrost can cool substantially. I think realistically we can get 2 to 3 degrees cooling of permafrost at that. Second effect, it's called albedo effect. The lighter the surface, the higher portion of energy is reflected back to space. And grasslands are much lighter than shrublands and forests. And especially that's pronounced in our region, somewhere in April and May, when we have already enormous amounts of sun energy entering the atmosphere. But at the same time, all the pastures are still covered with snow and reflecting all the energy back to space. And trees and shrubs are dark, standing, and getting heat and absorbing the sun energy and even melting the snow around them. And the third thing, as a main nature-based solutions is always considered planting of trees. And in warm climates it makes sense, but in the Arctic, trees are short, sparse, and grow for a very long time. And recent years show that forest fires are kind of really bad and emitting carbon in a very fast rate. So what can we do? We cannot store much in above ground vegetation, but we can store quite a lot in below ground. And what's the point? We have very cold Arctic soils. They're frozen most of the time, and at that decomposition in these soils is very, very slow. So if you make any sort of input of carbon into these soils, it will stay there for millennia. And that's how can you accelerate that? Right now in the Arctic, most of the roots of modern vegetation is located in the very top 10-20 centimeters of ground. So most of the lichens don't have any roots. Large forests, large trees have all the roots along the surface. So all the organic material is located only along the surface. If you get shrubs, grasses, herbs, all of them grow very fast. They need lots of water, and they are forming deep root systems. So you're taking that greenhouse gas from the atmosphere with photosynthesis converted into organic matter and bury it deep into the ground. And out there it's entirely protected from forest fires. No forest fires will take that place because there is no forest, first of all. And we actually did some measurements on that, and we estimated how much carbon we have in our oldest fenced area in the park. And first thing we saw that indeed the regular mossy forest, which we have right now in the Arctic, as the dominant ecosystem, contains twice less carbon compared with what grasslands and shrublands contain in that place. And also we saw that our work in the places in the park with getting animals in and them starting to accelerate nutrient cycle in this ecosystem is really helping to sequester more carbon into the ground. And here is how the carbon is changing with depth. The blue line here, it's a regular forest. So we see some carbon is at the surface and goes down as we go, I don't know, 80 centimeters below. Green line, it's pretty much how the place where we have the park looked like before we start our experiment. So there is much more carbon, but it's slowly declining with depth. And the red line, it's our effect within the place in park where you see we actually have increasing carbon content with depth. So because as you go deeper, the decomposition is getting lower, you can have even like more carbon below. And the lower it is, the safer it is. So it's a very strong potential to sequester lots of carbon. And to put these graphs into some context, I first of all decided to compare the work we did with kind of my personal carbon footprint. And I estimated how much carbon I emitted in the 15 years. And then I saw how much carbon we sequestered within this tiny little 40-hectare territory, which we have in the Pleasant Park. It's just a small portion of Pleasant Park, actually. And totally, finally, I saw myself quite a carbon negative person, and I'm rather happy about that. And for your understanding, so majority of all the activity was shown here, which was started from 1996, was maintained entirely by the kind of resources of my family. So my father who started that, myself, and all the resources which we have, we were making, running Arctic research station doing fundamental science. And as you could guess, it's not the most profitable full business. So we actually always had very little resources, and still we did achieve quite a lot. And if you have kind of, imagine what it can be done with proper resources. And fortunately here, now we actually, our Pleasant Park project is getting momentum. And starting this year, we are getting, starting to collaborate with Andrei Milchenko, who was here foundation. And already start next year, we are planning to increase territory of our Pleasant Park 10 times, increase number of animals 10 times, do all sort of research to prove the concept. And we are inviting scientists to join us on that. And the ultimate goal is to create an ecosystem big enough and to create one of the largest wild ecosystem, the richest ecosystem, and the ecosystem which will be able in the future to mitigate global climate. And I think that's it. Thank you. Oh yeah, and announcement. I think today at 17:30 there will be another panel on the Pleasant Park, and I think there will be more information. I will be also giving another talk with more slides. So if you're interested, welcome.
Thanks so much, Nikita, for a very interesting presentation. Indeed, it's a very impressive project, actually, what you develop in Siberia. And also it has clear connotations, actually, with what we are going to discuss after lunch today with similar projects in carbon supersites. We have talk by Alex Yeliseev, but I suggest first to have a coffee break, which is served already. And then we will switch to Alex's talk, and he will broadcast actually from virtually from remote source. Okay, so let's take 15 minutes instead of 20. It's okay? Thank you.
Так, я готов.
Hello. Well, I suggest that we continue somehow. Take your seats on the floor, please. Да, конечно. Dear participants, may I kindly ask you to take your seats and we will continue. Nothing wrong, by the way, to take a cup of coffee actually and to sit with it. Because we have quite a dense schedule. For this reason, I suggest to continue. Guys, it's also my statement regards to you as well, guys. Sasha, Sheriff, that would, I say in general that we have to continue. Well, so I suggest to get the next talk by Alex Yeliseev, and he will speak about the global carbon cycle and its role in climate variability and change. And Alexei will broadcast remotely. I hope it works with our technologies. We'll just...
Okay. Thank you, Sergey.
Yeah, okay. Yes, okay, great.
That everybody hears me. Let me share my screen. Is it okay?
Yes, it is.
So,
That's
thank you. Dear colleagues, good day. And the topic of my presentation is the role of the global carbon cycle in climate variability and change. First of all, we have to discuss some motivation for my talk, because in the latest IPCC report, it was stated that the state of the global carbon cycle is very unprecedented. I mean, the present state, because it was stated in the latest IPCC report that the atmospheric CO2 concentration value is unprecedented, at least for the last 1 million years. And CO2 growth rate in the atmosphere is unprecedented for the last about 60 million years. Sure, during this 60 million years, it was time interval with much larger carbon concentration than now. But nonetheless, the growth rate which we observe now is very unprecedented. It was not observed or reconstructed for at least the last 60 million years. And the major driver for this change in carbon cycle are anthropogenic emissions. Anthropogenic emissions because of using the fossil fuels or coal, gas, oil, and some other activities. And another important source which gives around 10% of the global carbon emissions is the land use change emissions. For me, and I believe for our meeting, it is important to say that the contribution of Russia to the global carbon emissions is not so pronounced, about 3% during the last 2 decades, and it diminished by a factor of 2 or 3 during the 90s, partly because of the collapse of the Russian economy during this period, and partly because of investment in more green technologies, in less leaking pipes, and so on. And this changing state of the carbon cycle is reflected in very different variables. For instance, there is a positive net length CO2 sink, which currently amounts above 2 petagrams or 2 gigatons per year. This increasing length CO2 sink is mostly driven by the overall greening of the Earth's surface, and this is reflected into proxy for the state of the terrestrial ecosystems. This is NDVI index, which is a proxy for the green phytomass, and so the green phytomass is increasing now. And another is near VC anomaly, which is a proxy for the terrestrial photosynthesis. So gross primary production is based according to this proxy data, as well as based on the direct or inverse calculations with the biogeochemical models. And this is also accompanied by the positive carbon uptake. Take care that the sign convention between right and left panels is different. So here, I mean, at the left panel, negative values again correspond to the ocean uptake, and this uptake is now quite close to the land CO2 sink, which is from about 2 petagrams per year to 2.5 petagrams per year. And but this is only the part of the story, because the major thing is how does it affect climate. And carbon cycle affects climate primarily via two important feedbacks. One is the carbon concentration feedback, which is a direct impact of the growing CO2 on the state of the Earth, of the terrestrial ecosystem and on ocean uptake. For the terrestrial ecosystem, this is reflected in the enhancement of the terrestrial photosynthesis by the growing atmospheric CO2, and over the ocean, it directly changes the particle pressure of the carbon dioxide in the atmosphere. I mean the lower atmosphere, of course, and this enhances the oceanic uptake. And another, I would say, more misty story is the carbon climate feedback, because these feedbacks result from the changes of the state of the terrestrial and carbon loops of the global carbon cycle, and sure, these changes depends on changes on climate changes, or I mean temperature, precipitation, winds, and so on, in a quite complex way. And all these effects are collectively referred to as carbon climate feedback. As the carbon concentration feedback is negative, I mean, it enhances the uptakes, both oceanic and terrestrial uptakes, and somewhat suppresses the build-up of the CO2 in the atmosphere. So it retards its growth and retards the associated climate changes. But the carbon climate feedback, despite it is rather uncertain, as we this is positive, and it mostly enhances the build-up of the CO2 in the atmosphere and the associated climate changes. If we look at the geography Again, we consider that these are very, how to say, very inhomogeneous. This is not so for the carbon concentration feedback. It is it has the same sign over the most part of the globe. But for carbon climate feedback, the complexity of the overall of the underlying process leads to sign changes between tropics and the northern extratropics. In the tropics, this feedback mostly enhances the buildup of the atmosphere, and it is exhibited at a global level as well. But over the extratropics, it again separated the buildup of the CO2 in the atmosphere, mostly because of the lengthening of the growth season, because of the sea ice loss in the Arctic Ocean, and so the Arctic Ocean starts to take up the CO2 from the atmosphere, and so on. So this feedback is very inhomogeneous. And if we estimate both positive and negative feedbacks, they assume close to zero. But this is somewhat misleading because this is compensation of two feedbacks which are, how to say, not only in homogeneous space, but they also to be expected in homogeneous in time, because the carbon concentration feedbacks is expected to saturate probably in the middle of the century, but the climate carbon feedback would only be enhanced because of the ongoing climate change, ongoing and expected climate change. And according to a large amount of simulations, I could show here my own old simulations, but they're quite characteristics of the cell. The carbon climate feedback amplifies the response to anthropogenic emissions by about 10 or 15%. This is not so large, but this is certainly not negligible. Another issue that some feedbacks are understudied. I mean, some processes consistent of the climate carbon feedbacks. Again, returning to the estimate of land carbon response to climate, we can see that at first there is some reduction of uncertainty from CMIP5. I mean, this patchy plot and CMIP6 models, this brown plot. But again, this is because most CMIP6 model, in contrast to the CMIP5 ones, now include interaction between carbon and nitrogen cycle. This interaction somewhat suppresses this feedback, but now we have another way of model development. I mean, the implementation of interaction between carbon and phosphorus cycle, and this would, I expect that would enhance uncertainty, because phosphorus cycle is mostly important in the tropics. And even for the contemporary models, the most uncertain feedbacks are emissions from natural forests and their response to climate, and emissions from permafrost. And let me show some example. This is the example for interaction between carbon and nitrogen cycles in some artificial numerical experiments with the land surface models, including biogeochemistry. These models were fed up by the atmospheric concentration increase from the present day value up to 550 parts per million in volume, and we can see very large diversity of response at the local scale between these 5 models, and at the global scale as well. This is the enhancement of the net primary production. And this is due to very large differences in impacts of mineralized nitrogen to the terrestrial primary production. And so this reduction of uncertainty, which is exhibited in early plots, is somewhat misleading. Another issue, this is from CMIP 5 Earth system models, because I didn't see the respective analysis for CMIP 6 models yet. This is changes of the burnt area, upper plots, and the associated CO2 emissions into the atmosphere from 9 models. These models are not completely independent, because you can see they even came from the same center, so they share a lot of code, and some other models also share land surface schemes. But nonetheless, we can see that there is a very large diversity for the behavior of natural forests in models, even for both historical period. The left had about two-thirds of each graphs, and in the 21st century as well. Some models show the decreases in the burnt area and in the associated CO2 release into the atmosphere. Some show decrease. This is exhibited both for historical period and for the 21st century as well. So the situation is quite diverse, and this part of the modeling is far from being settled. Another issue is the possible release, CO2 release from the zone permafrost. This is quite consistent with the talk by Nikita Zimov. Again, this is just one model, and just one land surface model, JULE, developed at the Hadley Center, and another is working in Missouri. And this is driven by a simple climate model, but this is not so important for the purpose of the study. And the most uncertainty is, again, in the interaction between between the carbon and the nitrogen cycle, because it is unclear what would happen when the deep layers, or when the deep permafrost is lost. I mean, whether the substrate which is included into the carbon into the active carbon cycle is of good quality or bad quality according to the availability of the mineralized nitrogen. You can see this two plots. This is the same model, but with a different consumption of the layer with a nitrogen-rich substrate, either 2.5 meter or just 56 centimeters, and the difference is very pronounced. But nonetheless, for moderate and for high anthropogenic emissions. This is just this is not more than 10% from the basic warming. These emissions give the value is somewhat larger for RCP 2.6, and this is nonetheless is somewhat easy because this feedback is certainly understudied, but it is not so pronounced, but again certainly not non-negligible. There were some estimates for some attempts, I would say, for estimating this climate carbon feedback from observation, from past reconstructions, and from the historical data, and all these papers, actually, we just a handful of them, leads to much weaker carbon climate feedback parameter respective to the existing land surface models, but this parameter increases by magnitude for larger time scale, and they also depend on the basic climate state. So it looks like contemporary models, while despite giving quite diverse estimates for this feedback parameter, still more or less realistic. And another issue, probably the last issue, not last, I'm going to show you is somewhat how to say, unexpected dynamics of the Earth system because of interaction between climate and carbon cycle. This is a quite well-known plot that, according to the borehole data and according to the paleo reconstruction for the last millennium, temperature, atmospheric CO2 by several centuries for ice core data and by several decades for the last millennium. And according to this, it was stated that all climate models, all Earth system models are wrong, and ongoing warming has no common with the anthropogenic greenhouse gas emission. But, excuse me.
Alexei, we have quite short of time actually, so can you come to conclusions, please?
Okay. Then I will come to the conclusion that the carbon cycle is very important for modifying the climate response, and this modification could be as large as 10%. Nonetheless, the effects are regionally dependent, and most uncertain and most understudied issues relate to the interaction with other biogeochemical health and simulation natural fires. And the thing which I was forced to miss in my presentation, that in the interaction between climate and the carbon cycle would lead to very unexpected and to very counterintuitive dynamics of the whole Earth system. So thank you very much.
Thank you. Thanks so much. One short question. I can allow for one short question. Alexei, can you hear me?
Yeah.
Yeah, my very short question, very short answer. For global carbon budget, ocean and land, for which domains the uncertainties are higher?
If you talk about the contemporary fluxes, they are quite comparable. If we talk about the stocks, it depends on definition, because for the carbon cycle at centennial or decadal scale, they again comparable, but for the carbon cycle at the geological time scales, the oceanic domain is much more important, certainly.
Thank you. Thanks. Thanks again. So our next speaker, it's also online, Alexander Gelfand. He is a hydrologist from Institute of Water Resources Moscow, and he will speak about the climate change impacts on water resources. It's connected now? Yes.
Thank you. Have I
Thanks.
shared my presentation? Okay. Dear Chairman, dear colleagues, good morning. First of all, I would like to thank the organizers for inviting me to give a presentation in such a high-level conference. I'll begin from some preliminary notes about water security and its centrality in adapting to and mitigating climate change. I'll continue with a brief compilation of modern ideas about the ongoing changes in water resources and flood risk, mostly on the basis of the last IPCC assessment report. I was one of the leading authors. And then I will talk about the question, how confident are we in our estimates of the climate change impact on river runoff in the context of water security. Water security is globally recognized as one of the imperatives of global development, and the threats to water security are considered some of the key factors of global risks. In broad terms, water security threats come down to three main problems: the lack of water, hydrological scarcity, the excess of water, floods, and the low quality of fresh water. There are at least three reasons for the centrality of water security in adapting to and mitigating climate change. The first one is that approximately half of the world's population are assessed as being currently subject to severe water scarcity for at least some part of the year due to the climatic and non-climatic factors. The second one is, while climate change directly affects freshwater availability across space and time, it also affects water requirements for different uses, such as irrigation, potentially adding to existing societal challenges. And the third one is that a large majority, more than half of all adaptation responses documented for the last decade are about adapting to water-related hazards like droughts, floods, etc. Climate change can affect different, I would say, different dimensions of water security, and at the same time escalates the socio-economic, political, institutional, and other threats in different ways. Most directly, climate change enhances water scarcity following from longer period of dry spells and droughts. And the second most pronounced result of climate change in the context of water security is increasing flood risk owing to rise in precipitation extremes. I will talk about these two footprints of climate change. What changes are registered during the last decades in the mean annual river flows that are freshwater resource? So annual river flows, this is a freshwater resource, this is synonyms. Recent studies showed that that changes in the renewable water resources for the period of observation are generally consistent with the tendencies of precipitation changes, both globally and for the most of the regions. But the assessment of the scale and significance of water resources changes contain large uncertainty. According to a recent global analysis of observation-based stream flow, significant decrease, for example, were found in North and South America, Africa, and Asia, while increases in Europe and Arctic region. Also, you see the prevailing contribution of climate change as compared to human activity in the observed runoff changes was demonstrated for more than half large rivers from 40 analyzed rivers in this paper. In Russia, total water resources for the last decades have increased, but only 5% compared to the previous period. But this increase is not statistically significant, of course. However, changes in renewable water resources vary greatly across Russia, from a statistically significant decrease in some southern regions, for example, in the basins of Don, Kuban, Selengai rivers, and some others, to an increase in the rivers of the Arctic basin. A few words about a hypothesis of the dynamics of water availability that has been widely discussed in the media. According to this hypothesis, as a result of the observed climate change, the arid regions of the world become more arid and the humid regions more humid. The analysis of observation data and modeling results shows that for those regions of the world where decreasing water resources may have the most dramatic socio-economic consequences, this hypothesis is not confirmed. Now, about the ongoing changes in floods. There are a lot of observation-based confirmations that the global warming is accompanied with increasing frequency, intensity, and duration of extreme precipitation in different scales, and you talked about this many times. But at the same time, the expected response of hydrological systems to these changes is far from obvious. It means that despite an increase in extreme precipitation, there is a great diversity of empirical assessments of rainfall flood responses to the ongoing precipitation changes. And here, let me quote outstanding hydrologist Professor Kundzevich. Although media reports of both floods and global flood damage are on the increase, there is still no Mauna Loa-like records that shows a global increase in flood frequency or magnitude. In the this is a Mauna Loa record about increasing of carbon dioxide in the atmosphere, concentration of carbon dioxide. Also in Russia, we see also that heavy rainfall was decreased for the last decades, but we do not see any increase in snowmelt or rainfall floods for the large regions. In the context of water security, the challenging issues arise. How do we move from global estimations to local decisions in water management and flood protection, because we need to make a decision on local scale. And do we have enough evidence to develop mitigation adaptation measures? In order to increase our confidence in climate impact assessments, we need to analyze these two problems. These problems are well researched in climate studies, but not so common for hydrological community. Of course, I'm saying about detection problem and attribution problem. The detection problem relates to the evidence that the observed changes in river runoff are significantly different in statistical sense from its natural variability. That is, it is unlikely that these changes may be due to the natural variability of the hydrological systems. So the detection problem is poorly statistical problem, but when we are talking about mechanisms of the changes, we need to solve the attribution problem. This is the problem of determining the most probable causes of detected changes and proof that these changes do not result from other physical possible causes. In order to the detection of changes in the observed streamflow series is a challenge because it is complicated by at least three circumstances. The first one is high natural variability, against which it is difficult to distinguish the peak as a rule climate change footprint is the streamflow data series. The second one is additional effect of other than climatic drivers. You know that river runoff is very influenced by different anthropogenic impacts. Some of them is urbanization, deforestation, and so on. And these impacts may interrelate and or noise the climate signal. And the third one is that short streamflow records results in increase in sample variance and a decrease in the efficiency of statistical tests, especially on the inherent low signal-to-noise ratio. So just an illustration of the last point, low density of the hydrological monitoring network and shrinking the existing network are more than a serious challenge when solving detection problem for most part of the globe. Here the conditions are listed that the streamflow series have to meet in order to mitigate the detection problem. Together with the colleagues from Moscow State University, we applied these recommendations in order to obtain statistically stable estimates of runoff changes for hundreds of Russian rivers, and here you can see illustration of these exercises. Revealing the climate footprint and the detected streamflow changes is of course, more challenging problem. We proposed the solution based on hydrological modeling experiments. The idea is to compare simulated hydrological responses to observed and counterfactual without anthropogenic signal climate data. The statistically significant difference between the simulated responses is considered as an evidence of the climate change impact on hydrological changes. Just two examples. The trended climate data developed within the EasyMap were used to provide that the ongoing changes in river flow detected for several Russian rivers are caused by climate change. Particularly we found that the long-term hydrological drought in the Selenga River basin, this is a very deep drought for more than 15 years. So this long-term hydrological drought in the Selenga River basin would not have occurred in the absence of anthropogenic greenhouse gas emissions. I'm move to conclusions. The existing water management and flood protection measures are based on the hypothesis of stationarity of climate and anthropogenic impacts. That is, it is assumed that the observed behavior of the hydrological system will not change in a probabilistic sense in the future. However, Given the ongoing changes, this hypothesis needs to be tested for each specific river basin, not globally, not regionally, but for each specific river basin. If directional changes in the river water regime are detected over the observation period, the hypothesis is rejected, and then the task appears to attribute these changes to climate drivers. Solving the detection and attribution problems at local scale opens an opportunity for justified improvement of decision making in the water sector. Thank you very much for your attention.
Thanks, Alexander. I can allow for one very short question on the water resources and hydrological cycle. We have two talks which will not be presented at consult by Olga Solomina. She is unfortunately very ill actually for different reasons, and Alexander Makarov, who couldn't get here. So now we will have two model talks, and actually on this point, after a second model talk by Igor Shkolnik, our morning session will be ended and will be quite okay actually with the lunchtime. So I suggest now to switch to talk by Andrei, and he will say something about global models, global modeling. And you can use this mic or whatever.
Okay, perfect. So I'll start my talk about global climate modeling from seasonal to climate predictions. And first of all, I would like to say some very basic things, but I think they will describe the concept of my talk in general. So we have two major concepts. First is the weather, second is climate, and they're very different actually. So maybe, of course, everyone knows this, maybe not. So what is weather? Weather is just a specific state of Earth system at some given time moment. Actually, if we could have live ensemble of lives, we would enjoy this multiple weather at any given moment. But unfortunately, we have just one weather realization and at any given moment. And basically, the climate is the set of all of those permitted states of the climate system. So weather is just a point in this space of the system. Of course, it's very complicated because it describes all the meteo variables like a three-dimensional temperature, weather, wind speeds, humidity, and so on. But climate is much more complicated because it's basically the set of all of those states. So the first is state, the second is just a point. Sometimes people define so-called climate in narrow sense as basically climate average, and we will not mention on that. Okay. So now, what is the weather forecast? Basically, we have some knowledge about the current state of our system from observations, or maybe we just know it. And also we more or less, with more or less good accuracy, know the equations that governs our system, so we can make a prediction. But because there is no exact knowledge about initial state, and there is no exact knowledge about the equations, it's, very, very quickly we have some error and some uncertainty about our prediction. So if you want to make any forecast for the lead time, say, larger than a week, we need ensembles. So it's a basic point. We need ensembles to do some medium range and longer range forecast. And what is the climate change forecast? Basically here we need some acting forcing on our system. And this forcing should change with time. This changing forcing, say greenhouse gases concentration rising, push all possible states of the system in some direction. In the case of global warming, we have basically warmer states of the system in general. Of course, there are huge amount of them, but in some sense they're a little bit warmer. And again, to predict changes of the climate, we need ensembles to basically capture the motion of these sets with this changing forcing. So in both cases, we need ensembles. Okay, and as already follows from my two first slides, basically we have two sources of predictability. First, if we know the position of our system at any given moment, we make use of this information to make a prediction. It's a usual weather forecast by hydrometeor centers. And from the other point of view, if we have some changing forcing and its action may be slow, but it accumulates in the future, we can extract this information and also make prediction, and this is predictability from the second type from boundary condition or external forcing. So I need also to mention some sources of long-range predictability longer than, say, 3 to 6 days. First, as I told you, it comes from the initial conditions. And basically, it's low-frequency variability of atmosphere, ocean, and couple climate system. From some atmospheric phenomena, one can mention Pacific North Atlantic variability, NAO, North Atlantic oscillation, maybe some Madden-Julian oscillation with a period maybe already 45 days, and maybe the longest atmospheric feature is a quasi-biennial oscillation with a period of about 2 years. And of course, ocean modes like famous ENSO, maybe more less known Atlantic multi-decadal variability or Pacific decadal variability gives you the time scales of something like 10, 20, and more years. And this is the source of sorry? Yeah. So these modes are sources of the longer range predictability. And one more look at this concept pictures. Here I have a axis over time. Here's day, week, month, season, year, decade, and century. And the shading of these colors gives you the amount of predictability. The brighter, the more predictability. So here initial value problem, then we have some low predictability from initial values at seasons, maybe years, and then forced external forcing predictability starts to kick in. So it's a kind of gray zone. And my third statement is that if we want to predict, So my third statement is if you want to predict climate changes, probably we need to also do some more or less decent job in predicting the state of the system on year or seasonal time scales. So let's look how we do in this department. Just a demonstration of what climate models are. They basically are based on the systems of a partial differential equation, Navier-Stokes equation. We have some grid, approximate deals on grid and put in the computers, add some physics. And actually, this is the approach that was the first successfully completed by Manabe and Brian, and they got basically a Nobel Prize for that. And also in USSR, we have this not many years later. It's the 80s, and already there is a general circulation model. Nowadays, we have, of course, much more complicated and sophisticated systems. We have atmospheric ocean size dynamics, atmospheric ocean boundary layer, sophisticated land surface model, aerosols, and so on, and other optional things. And also, we are participating in many IPCC type of projects on comparison of climate models. But first, I will start from the seasonal and decadal predictions. So typically, what we do, we take some real state of the system from the analysis, say, we do this anomaly initializations. This is kind of useful procedure. And then we put into the model and do the seasonal prediction or decadal prediction. So, of course, we have ensemble integration. For the seasonal prediction, we integrate our model for 4 to 9 months. And we have experiments every month in this kind of time frame. And this is how we perform. It's so-called RMS error for temperature to meters forecast. And here is the time. This is this RMS. Red is INM CM5 model. And those are other models from the weather forecast, from other weather forecasting centers. And the low is better, of course. And we see here that it's kind of doing a good job, especially if we think that this is a specific centers to do the prediction. And they have a better resolution and better initialization and so on. So far it's quite good. There are a couple of pictures how this model perform in some specific cases, like a heat wave in Europe, and it actually can predict it quite with a lead time something like a month or 2. 3 minutes. Okay. So I'll skip this. Then we have a decadal prediction. Basically, everything is the same, but we integrate our model much longer. And then, of course, compare what will happen in a year or 2 or 5. And this is, again, a demonstration of how model performs. Basically, if we use information from the forcing, from the changing greenhouse gases, and from initial state, we have this kind of picture, temperature at 2 meters SLP. If we use just right-hand side forcings, we have this kind of prediction, and this is added value from use of the initial conditions. So, in fact, this is quite better. Okay, again, so far so good. This is, I'll skip it. This shows how we perform in the ocean. It's a heat content in 300 meters, some good things. Again, and what is with this climate integration? We start from 1850 and do this standard SMIP6 experiment for 165 years. Black is a globally averaged 32 meters from hot crude reanalysis data. Red curve is basically ensemble mean for this all of these experiments. And again, you can see there's quite a good correspondence. Then now we have a new version of the model. And in fact, in red, I show that we have some major improvement in this INM6 with respect to INM5. Temperature 2 meters, temperature 850, H 500, so RMSE is much better. And then, I don't know how much time I have. Model new version of the model performs much better with respect to all these SMIP6 other very good SMIP6 models. My final picture is this. What if we do this 21st century prediction with both of these models and compare it with this other SMIP6? And what is important here, again, it's 1850. Now this is a 2100. And INM CM5 is here. It's quite of a low sensitivity model. And now INM CM is here. It's 1.5K more than this one. And these are other SMIP6 models that are quite famous from their origin. So my conclusion is this. We have a decent seasonal prediction with INM CM5. We have decent decadal prediction with INM CM5. And basically we can show that climate characteristics of INM CM6 is better than INM CM5. So can we trust it? Its 21st century prediction more? And my answer to this is, first we need to do seasonal forecast with INM CM6, decadal forecast with INM CM6, and then we can give you a definite answer.
Thank you, Andrei. Stay here. Thanks for this nice presentation. If there are any questions, please.
Yes, please. Use mic. Thank you. Thank you very much for the presentation. A question regarding comparable advantages and disadvantages of Russian climate models versus international peers. Are there any aspects of the climate modeling that we understand better?
Thank you.
Well, of course, all of these models are based on the more or less same principles. What we did with INM CM6, we basically improved cloud parameterizations and little bit parameterizations of the atmospheric boundary. And basically now it looks like we understand how the model with high sensitivity works. Well, on Sunday, there will be a presentation about this VIP-Gazette project, and I will tell you that how we construct different models. Also, we do a sophisticated land surface modeling, and those swamps, they will be covered by it. Yeah.
There will be also regional climate modeling talk actually right next after Andrei. Andrei, I have a conceptual question to you. The climate is changing. So for instance, okay, in a couple of decades, or probably in a century, 2100, we do expect that we will have more wet atmosphere just for the reason of warming. Could it be that the skills of the solution of classical Cauchy problem, initial value problem, in fact, will also change, and that the skills of weather predictions, actually, as initial value problem, may also change with climate change? What do you think? It's a provocative question, but nevertheless.
Well, I don't think so. I don't think that our climate will change that much that will affect short-scale prediction. Is it the answer?
Okay, it's your answer. My premonition. Okay, it's not my view. It's more like premonition. My premonition is different. That probably we will have different scales of weather prediction. Probably smaller scales, shorter predictability will be available if the atmosphere is becoming more wet, because the moisture is a fuel for the atmosphere in terms of initial value problem. Okay, we can discuss this. I know. Yeah, and it's to answer this question, it's a quite complicated thing because even if you store the weather forecasts, you cannot analyze them because it's a question of attribution. Because actually, it's hard to distinguish in between actually this effect, if it exists, and the effect of the just general improvement of skills of weather prediction over a very long time, like for the present climate for several decades. Thank you. Thanks so much. Thanks so much again. And now the last talk for the morning session, Igor Shkolnik for regional climate modeling.
Thank you. Okay. So can you start my presentation? Okay. Good afternoon, everyone. So my talk is about Central Asia, but actually some outcomes of this study may be relevant to the region where we are here right now. Okay. Oops. Oh, yeah. This one. First of all, I will inform you that we have developed the system of regional climate models for the three regions, the Arctic, the Russian territory, mostly the northeastern Eurasia, and the Central Asia. But the region of interest is right here. The climate changes, the global climate change will affect in drier conditions over these regions, affecting the economy and mostly agriculture. These regions include southwestern Russia and Central Asia. Here's the changes of maximum number of consecutive dry days. The consecutive dry days is a good indicator, actually, of droughts. And you can see here the changes derived from observations on your left. The model prediction for the mid of 21st century is on your right, and you can see that there is a qualitative agreement between the model simulations and observations here, suggesting that the model simulation is physically consistent with what's going on in real climate. Okay. Unfortunately, we have the observations only for the Russian territory, but the Middle Asia is here. The Middle Asia will undergo the same changes here, suggesting that there is a huge impact on the local economy. First, back to the Russian territory, we carried out the study for the major arable lands in Russia. They are here. They are in three major districts here. The color, the depth of the color, denotes actually the size of the area of arable lands. And we predicted using the regional climate model with 50 ensemble members and sophisticated crop model, they drop in the yield of wheat over these regions by the mid 21st century, by the late 21st century as well. And you see the changes are up to they actually are in the range of 10 to 20% of drop. While the Middle Asia, the effect of climate changes in Middle Asia is even more prominent. You can see on the left the changes in the irrigated areas in Middle Asia. It's steadily increasing. Unfortunately, I don't have the latest data here. They finish in 2010 here. But the problem is you can see that in the center of the map of irrigation areas here, the problem is that the lands of crops there are very small. They're actually much smaller than the size of modeling modeling grid, which is 25 by 25 kilometers. And you can see here in the center, the color denotes the percentage of the grids of modeling grid cell covered by the irrigated lands in the Middle Asia. And the light color, the white color doesn't mean that there is that there is no irrigation lands. They just are about 1 or 2% of the modeling grid, so that we cannot predict the changes of the climate changes there for the irrigation areas there using the 25-kilometer resolution, because they are not explicitly resolved there. There are a few words about experiments. The modeling domain includes 97 to 181 grid points in the horizontal, with 25 unequally spaced levels in the vertical, and there are 30 simulations, 10 years each for the late 20th century, and for the future period, it's 2050, 2059. The model simulations included perturbed initial conditions in the atmosphere and land surface. The model is driven by MGO atmospheric global climate model. The experiments include the prescribed SST sea ice concentrations evolution derived from the CMIP5 models. These are 3 models. And totally we have 300 years of simulations under RCP 8.5 scenario. And as a next step, we use the downscaling of RCM projections using the atmospheric boundary layer model, which has much finer resolution. And by this, we can describe the future changes in water demand across irrigated lands, which are very small in Middle Asia. Okay, here is the structure of high-resolution boundary layer model, which is driven by the model, the RCM ensemble here. So I won't stop here for longer. The model has 151 levels in the vertical in the boundary layer, and provides the detailed descriptions of the thermal and moisture conditions in the boundary layer. So this model allows us to simulate changes in hydroclimate across very small pieces, very small plots of land in Middle Asia, which are irrigated. Here's the results. Shown here projected changes in surface area temperature and precipitation by the mid-21st century for warm season. On your left is there a pointer? I mean the pointer.
Oh, pointer, no.
Oh, yeah.
Pointer doesn't work on this.
Okay.
It works, but for the reflectivity reason.
Okay. The changes in surface temperature provided by the standalone RCM simulation is on your left, and on your right is the same, but for irrigated lands only. As you can see, the changes in the temperature are smaller because of evaporation. We estimate the changes in precipitation using the standalone RCM simulation close to 0. Here, dots denote the grids where the simulation, the changes stand out against noise here. The noises here is the unforced climate variability, typical for the ensemble simulations. Okay, these are changes in evapotranspirations as simulated by standalone RCM on your left. the changes for the irrigated lands on your right, you can see the evapotranspiration and water deficit are much larger because the soil of irrigated lands is saturated. But the question is, how much water will we need to provide the same level of moisturizing the soil? Okay, here's the ensemble matrix. It shows the effect of climate variability, which is typical for the model ensemble. So you can see the changes in water demand here as cubic meters per hectare. It strongly depends on the member. So there are large changes in some ensemble members exceeding 500 cubic meters per hectare, and there are even projected drop in water demand here in some ensembles. So the effect of climate variability is very large. Now we're close to the final result. On the top of the slide is the projected change in irrigation rate and cubic meters per hectare, arranged by different boundary conditions over the oceans. Here there are 3 types of boundary conditions from 3 different global climate models over the top, and you see there is even if the region is very distant from the ocean, there is an effect of boundary conditions over the oceans, at least for the changes in irrigation rate here. And the final outcome is, is here below. This is the 30-member ensemble mean in the projected changes. They are actually in the range from, well, 100 to 400 cubic meters per hectare. It corresponds to the range of 5 to 10% of the current water usage for irrigating the crops of cotton and wheat there. Okay, and here's a summary. So, development of modeling chains from global to regional models to submodels and impact models is an important step in developing effective mechanisms for providing climate information to end users. Because the regional climate models, the high-resolution models are actually the connecting chain between global climate simulations and end users. And here in this study, the downscaling of RCM projection allows one to approach a quantitative assessment of future water demand for irrigated cropping regions, where it turns out to be critical to justify regional development strategies. Here, the projected increase in future irrigation water consumption by the mid-21st century is in the range of, like I said, 5 to 10% relative to its current estimate. In exotic regions like Central Asia or Emirates, for example, there is a need to apply multi-scale downscaling methodologies, including very high-resolution modeling systems to describe the effects of climate change on agriculture. And future assessment should include building larger ensembles, accounting for wider range of forcings and models. It's a good opportunity for the WSRP Cordex Central Asia community under lighthouse activity, something for society. I forgot. Thank you. That's it.
Thanks so much. Thanks, Igor. Is there any questions? Okay, I have a question. When you demonstrated actually this 10 ensemble members, my impression just in section by eye has shown that in the third line actually they're split into two populations with just more or less very similar red, yellow, and very similar to each other, also blue. So does it mean that your ensemble doesn't have a kind of one peak Gaussian distribution or not?
Yes, in a way. That's why, like I said, we need larger.
How many ensemble members do we need actually?
Oh, that's a good question. The larger, the better. Yeah. Maybe 100. So nobody knows. Sometimes dealing with hydroclimate, maybe 1,000 ensemble members is not enough. There is no number for some characteristics, actually. So you can't get any statistical significance in any case.
Well, okay, thank you. Well, thanks so much again. At this point, we end our morning session. We are perfectly in time, by the way, not because of the very good discipline of speakers, but rather about for the reasons that two talks are cancelled. Very unfortunately, as I said, Olga Solomina talk about continental glaciers are cancelled, but people who stay here at the conference until December 10th will be capable of joining talk of representative of Ministry of Science and Higher Education on the same topic about continental glaciers. This will be water day on 11th or 12th, I forgot, 10th. December 10? 10, okay, very good. And the second talk is cancelled by Alexander Makarov about Arctic sea ice. But again, Alexander will arrive here on December 9 and will participate into two other sessions actually on 10th and 11th, and people who stay here on the venue, they will be able actually to join his talk as well. Now we have 90 minutes lunch break. I don't know why it is not served yet, but okay, it should be served. Actually, we ordered lunch boxes and beverages, and in meanwhile, it should come somehow, so you can enjoy free time, fresh air and sun, and then, okay, when it's served, okay, you can also enjoy the meal. Thank you very much. And in 2 p.m., we start a special session on Russian carbon supersites. And there we have only one cancellation, so we'll need to be very strict actually to somehow limit your capabilities to talk for extra time with respect to what is given to you. Thanks. Thank you. So, well, it's time to start our afternoon session. It's 2 p.m. now, 2:02. I'm very sorry for cancelled lunch today. We just visited catering management office and had a very long discussion with them. They said that this is a general problem actually here on the conference. Nearly more than 50% of all orders were cancelled. They point to the reason that actually there is a kind of conflict between our management of COP28 and management of the catering company. And the problem is that COP organizers did not provide enough badges for servicemen who are, and service women probably, who are going to serve this coffee breaks and lunches, so that delivery goes on, but then, okay, they don't have enough manpower actually to do this job. But good news is that they confirmed the afternoon coffee break, 3:30, and they are now working on the issue of the evening reception. During the afternoon coffee break, I will call them and will notify you what are the perspective of this. Well, now we start a session, a special session on Russian carbon supersites. This is a project centered on the monitoring and estimating of regional carbon budgets for different landscapes and different landscape types in Russian Federation. I would definitely recommend everyone on the floor to focus on this new brochure, which summarizes 3-year progress in this project. And my first speaker, Alexander Olchev, he is professor at Moscow State University, and he will give a general overview of this project, and then we will go with as many as 4 more talks which are centered on different supersites. Please, Alexander, it's your turn now.
Good afternoon. Hello, okay. Good afternoon, everybody. I'm very happy to see you here in a very nice city in Dubai in climate conference. Well, in my talk, I would like to say about the first primary results of the 2 years activity of Russian carbon supersite. Russian project, it's a pilot project of Russian experimental supersites, was initiated by Russian Ministry of Science and Higher Education in 2021, has the main goal to obtain representative, highly accurate experimental data on greenhouse gases in different natural ecosystems, that's first of all. And the second goal is to initiate, to develop control technology to for emission and uptake of greenhouse gases in natural ecosystem. One moment, please. Okay, thank you. Well, this project can be classified as very important part of Russian implementation and contribution to Paris Agreement on climate, to implementation of presidential decree and Russian strategy of low carbon development. Well, the Russian Federation is one of many countries what have joined and approved the Paris Agreement on climate. Well, the main goal of this agreement is to avoid dangerous climate warming, first of all, of course, and to stop the global warming and to stop global warming and limit it to well below 2 degrees, aiming to limit it to 1.5 degrees. Another very important point is to achieve actually the balance between carbon released from natural anthropogenic sources and uptake of greenhouse gases, all greenhouse gases, to the second half of this century. A couple of words about low carbon development strategy of Russia. This is actually the main goal of the strategy is adapt of Russian economy to global energy transition, reduce greenhouse gases emission, and achieve carbon neutrality to 2060. Well, among different activities of this strategy, we can find, for example, different activity, and first, I can focus it on the third point is developing technology to increase greenhouse gases uptake and reduce emission from natural ecosystem. Actually, this strategy it's very important because it's assumed it's what natural ecosystem has its very high potential for regulating greenhouse gases balance, and it's very possible to use to actually to achieve this carbon neutrality, and this is highly attractive because it's relatively not expensive comparing to other strategy to low carbon development. Yeah, well, a couple of words about objective of Carbon Superside project. This is, of course, monitoring greenhouse gases in natural ecosystem. This is analysis of spatial and temporal variability of greenhouse gases in different natural ecosystem, terrestrial and marine ecosystem. Development of technology to control greenhouse gases emission, adaptation technology to measurements, application of remote sensing technology, of course, application development of different mathematical models to solve different problems related to greenhouse gases fluxes, and of course, education. It's very important because it's very important ecological education. It's maybe can be considered as a basis for our future development. Well, global monitoring, why we need it? Actually, modern global monitoring network of carbon dioxide fluxes, actually it's about count more than 1,000 stations, current station and historical station. Actually, this station, this network was developed started since 1997 to support NASA Earth observing system, actually satellite system. And you can see in this map the different distribution of spatial distribution of the station, and you can see that Russia is represented by a very little part of the world station. It's about only 20 stations what we have. Actually, nobody say what this station can be used for analysis, for calculation of regional and global budget. It's not the task, it's not the problem. This station is used as representative points which used for calibration of satellite data. And using satellite data, we can describe the total global and regional fluxes. Like, for example, you can see in the slides from the right side. Unfortunately, I can see, but probably you can see it. Well, some example of estimation of the fluxes, monthly fluxes for different seasons using Chinese satellites. Well, in our study, we used a monitoring network for greenhouse gases. Well, this is integrated system that include in situ terrestrial and marine measurements and remote sensing monitoring. Well, monitoring, remote sensing includes some information about, it's a little bit noisy here. Include remote sensing information from satellite and unmanned aero vehicles, which equipped using different equipment. And of course, terrestrial net observation of different carbon pools in vegetation and in soil, and direct measurements of fluxes, all possible different fluxes, carbon dioxide, methane, other fluxes, isotopic composition of the air, and other many numerous tasks. Well, what about what already has done? Well, we have now, it was project run already 2 years, and we have a main focus on different type of terrestrial and marine ecosystem. For example, this slide illustrates flux tower, eddy correlation flux measuring tower, which focus on measurements on main carbon dioxide and water vapor fluxes on K forest ecosystem. You can see here the meteorological tower which installed in Moscow region, Chechen Republic, Khanty-Mansiysk, and Tatarstan. Similar measurements conducted in different agricultural and grasslands. For example, for such measurements, we used chamber measurements and eddy covariance flux measurements. Here you can see the different episode slides of field measurements in the site. Well, similar measurements conducted in wetlands, but I'm not like to say so much about these slides because the next, I think, in today will be a special talk concerning especially a study of greenhouse gases fluxes in wetlands. Well, what about drones and remote sensing observation? Well, this information is very important. It can be used it's very important information. Of course, it can be described using this information the topography, surface topography, vegetation structure, vegetation composition, and vegetation properties. Additionally, if we have drones equipped by a portable gas analyzer, we can describe the spatial distribution of the greenhouse gas concentration in atmospheric boundary layer, and from this data we can solve inverse problem of the remote sensing to reconstruct, to retrieve surface greenhouse gases using remote sensing data. Well, modeling, of course, if you try to retrieve greenhouse gases, we need some modeling approaches. And this slide illustrates an example of complexity of existed greenhouse gases fluxes. Actually, our ground surface is not uniform. It's very heterogeneous, topography, vegetation, and so on. Well, these slides illustrate, well, this is complexity of the fluxes, vertical fluxes. Actually, it's not possible to measure it directly. We can only maybe use some alternative approaches like inverse modeling or direct modeling of the fluxes. It is one of the best way to solve this. Well, a few words about coastal ecosystem study. There are such measurements in Black Sea, in Baltic, in Far East, which focused on actually measurements of carbon dioxide and methane fluxes between sea surface and the atmosphere, and concentration of total and organic carbon in the water, of course. It's very important. Well, I go to the finish today now, and like to say a couple of words about developing technology solution to reduce greenhouse gas emission and increase greenhouse uptake. There are many different possibilities to solve this problem. And of course, it's reforestation, sustainable development, cultivation of distributed lands, peatland revetting, cultivation cultivation, highly productive plants, regenerative agriculture, algae cultivation, and so on. Of course, all this technology has many positive and many, unfortunately, negative effects on the climate system. Well, and what we have now, it's a developing technology solution. What we have already is this example of, for example, in Ventland, revetting of the peatlands in Kaliningrad region, planting young trees in Voronezh. The next presentation will be exactly, I think, about this activity. And for example of Chechen Republic, it's this landfill recultivation. It's very interesting project, of course. There are many possibilities, and of course, probably the last remark, what I must to say. Actually, many such projects, climate projects, actually mainly focused on only carbon sequestration in soil or in plant, what soil. But its effect of any ecosystem, ecosystem influence on climate system in a multiple way, actually, through surface albedo, through net radiation, energy budget, for example, sensible latent heat fluxes, soil heat fluxes, carbon dioxide fluxes, and many other possibilities. And it's only one possibility we must take all different factors which influence the climate. In other case, our estimation can be unfortunately unsuccessful, unfortunately, and it's very important. Okay, thank you very much for your attention.
Thanks so much, Alexander, for this very nice overview of this project. Is any questions on the floor? No questions on the floor. Okay, from my side, thanks, Sasha. I have to say that indeed it's a very challenging thing. And sorry.
Sorry, I could not see the presentation from the very start, but I saw some of the slides. So, sir, we would be very interested to know that because most of your studies are very much related to the baseline information related to like peatland and ocean ecosystem, wetland ecosystem. So as you know that in order to conserve this critical ecosystem, we also need a lot of finance and capital to be invested for the restoration and conservation. So do you also trying to develop such projects under various voluntary or compliance carbon market, which is kind of very important to mobilize climate finance in the sector? Right. Yeah, but I think commercialization is also very important for the conservation of what the scientific, evidence-based research you are doing. I worked a lot on climate finance. That's why I was very keen to understand where does you stand on the climate finance part. I said I work a lot on climate finance, so I would be very keen to know how he is really integrating those aspects in his research studies.
Well, I can answer indeed. We started as a scientific project, mostly based upon physical and chemical consideration, actually. of the fluxes and carbon budget for particular areas, but industries and also even big dogs in our government, they always push us in this direction, as you said, how to start to create actually offsets and how to start to sell them, how to organize the audit of this. What we argue, not against this, but we say that, okay, it's a little bit too early to do this, because to estimate actually the value of any unit and to start to put this unit to distribute it to the market, you need first to know how this unit was generated, and for instance, you know the technology, how to generate the unit on a particular landscape, but first you have to know the background, actually, state of this landscape in the sense of carbon cycle. So what do you earn with such and such technology? And but we are on the way in this, actually, and we have even small working group inside the project which concentrates on this. Thanks to mentioning this, and you particularly, again, I suggest you actually to take this brochure, or the brochures there, actually, which describe the project. Thanks again for the question, and thanks to Alexander for this overview. And indeed, I also would like to thank Ministry of Science and Higher Education and its representative Anton, who is here, and he personally, during these last 3 years, invested quite a lot into development of this project and into the stage of this project, which is going on, which is not stopped. And recently we had a meeting in Sochi just a week ago, and also was a consideration of some climate issues, and I said there that climate is on no return point, so climate cannot get back actually to the previous states, but our project, this Carbon Super Science project, is also no return point in the sense that, okay, it will not be stopped, it will be alive and will develop. Now we switch to, particular super sites, and we start with Voronezh super sites, where Mikhail Dropolyuk will tell us about the restoration of forest ecosystems and the afforestation, and whether it's challenges for climate projects.
Where was this used? Dear colleagues, the area of the forest found in the Russian Federation is 1.1 billion hectares. This is 10 times larger than the area of arable land and included. Forest found 1.1 billion hectares, protection forest 4.9 million hectares, open forest 1.7 million hectares, protection natural area 28 million hectares. Russia's forests continue to decline due to forest fires, clear cutting, damage by insect pests and forest diseases. The imbalance between losses and reproduction of forest resources accumulated over a decade amounted to an unprecedented value of about 5 million hectares. 1.8 million hectares are losses of reforestation, and 4.8 million hectares of lost forest are the result of forest fires and other reasons. To a large extent, climate change exposure is significant in sparsely forested regions of the country, one of which is the Voronezh region. Forest fires in 2010 caused enormous damage to the region forest. The forests managed by Voronezh State University of Forestry and Technologies were also affected by forest fires. From total of 12,000 hectares of our forest, 3,000 hectares were lost in forest fires of 2010. This is significant damage since reforestation in the region is extremely difficult due to climate conditions. In order to restore destroyed forest, Scientists and students have been preparing the soil for planting on 2,000 hectares. To grow seedlings, the university has a modern smart greenhouse and forest nursery. More than 3.5 million seedlings were grown in the greenhouse complex, which were then planted in the burnt areas. Unfortunately, only 30% of the plants were survived, despite the great efforts of our foresters. Therefore, development of innovative technologies and the cultivation of drought-tolerant varieties to maintain the balance of reproduction and forest loss has become a key research priority. In 2021, the university, the government of Voronezh region, and Sibur company signed the agreement to launch a joint reforestation project on the non-reforested burnt areas. The forestation project involves revegetation by planting seedlings, followed by plant maintenance. The project is agreement with the principles of climate projects. The baseline of reforestation climate project depends on the forest zone. The forestation project is implemented by the university in the forest steppe zone on the condition of sharply increased aridity of the territory. The risk of carbon leakage under the project is minimal if the activities are carried out on forest lands transferred for research. Therefore, the period of use of the project area is unlimited. Seedlings of poplar, birch, oak, and pine were used to create the plantation. Generally, 9 different species and varieties of species trees were planted in the forest areas during the project. Sibur actively implements ESG principles in its policy. They acted as investors in reforestation project, investing more than 40 million rubles in the plantation's establishment. Thanks to the company's participation, the project created a carbon test site for testing method to control the carbon balance of forest ecosystem on an area of 158.2 hectares. Forest ecosystem include multi-age poor and mixed stands of oak, pine, and hardwood species. Sibur purchased research equipment for the carbon test site. The total area of forest climate project includes the carbon test site was 2,000 hectares. During two growing seasons, researchers studied productivity and carbon sequestration of tree species like birch, pine, poplar, larch, and oak at an experimental site. Fast-growing species like birch, poplar, and pine promising for reforestation and lower fertility soils, while oaks thrive on more fertile soils. The university has conducted breeding work with poplar ES38, Voronezh gigant, showing strong growth and photosynthetic activity. Sibur volunteers take an active part in plantings at the project area. By the end of 2023, plantings have been created on a total area of 456 hectares. Gentle technologies are used during reforestation, no-till planting of soil, manual planting. This allows to preserve carbon in poor soils in areas damaged by forest fires. For the reforestation project in 2023 alone, university science grew more than 1 million seedlings and planted them on the project area. The success of reforestation on the burnt areas is also related to the care of seedlings. During the summer, agrotechnical care, protection from fires and diseases were carried out. A drip irrigation system was established to increase the survival rate of plants. Reforestation is costly, which investment of 139.9 thousand rubles per hectares. Revenue is based on carbon units in the Russian market. The traditional species for forestation are pine and pine birch, but introducing fast-growing poplar and changing techniques and machinery can shorten the investment payback period to 10.4 years. Reforestation in the forest steppe requires collaboration between science, business, and government. This allows for the development of new technologies by scientists, help business determine emissions levels and avoid environmental taxes, and enables the government to monitor the environment and establish a carbon accounting system. Reforestation projects with 30-year implementation period are attractive investments, contributing to Russia's national objectives of improving environmental landscapes and integrating companies into global carbon accounting. And dear ladies and gentlemen, I would like to address the tomorrow day. We have joined forces with our partners, the high-tech company Sibur and Russian leading scientific research institute in St. Petersburg to create a new knowledge, and we hope that our results and experiments will be demanded by education and business. The agreement will be signed tomorrow with the participation of Mr. Shashkin from the Ministry of Science and Higher Education and Mr. Dmitriev from the Federal Forestry Agency. Thank you very much for your attention.
Thanks, Mikhail. Thank you very much. It's a very interesting presentation. By the way, particularly, this is one of very few super sites where they already have started estimation of economic issues actually, and estimation of the offsets which they can create or will create with activities on reforestation, and particularly also what Mikhail has announced for tomorrow. You can go there and be part of this interesting discussion. Is there any questions with respect to this presentation? No. Okay. Just before I give a floor to Elena Latkovska, who should speak on blue carbon potential. She is from Sakhalin. She will be remote, I guess. Okay. While our assistants start actually the session, I have to say that good news is that the reception is confirmed. I got a call from the office. So this lady said that okay, it is confirmed. So 6:30 here, this side, the reception will be served, as well as afternoon coffee break. These are good news. Now what? Pardon? Can you say it again, please?
I just wanted to remind you that at 5:30 there will be a presentation of the Pleistocene Park, and after that there will be reception. So please come to the presentation first and then enjoy reception.
Yes, of course. The reception will be preceded by the presentation of Pleistocene Park. Here, I guess, here. And Nikita Zimov and his colleagues will do this more extended presentations than it was in his morning talk. And then this presentation will be followed up by the reception, which is sponsored by Andrei Melnichenko Foundation. At least we know now that the money will not gone somehow just okay to some black hole. Well, do we have Elena? She's in line? Okay. So now we switch to talk of Elena Latkovska, blue carbon potential. This is a very interesting project in the Sakhalin and Okhotsk, Sea of Okhotsk and the offshore regions of Sakhalin. And Elena, it's your floor now, your turn. Can't see you on the screen.
I cannot see my presentation, but I already.
We can hear your voice, but we cannot see it. We can see neither you nor your presentation still.
Yes, I already. My presentation already here.
Here, okay, let's go.
Okay. Dear colleagues, my name is Elena Latkovska. I'm from Sakhalin State University in Sakhalin Island, in Russia from East. So around us two seas, Japan and Okhotsk, and we have many opportunities to investigate marine ecosystems and blue carbon production. Is the slide changed? Okay.
Pardon?
Is the slide changed?
Yes.
Okay. The Sakhalin region has a goal of achieving
We have the global map.
neutrality.
Of course.
Yes. Everybody hear me? I hope so. Okay. Sakhalin region has a goal of achieving carbon neutrality by 2025. So we should have understood how the natural features of our region can be used to achieve this goal, and how to make Sakhalin a provider of ecosystem carbon storage services. In 2021, NOAA presented Blue Carbon Inventory Project. The aim of this project is to support the long-term management of coastal blue carbon ecosystems and to assist partner countries in including blue carbon ecosystems in registers as well as in plans to reduce their carbon footprint and adaptation to climate changes. Here is a global map of average annual carbon storage by coastal marine ecosystem from research by Bertram and others, 2021. This map part of the analysis of which countries are donating natural carbon services to planet and which countries are recipients of such services. How can you see the Russian coastal marine ecosystem have a high potential for carbon storage, and Sakhalin region, here it is, a little bit. Sakhalin, the regions too have very high potential for carbon sequestration. The role of algae in absorption of dissolved carbon dioxide is well known, and now we have many global estimates of current carbon storage and long-term forecasts of both natural and artificial seaweed forest. One of them in this slide, a global project called Growing Carbon from Seaweed. This project has international foundation on the Ocean 2050 platform. Here was assess the present and future absorption of carbon dioxide in algae mariculture. It was estimated through scenario of development of mariculture economics in research by Duarte and others in 2022, and with an intensive growth rate of algae mariculture, it's about 20% in a year, and by 2050, more than 200 million tons of CO2 in equivalent can be removed annually, only for seaweed mariculture. This is very big, of course. In accordance with the need to reduce their carbon footprint, many countries with high mariculture level put climate changes mitigation through the development of their mariculture in priorities. We have many interest research from China, India, Indonesia, South Korea, Malaysia, but nothing from Russia, we hope yet. For example, this research by Tang with others show what from 1999 till 2008, seaweed and shellfish monoculture in China absorbed about 40 million tons of carbon and more than 100 tons in CO2 equivalent. Projects to use shellfish for long-term carbon storage are also popular because it is very easy to calculate the accumulation carbon in shell. It's always about 12%, you know, and the metabolic processes with the release of CO2 into the environment during respiration are also well known for common species of mariculture mollusks. In South Korea, CO2 absorption due to the mariculture of main species of algae and shellfish is about 160,000 tons of CO2 equivalent per year. And that is equivalent to 6% of CO2 discharges from all wastewater treatment plants in Korea. It's very big estimate. Next, very interesting Chinese scientists estimate the carbon uptake by bivalves at the all cultivation period since 1981 for whole life period of mariculture of bivalves. So, in present time, shellfish storage in shell more than 1 million tons carbon per year. It's about 4 million tons in CO2 equivalent. It's also very big value of sequestration. So, mariculture offers many opportunities to mitigate and adapt to climate changes. Various modifications of marine carbon farms have been proposed, and most of them including the joint cultivation of seaweed and shellfish. This slide shows one of the model of marine carbon farms from Korean scientists. We named it coastal CO2 removal belt of seaweed. Here, marine farms of seaweed are integrated into natural kelp of brown algae. And the investigation show us the common brown algae Eclonia can draw down till 10 tons of CO2 per hectare in a year. This is just an example for a large-scale multi-trophic farm in northern of China, where algae, shellfish, and fish are grown together. This model of evaluation, or this model of cultivation of organisms with different trophic levels in same time and same volume has shown the best results of in sequestration of CO2, and we hope we can see such pictures in Aniva Bay very soon. So let's consider the potential for carbon sequestration of marine areas in Russian forest. According to calculation by Sergei Maslenikov, the area suitable for intensive mariculture here, without Kamchatka region, is more than 2 million hectares, and the production of brown algae plantation can reach 200 tons in a hectare, of course, annually. Potentially, it is possible to absorb more than 90 million tons of CO2 every year. Is it lot or little? We calculate this value from low production cycle. It's about 85 tons biomass per 1 hectare annually. So, for example, to achieve carbon neutrality of the Sakhalin region, it is necessary to compensate for 3 million tons of CO2. So, of course, we cannot use all potentially suitable areas for mariculture of seaweed, but even we will be use only 10% of suitable areas, it will be about 9 million tons of CO2. So, Russian forest seas can really become a provider of carbon storage services for all planet by seaweed mariculture. So the next point of our intention is volume of carbon storage in shellfish. Carbon storage, so the Sergei Maslenikov also calculate the productivity of growth shellfish and crustacean in forest area for mariculture, and they can potentially storage in shell from adults of bivalves, common species, not all species, only common species like scallop or oyster, reach more than 1 million tons in CO2 equivalent per year. Of course, next. So, this is Sakhalin Island, this is Bay of Aniva, this is our carbon polygon. So why is Aniva Bay? Because it's very shallow, it's very transport convenient. In here we have natural seagrass meadow like Zostera marina, Zostera asiatica. We have natural kelp for brown algae like Saccharina japonica. It's more than 4,000 tons from natural settlement. We have our business partner. They have places for plantation. This is scheme of plantation for the seaweed cultivation. This is a little spatophyte of brown algae, and this is picture of one line with spatophyte of brown algae. So about our results, just a brief. For season 2022-2023, the brown seaweed harvest was not high. Lower grade level was estimated about 85 tons per hectare. It's not so much. Annual volume of CO2 fixation in biomass of the cultivated brown algae is about 20-40 tons from hectare annual. Biochar yield pyrolysis in low temperature or the dry mass of several species of algae, including brown, reached 80%. So, and if all the grown biomass is given to the production of biochar, then the sequestration of carbon dioxide from hectare of the carbon farm in Aniva Bay, we can amount about 15 till 30 tons of CO2. So, the marine mariculture farm with algae and shellfish cultivation is optimal technology for carbon sequestration from environment. Clean, cheap, we cannot use the fresh water, we need not fuel and any ecology damage technology. And the main questions is what to do with biomass if I cannot eat it, and what to do with shells when I ate such tasty mussel. Of course, our scientific technology can give us many interesting ideas. this is just several more popular goods from seaweed and shells from carbon farms. Is not complete list, of course, and the use of cultivate mariculture facility for long-term carbon storage is being updated every year. So thank you for your attention. It's all.
Yeah, thanks, Elena. Very nice presentation. If there are any questions? Well, generally, it's a very promisable, very interesting issue. Can you come up, please?
I'd like to know where to find methodologies to calculate CO2 capturing by aquacultures. I mean, aqua bioresources, water bioresources. Yeah, by aquarium systems.
Irina, there was a question where it's possible to find methodologies to compute actually the effectiveness to some extent of some projects actually based upon aquatic systems. If you can answer, please.
Uptake through the cycle of seaweed or bivalve. We just calculate how many carbon in grown biomass. We know the wet weight, we know the dry weight, we know the content of carbon in shell, in seaweed, and it's very, very easy to calculate. But of course, the baseline, how many CO2 the release in environment during respiration, during microbial degeneration, we cannot, we can, but it's not need for calculate CO2 in grown biomass.
Well, thanks. No, indeed, it's a very good question what you posed. And there was a slide actually, what to do next. For instance, seaweeds, it's a very effective thing, and other mariculture and aquaculture is also might be very effective. But it's important then to calculate end-to-end what to do actually with these seaweeds. And actually, Irina presented several avenues actually for this with biochar, with some other projects. But end-to-end calculation actually, and what we call the carbon actually slice actually in all these technologies, it's never calculated. It's a very very virtual thing indeed, and unless you do this precisely, of course you cannot say whether it's effective thing or not. But we have to move in this direction, actually. But this also relates to not only to marine projects, but also to all other projects, in fact. And yeah, it's okay. I still have some time, actually. We are in this Dubai city, and many years ago, 10 years ago, actually, I had a discussion with. There's a good Dubai Ski here. Have you seen Dubai Ski? No, it's very impressive facilities actually. It's kind of mountain skiing here in the desert. Now it's 2,000 meters slope with a real snow and with just temperature inside being about +1 degree centigrade or -1 degree centigrade, and with alpine villages on the slope, so with all machinery which is necessary. And I argued several times, actually, many years ago, that it's a kind of nonsense, actually, with respect to climate change, because you can just imagine how much energy. This is the largest energy consumer in the world per capita. Per capita, it's the largest energy consumer. But what they say is that now we are very close to be neutral with respect to carbon, for the reason that if you calculate actually the cost and the carbon emissions from the air traffic, if all people living here in this area start to fly to Austria and to Swiss and to do this mountain skiing there, then okay, we will just okay. So you know, it's a very complicated thing. So, but you always have to do this end to end, indeed. Thanks. So our next speaker is Irina Akhmedova from the Northern Russia, from Yugra University, and she will speak about wetlands and the role of wetlands in carbon budget. Irina, you are very welcome indeed. This is extremely interesting talk, and this is one of the best, or probably the best developed carbon super site actually in Russian Federation. Irina will speak in Russian, which is not a problem. And I will provide a translation, not in parallel, but just, okay, sentence by sentence or statement by statement. So you can, вы можете использовать, Ирина, вот этот микрофон, а я буду использовать этот микрофон.
Good afternoon, ladies and gentlemen. I thank you for invitation to participate in this event, and I'd like to tell you about our carbon station Mukhrino, but in Russian.
Давайте, нормально.
Ну, я недолго буду говорить про карбоновый цикл. Все знают о том, что болото – это очень мощный мировой сток.
Говорите.
Сток углерода, который способен накапливать и хранить многие тысячелетия. Углерод в чистом виде.
Okay, it is not necessary to speculate quite a lot for carbon cycles of the wetlands. It's well known that wetlands are very effective accumulators of CO2, and this is a place where carbon sinks.
Тем не менее, от природных климатических факторов зависит в данный момент болото является стоком или эмитентом парниковых газов. Влияет на эмиссию или сток как раз уровень болотных вод, наличие растительности и скорость накопления торфа.
Nevertheless, the situation is not as easy, and it is not necessarily that each wetland is a carbon stock, because there are many biogeochemical and chemical and other processes which engaged actually, and there are many actually feedbacks which make change actually the situation and either increase or decrease actually the effectiveness of wetlands to accumulate carbon from the atmosphere.
Именно эти три составляющие, то есть торф, растительность и уровень болотных вод, являются предметом мониторинга исследователей, которые осуществляют свою работу на болотах.
And these are very issues actually, very specific consequences and very specific processes which are in focus of the researchers who do this job over the wetlands.
Болота являются важным регулятором и оказывают экосистемные услуги человеку в части как раз регулирующих это адаптация к климатическим изменениям.
Also, it's important to mention that wetlands they play an important ecosystem services actually, providing actually, how to say it. I don't know how to say this. Can you say it again? Можете снова сказать, какие услуги они оказывают?
Экосистемные услуги в части адаптации к климатическим
Yes, okay, sorry. And these ecosystem services, okay, they are centered on the adaptation to climate change.
И в отличие от лесных экосистем, болотные экосистемы могут менять свою роль при воздействии на них. То есть лесные экосистемы у нас всегда остаются поглотителем, а болота при нарушении превращаются у нас в источник.
Well, in contrasting to the forest ecosystems, wetlands are interesting in the respect that they may change actually under the impact and under the action of humans. They may change the capabilities with respect to the sequestration of CO2 and other greenhouse gases, because forest ecosystems, they work only as sequesters, and the human influence is just working to either may work in a way to increase this capacity. But for wetlands, it's different. Humans may affect wetlands in a way that the cycle of flux might be changed over the wetland.
Да, на слайде как раз видно, как меняются компоненты болота при воздействии на них.
And this slide exactly shows how the components and how this wetlands may change before and after the impact, the human impact on the wetland.
Ханты-Мансийский автономный округ – уникальный регион, площадь которого покрыта болотами, и она составляет более 30%.
Irina speaks about Khanty-Mansiysk area. We call it Автономный округ actually in Russian. And this is a huge territory in the northern Russia. And you can see here actually a short description of this territory. But importantly is that more than 90%, specifically 92% of this actually of the area in square kilometers of this Yugra is covered with the wetlands, by the wetlands.
В отличие от европейской части, в Ханты-Мансийском автономном округе нет осушенных болот. У нас проблема с болотами, которые нарушены в результате добычи углеводородных ресурсов.
Contrasting to European part of the Russian Federation, wetlands of Ugra, they're not. Саша, ты знаешь, как осушенное болото будет? Anyway, Нет, нарушенное или осушенное?
У нас осушенных нет, а у нас есть нарушенные.
So the sense, I'm very sorry about that. Okay? I'm not expert in the wetland systems, but nevertheless, осушка means
drying it.
Drying, yes, that's what I want to say. Drying, yeah. In European part of Russian Federation, the many wetlands were dried, so the water was removed actually from the wetlands. It becomes no more wetland, in fact. But this is not the case for wetlands and wetlands in Ugra. Yeah.
Да, здесь на слайде как раз очень видно, как влияет нефтедобыча. Это размещение инфраструктуры на болотных массивах, это перекрытие растительного покрова, нарушение водного режима, что приводит как раз к повышенной эмиссии потоков парниковых газов.
Here in this shots you can see how the industrial activity over Ugra, first of all, associated with exploration and actually taking the mineral resources and oil resources, how these activities may change the wetland and peatland ecosystems. And first of all, they're changing water cycle of each peatland.
Поэтому на слайде как раз видно, каким образом может происходить первоначально накопление углерода и, собственно, некое поглощение парниковых газов при воздействии болото у нас превращается в источник. И заново, если мы реставрируем, то есть не вторично заводняем, а реставрируем нарушенное болото, мы снова возвращаем его в состояние, в роль осуществляющего сток болота.
On this slide, you can see how the peatland can evolve in this respect. First, okay, peatland starts to be from a sink as a source of emittent actually of CO2, and then when the human influence is applied, it again goes back as a cycle actually and becomes again actually the sink for CO2.
Все мониторинговые работы осуществляются у нас на карбоновом полигоне Мухрина как раз для того, чтобы изучить динамику состояния верхового естественного болота и, возможно, эти данные использовать для реализации климатических проектов для корпоративных наших партнеров на нарушенных как раз болотах.
Well, the research which is going on in Ugra super site are explicitly focused on the study of all this process, and also they are trying actually to make precise measurements and estimation of peatland capacity with respect to CO2 sequestration, be it plus or minus with respect to the cycle, depends where does it go. And then, okay, with quantitative knowledge which they get, they may come to their investors and to start probably negotiate climate projects associated with peatlands, be they dried or not dried, whatever.
На карбоновом полигоне Мухрина, одном из самых оснащенных карбоновых полигонов Мухрина, по мнению экспертов сегодня в России, осуществляются разнообразные исследования, то есть это и изучение накопления, скорости накопления торфа, это активность почвенной фауны, это измерение потоков парниковых газов методом Anticovariance, камерные методы измерения и также эксперименты с манипуляцией с климатом. И краткая схема полигона на слайде представлена.
We are speaking actually this Mukhrina is a carbon super site in Ugra, and this is one of the best equipped, in fact, super sites among the other carbon super sites, which we have 17 now, and that's indeed, and this is one of the oldest one. They have very nice equipment, and they make probably the most advanced and rich actually program of observations spanning from eddy covariance measurements to different chamber measurements, and also very specific measurements which are listed here, including also the analysis of vegetation, actually the estimation of the pulse of carbon. And indeed, it's despite actually very remote location, actually this is a very advanced, and for many of our super sites, this is I'm saying from myself now, which stands as a prototype of what each super site has to do, be it on peatland or in the forest or in agriculture and so forth.
На карбоновом полигоне сегодня установлено 3 вышки. Высотой здесь на слайдах представлены 10 метров, 7 метров и 40 метров, которые работают по методу Anticovariance, измеряя потоки парниковых газов, то есть водяного пара, углекислого газа и метана.
So there are 3 towers on this carbon super site, 10 meters, 7 meters, and 40 meters. Yeah, each is equipped with Anticovariance equipment, and they measure carbon fluxes, actually CO2 fluxes, directly, because this is the only way actually to directly measure this. And also they get actually profile measurements. So that's it.
Ну, это иллюстрация приборной базы, то есть вот эти еще раз вышки, да, и с оборудованием. Оборудование установлено стандартный американский Light Course.
So every tower is equipped besides the AD coherence with LICOR, LICOR system.
Yes. Это камерный способ измерения потоков.
Here's a chamber approach to measure fluxes is presented actually.
Установлены автоматические метеорологические станции, которые фиксируют разные параметры.
And in each venue, in each site also there is an automatic meteorological station which measures meteorological parameters, and which is very important because you cannot do anything if you don't know meteorology.
Проводятся гидрологические исследования, это 3D-моделирование и измерение уровня болотных вод.
And also besides this, things which are directly focused on carbon and carbon fluxes, there are hydrological program, which includes 3D modeling of hydrological cycle. И что еще делает?
И измерение уровня болотных вод. Уровень болотных вод.
Yes, and also this research is extremely important for measuring the water table in the wetlands.
И на слайде представлены основные результаты. Разница в параметрах существенно может отличаться на гряде и мочежине по нашим исследованиям только в летнее время и утренние часы. Ну, здесь вот примеры обработанных данных.
Yeah, and here's examples of instrumental records obtained for meteorological parameters for the heat balance, actually, or thermal balance, and for CO2 fluxes. And разница, что может делать различие?
Разница между параметрами метеорологическими на микротопах болотных, то есть гряда, мочежина отличаются метеопараметры.
Окей, а где на болотах, на каких топах?
Есть у болот разные, скажем так, микротопы. То есть есть гряда, есть мочежина, то есть болото грядово-мочежинное, верховое. И вот разница параметров отличается. То есть вот эта мозаичность болота, это и проблема болота, потому что нет единых, то есть стабильных данных.
Я понял. Okay, I will try to explain this. It's a question of terms. The scope is that peatlands is very inhomogeneous. Normally they are very inhomogeneous, and there are different patterns in patches which are characterized by different conditions for fluxes. And this slide particularly demonstrates that even in a short distance, but for different patterns of these peatlands which are characterized by different conditions, actually the meteorological conditions and also fluxes may be very different, and the difference may even affect actually the sigen of the flux.
Да, и на слайде здесь представлены как раз потоки углекислого газа на разных микрорельефах болота, на гряде и мочежине. То есть оно неоднородный рельеф имеет, и, соответственно, показатели потоков, они тоже отличаются.
And here it's exactly a demonstration, an example of how on this short distance, but in different, actually, the different particular subregions of this peatlands, actually, the carbon fluxes may change and may vary from each other quite substantially.
Ну и по многолетним данным как раз была попытка рассчитать углеродный баланс болота Мухрина, который вы видите на экране. Да? То есть наше болото Мухрина сегодня по факту это сток. То есть все-таки поглощение порядка на слайде указано 100 грамм.
And all at all, for the whole region of the Mokhrina wetland, there was an attempt to calculate carbon budget, and interestingly, this computation resulted in the conclusions that the Mokhrina wetland is a sink for CO2 now.
Ну и для развития сети в перспективе предполагается, что будет 5 подобных полигонов, возможно, не таких масштабных, но тем не менее правительство округа поддерживает развитие региональной сети мониторинга.
And being based upon the achievements which they got on this first super site in Mokhrina, they are now expanding this network. You can see this on this slide, and the local municipal government is largely supporting actually this activity, and there will be 1, 2, 3, 4, 5 sites, probably not super sites, probably with limited capacity, but nevertheless they will enrich the whole vision of this important ecosystem with respect to carbon budget.
Да, в настоящее время работают 2 станции. В следующем году, летом 2024 года, планируется станция еще одна Салым и 2 проектируемые.
Currently, there are 2 sites of this are working already, and in the next year there will be 1 more added to this operationally, and 2 are planned and currently in the design stage.
Активно помогают индустриальные партнеры. И вот как раз 3-я станция – это компания Salym Petroleum, которая помогает реализовать наш проект.
And the industrial partner кто?
Salym Petroleum.
Кто?
Salym Petroleum.
Salym Petroleum, industrial partner. He contributes quite a lot into the development of this project, and the cooperation between scientists and industry here is very impressive.
Ну и поскольку сеть развивается, нам необходимы специалисты. Для этого в университете реализуются несколько образовательных программ, направленных на подготовку высококвалифицированных кадров для работы на наших станциях, карбоновых полигонах.
And there's many other actually super sites, of course, Polygon, Mokhrina super sites, and on the other super sites actually a lot of educational activities is going on, because a new generation of researchers should somehow appear, and to appear they have to be taught how to do this. And here you see, probably I will not read this presentation of what is going on at this particular super site in Mokhrina. A lot of educational programs on master level and on bachelor level and on PhD level as well. And I hope Yugra University is also facilitating this. Да?
Yes.
Югорский университет.
Yes.
Да, yes.
И в следующем году у нас состоится симпозиум «Западно-сибирские торфяники. Цикл углерода. Прошлое и настоящее». Поэтому всех приглашаем принять участие. И thank you for your attention.
And next year there will be a scientific symposium actually in Mokhrina. It's very challenging to visit this symposium because it's an extremely interesting place. And Irina invites all of you and your colleagues, just distribute this link and be part of this interesting scientific event.
Thank you.
Thank you. Thanks, Irina. Thank you very much. Thanks indeed. Extremely interesting presentation. Well, I'm very sorry I could not properly translate some things because it's not a question of my English, it's a question of my knowledge actually of specific terms associated with wetlands. But nevertheless, okay, I have to learn also something. Well, our next speaker and the last one before the coffee break, which I hope to be served actually, is Nila Orlova from Samara, and she will speak about agricultural ecosystems, which were not discussed yet so far. Which mic do you want to use?
How we can put? And to move left, right? Okay.
Yeah, this is next. You can keep pressing.
First of all, I would like to congratulate everybody with World Soils Day today. Celebrated the world this and I will introduce agriculture carbon supersite. In the world now, a lot of crises, soil degradation, carbon degradation, climate crisis, but they're all together. Every year, world losing 12 million hectares and emitted 30%, up to 30% of greenhouse effect. It's in the world. In Russia, we have also 30% degraded our land, 60 under erosion, and we are losing also 1.5 billion ton of soil, fertilized soil, and they are losing also carbon, 3.6 gigaton from 0 to 1 meter layer. And agriculture, one of the main emitters of greenhouse gases. And emission from the sector take the third place in the term of greenhouse gas emission among in the Russian economy sector. And losses from impact of climate change on Russian agriculture, according to some estimates, could be reach 1 or 2% of GDP per year by 2030. And sustainable development in the world of human depends on agriculture, soil, climate, and determining of the carbon cycle later. And this, I will look here, the foundation of carbon farming is soil health. And the vital activity of microorganisms depends on carbon. Soil carbon is subject with its own socio-economic assessment. According to Professor Ratan Laila, Ohio University, 0.13 kilogram of carbon cost $1. Also CO2 and some soil organic matter. And to save carbon and soil, European Union spends 38 billion, United States of America 44 billion per year, and in the world where they're doing this program 300 billion. In Russia, we have all the data for preserving soil of erosion and degradation. It's from 100,000 ruble per hectare up to 1 million. And because of new policy, we have new also terminology and appeared carbon neutral agriculture, carbon conservation agriculture. It describes a holistic approach to using agriculture practice to reduce or offset agriculture greenhouse emission with storing carbon in the soil. A carbon unit appeared meaning and carbon footprint. And this is carbon footprint is very important in agriculture because it's assess of efficiency of using enterprise resources, the level of production intensification, the adaptability of varieties and hybrids of agriculture crops, ensure environment friendliness and production, climate-oriented production, and have marketing advantages. Carbon market, you know, it was growing, and last 10 years it's growing because agrar carbon market. They are growing in 2021 amount to about 900%. In monetary, 544 million. And many countries are already developing an approach to implement a climate policy, including determining the carbon footprint of agriculture products. And this is very important for Russia because we are still by far from this policy. For agriculture recovery, there must be a fundamental change in the agriculture paradigm aimed at preserving and increasing soil organic carbon. And one of the methods for this, conservation agriculture, and main principle of this conservation agriculture is no-till, no mechanical work, preservation of crop residue on the soil, and diversification of crop system. But also we I understand more wider this technology. It's also a whole complex of precision farming technology and a lot of biological method. And what is this technology is given to the world? First of all, preserve and recover soil organic carbon, decrease greenhouse emission, prevent soil from compaction, erosion, degradation, desertification, achieve soil balance, setting appropriate conditions for the soil microbiota, improve soil productivity yields, improve soil resistance to severe weather condition and climate change, decrease the expense on the equipment. For example, for 3,000 hectares, you can save 3-4 machinery, agricultural machinery. It's a big investment. Particularly last year when price increased tremendously. Decrease also of negative effect of agriculture on the environment and provide for additional revenue for farmers through the mechanism of carbon credit. In the world now, more than 206 million hectares under this technology. And in the beginning, first role played American continent, United States, America, Canada, and then Argentina, Brazil, Paraguay, and Australia. But last 10 years, it has been growing, this market, because of Asia country. China started program in 2020 to save agricultural black soil land, and Europe in 2020 make a soil strategy and also technical management for carbon land use. In Russia, we have 6 million hectares under this technology, and this is different farmers from 1,000 hectares up to 200,000. And technical practice of conservation agriculture are capable of sequestering carbon in the soil according to various sources volumes can reach up to 10 tons per hectare per year at Brian McNay data. And this is different practice what can store carbon in the soil. And if used this practice all together in one field, we can achieve 10.5 tons per year. And this is, for example, one of the farms who are using conservation agriculture, carbon saving technology. And you see it's a little bit different in profitability. If we calculate it by direct cost, we see one figure. But if we take in account compensation of carbon losses, we have quite low figures, little bit low. And Ministry of Science and Higher Education started very good practice, and we heard about many carbons and also agrar carbon polygon. And agrar carbon supersite are set to conduct comprehensive research to study soil carbon storage and greenhouse emission in order to find the most accurate and economical efficient method to calculate soil carbon dynamics, but also second important part to research to study efficient management of carbon cycle and photosynthesis in conservation with biological treatment in conservation agriculture to increase soil fertility, yields, and production quality, and prevent soil from degradation. And this is size of our carbon farm, and this is crops what we are growing with average annual precipitation 365 millimeter. Technology, no-till, biological method. We try to learn to use different maps with to improve our technology. We used all analysis from traditional agrochemical retrospective analysis, but also microbiological, metagenic, and with using hyperspectral imaging on drones based on Offner scheme. And this result of first year, we see different between traditional technology and conservation agriculture technology. And all samples are selected, taken into the account of NDV maps completed on the basis of 6 years of data. And we try to follow IPCC methodology and use mostly FAO MRV protocol. This is why we pay big attention to microbiological analysis, because soil is live organism and there are a lot of microorganisms. So and it's to understand, to carry out research in different field plots and field for different crops, that will allow to find correlation between yield and soil fertility. And also studying soil, plant, and human microbiota will allow to establish a concept of a new microbiological system that can protect and influence each other, and also to make more effective carbon cycle and photosynthesis with biological method. We're using also microchromatograph. We don't have equipment, American equipment, because we just register, and 2 years we did before. It's pre our resort before officially registered project. And it's all equipment we use by, set up by National University of Samara, and this is a characteristic of hyperspectral camera. 700 gram, and spectral range from 400 up to 2000, with channels 250. We did calibrate, was calibrated to measure carbon concentration in the soil in the laboratory condition, and started also on the field. What is interesting, we to achieve safe level of CO2 in the atmosphere from 410 up to 230, we need to sequester 60 ppm, or about 400 million tons of CO2, and 18 million what additional appeared every year. In the world, agriculture has 5 billion hectares worldwide, and if we can assume that in everywhere, on 5 billion hectares, will use this complex technology of resource carbon saving or resource saving technology, and deposit about 10 tons of carbon per year. We can every year we can accumulate 50 billion tons per year, and during 15 years we can achieve 450 million. It's very optimistic figures, and very realistic if we can do this. And in Russia, we calculated 66 million hectares of agricultural land, and our deposition can be 660 million tons of CO2 per year. But also it will help now, according data of Arkansas University, in the world 61 military conflict. And if we stop military conflict, and if in the world, and if we introduce this technology in the whole world, then we can achieve neutral zero balance with carbon. This is our activity. We provide conference, seminar. We participate in international conference. We are member of a Global Soil Partnership, produce magazine doing this platform. And this is our farm. We try to live in harmony with nature and try to do everything to preserve our soil for the current and future generations. Thank you. It's all picture from our farm.
Thanks. Very interesting. If there are any questions, Durina, yes, Sasha.
Actually, I have one only small question about fertilizer. You said about carbon soil sequestration. It's of course it's one point which can be include but everything. But it's not only it's climate effect. It's very small one in this case. But what about fertilizer?
This technology is everybody who uses this technology, they try to use less chemical fertilizer because we leave crops of residue on the field, and this also common fertilizer. And we now calculate how much from which crops and from which crop rotation. This is very important to calculate also. And many farmers already try to reduce from chemical fertilizer at all. This is a big policy in the world. Because chemical fertilizer, but we are not extremists. I'm not extremist. I understand that we should not refuse from chemical straight away. We have to use integrated technology with chemical fertilizer, but less, and organic, yeah. And chemicals, fertilizer, Ministry of Agriculture, they promote chemical fertilizer because it's a big company, they have very big lobby, but it's, first of all, it's very costly. Now all farmers thinking about this, how much they could use. And we have, on our farm, we see our yield is growing. Every year we have better yield, and quality also. But to achieve this level, it's necessary, of course, help of scientists, investigation. But it's on the way. We are using much more less chemicals fertilizer than before.
Well, thank you. If there are no more questions, just a short announcement. So we need, you have a question, right? Yes, of course. Use that mic, please.
As you know, many companies use land and then provide recultivation, and I mean biological part of recultivation. Might these projects be included into projects of your organization? Especially in case if it's not belong to the land of agriculture.
I did not understand cultivation. Depends of cultivation. We have in agriculture most important technology. It's no-till, no cultivation, no plowing, nothing. But we have also minimum till, where they use cultivation. It's of course not this effect. It's much more less, but it's possible to calculate. In Russia, about 15 million under cultivation because plowing is very expensive. And we save, I said, for 3,000 hectares, you can save 3-4 machinery. It's a lot of money. And for Russia, it's probably 300 million. We could save investment. And fertilizer, 50% less. And now price of fertilizer, diesel fuel. And the price for diesel increased very much. It's very economical. And less people, less operation. Minimum till it's possible. They exist, but it's not the topic.
Well, you can continue actually to communicate during the coffee break. I have just few announcements. Okay, thanks. Have just few announcements before we start. The coffee break is served, which is good news, as I said. After the coffee break, probably we will start not 3:50, but 4, because we are okay with time, actually. Then after the coffee break, there will be we will switch back to general climate issues from this specific area of carbon supersites. We'll have Alexander Shirov and then Igor Bashmakov, who should be online, on different aspects of climate economy. And then after this, we will have a presentation by Elena Shmilova. Elena is a chair of Sirius Federal Territory, and she is also head of university in Sirius. And make a note in your program that her talk the topic of her talk, the title of her talk will be changed. And it stands now as Engaging Young People for Effective Climate Action, Ecological and Technological Tourism Problem, interesting. Why not? To speak about this. And then when it's done, after this 3 short time slots, 15, she requested 30. Okay, probably it will be shorter. We will have time for general discussion. Depends on how many people we have here. Actually, we will decide actually on the format of this discussion. It can be panel. It can be just coming to mic from the floor. We will see actually how many people do we have, and then after that, exactly 5:30. We'll have a presentation of Playstads and Park for 1 hour, actually for 1 hour to probably 1 hour 20 minutes. It will be here, and Nikita Zimov and also the chair, the head of Yakutsk area, Arsen Nikolaev, will be here, and then the representative of Andrei Melnichenko Foundation, the senior executive officer Ilya Chipulin will be also part of this, which is also very nice to see. And then this presentation of Playstads and Park will be followed up by the reception organized here and will be served here afterwards. And this will be a very nice reception. It's by courtesy of Andrei Melnichenko Foundation. It's paid by them. So you are all welcome. And now you can enjoy your coffee, which is served there, contrasting lunch, which was missed. And then, okay, we will start. Okay, let's put 15 to 20 minutes actually for now. Thank you. Mike? Oh, okay, it works. Thank you. Well, I invite everyone to take your seats on the floor, please. We are turning now to our last time slot. And as I said, we start with two presentations on climate economy, which will be followed by a presentation by Elena Shmylova on some engagement of young scientists into climate and ecological activities, or the tourism. So the title is changed. And then we will have a general discussion. So I'm very happy that the number of our attenders is growing up. So probably we will indeed have a reasonably productive discussion, I would say. And then presentation of the Pleistocene Park, followed by the reception. Let me invite you, Alexander Sherov. And Alexander is the director of Institute of Economic Forecasting, and he will speak on the development of the system for monitoring and forecasting of greenhouse gases emissions for advancing Russian economy. Which mic do you want to use? This or this? Alexander, какой микрофон тебе лучше?
Thank you so much. Dear colleagues, I'm very glad to be here in COP28, and I will present our view on the macroeconomic estimation in the field of climate policy, together with my colleague Andrei Kolpakov. And of course, today we looked at the different picture of estimation, scientific work in the field of climate in Russia. And of course, economy is not the typical science, because we work with economy, with social process, and of course our economic estimation is one of the main reason of this estimation is more and more goal our economic policy in the field of climate changes. First of all, about our methodological. In this slide, you can see the main ideology of our calculation. You can see in the center of this scheme, you can see macroeconomic, social economic impacts of climate policy. And of course, we have two types of income. The first one, the positive. First of all, it's structural changes in our economy, additional investment activity, and so on. But we have negative impacts. The negative impacts, first of all, it's a result of very expensive decision in the field of decarbonization. And these very expensive decisions go to the very high prices for energy. And of course, this balance between negative and positive impacts is a result of our estimation from this or that scenarios of decarbonization for Russian economy. If you look at the side of mitigation, we use for our estimation dynamic input-output models, different scenario of social economic policy and climate policy. Of course, the result of our estimation is GDP, output prices, employment, and so on. Of course, the next result of our calculation is dynamics of greenhouse emissions. And of course, we estimate the efficiency of different decarbonization measures. And in final, we have a result in terms of economic dynamics, GDP output, and so on, for different scenarios, socio-economic development, and different scenarios of policy of decarbonization. Here you can see our current scenarios in terms of greenhouse gases emissions in period till 2050. You can see three main scenarios. The first one, based as usual, without additional measure of decarbonization. You can see in this scenario the average annual growth rates is about 2.7%, and investment in decarbonization, zero. It's not reality. It's a problem with the screen. Okay, yeah. And finally, total greenhouse gases emissions increase in the whole period. Of course, it's not real scenario, but it's baseline scenario for different variants of policy. The second scenario is scenario with measures of decarbonization. In this case, you can see 1% of GDP, the total investment in decarbonization, and average growth rates is about 2.6. But unfortunately, you can see that in 2050 we have the level of greenhouse gases emissions more than 2030. It's a result that without help of LULUCF, our ecosystems, and other forests and so on, without this factor we cannot have decrease of greenhouse gas emissions. And the third scenario is a scenario with additional measures. In this case, we have average growth rates less than in first and the second scenario, but only 0.2 percentage points, 2.5% growth rates of GDP, average growth rates of GDP in period 2030-2050. We have investment in decarbonization about 1.7%, and including impact of our systems is about 0.12%. In this case, in 2050, we have greenhouse gas emissions and the level about 500 million ton of CO2 equivalent. The second point of our estimation and modeling is adaptation. Of course, adaptation is more difficult than mitigation for modeling, because in case of adaptation, we have not one, but two ways of different impacts. The first one is impact of investment in adaptation, and the second one is impact of damage to output and from climate change, because we have more and more investment in adaptation from climate change. We decrease of possible damage in the climate. If we have not so much investment in adaptation as it's necessary, we have additional damage, and we have losses in terms of economic growth. In this scheme, you can see our current version in the model of adaptation. We have in the core of this scheme current level of and the future level of investment in adaptation by sectors, by factors, and finally we have in the right side the impact from investment in adaptation, and the left side we have impact from damages in economy. From example, in this slide you can see the current estimation of potential damage to fixed access from permafrost degradation until 2050. And you can see the highest result for mining. It's about 250 billion ruble in the price 2016 in constant prices. And for example, for transportation, about 50 billion Russian rubles, and for another sectors you can see these estimations. In this slide you can see impact of investment in adaptation in different estimation investment in adaptation and potential damage. In case if investment adaptation and potential damage about 5%, you can see that cumulative output in Russian economy will be in 2023, 2040, 50 about 7 trillion US Russian rubles, and in case 100%, the result is about less for maybe less, and finally in this figure the level 75% and level 100% is are not effective for Russian economy. So thank you very much.
Thanks so much, Alexander. Is there questions? I have a question. Actually, the economy of any country, I'm sorry, from this point I will speak as just an ordinary person actually, not a scientist, because my understanding is that the economy of any country depends on many things actually. And of course it depends on climate. Of course it depends on climate. But, how to say this? There are economies which are more dependent on climate. There are economies which are less dependent on climate. If there was an attempt actually in your community, in your institution, and any other institutions, just to classify economies, for instance, developing economies, and even in the domain of developing economies, there might be also different economies. If there is any kind of classification of these economies actually, which say encapsulates those which are largely dependent or very much dependent on climate, which are independent on climate at all, or dependent to a lesser extent, it's kind of what I would see probably in the ideal answer is a map colored by different colors, and to see economy of which country is more dependent on climate, and on which time scales, of course.
No, of course, Russia is a big country, and a big country such Russia, United States, and Brazil, very dependent on climate changes because not only structure of our economy, but our territory is a factor of our dependence from climate, because in our estimation, in our models, we think that climate and adaptation is more important factor than mitigation for Russian economy.
Thank you. My premonition was quite an opposite. In fact, that I saw that a small country, for instance, if you consider a small country, and this country lives from catching some fish actually, and this fish depends hugely actually on the upwelling activity and in fact on the temperature of the water in the offshore zone. So the economy of this country is fully dependent on climate. And for big countries, okay, there are somehow flexibility and too many options actually to survive. Moreover, big countries, they have so many problems, like my country, and our country, in fact. And so that it's probably, always my concern was that climate is not the first and the second, probably even not the third problem of my country. Anyway, thanks so much. Do we have Igor Bashmakov online? So I will ask my colleagues. У нас Башмаков-то есть? No? Нету? Okay, Igor Bashmakov did not connect. It's another missing talk. Very unfortunate, by the way, because Igor is always very creative. Yes. So if we take a break for 2 minutes and invite Elena Shmelyova actually for her presentation, this will be quite in time. Yeah, it's a pity that Igor couldn't connect because he is, for many years, coordinating leader for Working Group 3 in IPCC, and he is really very experienced actually in the assessment of what climate means for economy and how to adopt or mitigate actually the climate changes. So, with respect to the time, we have 4 4:24 now, so let's assume that we start Elina's talk in 4:25. Yeah, so we are quite okay actually. We are very comfortable with the time schedule. I'm thinking about our discussion, which will follow up talk of Elina. Assuming that we will have a flow like now, who wants to? Can you hand up? Who wants to bring a point during the discussion? Speakers want to say something? Alex? No, I wanted just to hand up, just to estimate the number of people who want to be part of the discussion. Very good. Anton? Okay, me probably. Sasha, yes, right. 3 of us. You, very good. This very nice lady in black who posed as many as 3 questions. Now speaking to her colleague. I'm speaking about you. I'm sorry. Hi. No. It's come. You asked many questions, actually. Do you want to be a part of the discussion? You want to say something? Why not? Yeah, in 30 minutes. Okay. Irina Fitzgerald. Great. Very nice last name. Irina Fitzgerald will also be part of our discussion because she asked several questions. And no? Okay. Very good to see you, Елена Владимировна. Пожалуйста. Я вам дам микрофон. Well, I have 2 mics actually. There are 2 mics here. So probably Elena will use her, this mic. I will pass it to her and you can use this mic. Okay, very good. So now, where is my phone actually? I have to read this. As I said, the title of a presentation by Elina Shmylova has changed. And now it stands as Engaging Young People for Effective Climate Action, double point, Ecological and Technological Tourism Program. Elina is representing Sirius Federal Territory and the Sirius University, Research University actually, in the very south part of Russia actually. This is Russian subtropics, which is also challenging, interesting. I give you floor now, Elina.
Да, Сергей Константинович, большое вам спасибо.
Mr. Sergey, thank you very much.
Спасибо за представление. И я очень рада, что у каждого из вас сегодня была возможность содержательно представить те исследования, которые сегодня ведутся в России по разным направлениям и в разных регионах. И мы сегодня хотели поставить вопрос о том, есть ли у нас инструменты, чтобы вовлечь в них молодежь, и каким образом, потому что для нас всех это будет принципиально важно, для того, чтобы исследования расширялись, развивались, и чтобы полевые исследования выполнялись не только нами, но и молодыми людьми, которых это заинтересует.
All right. Thank you very much for everyone coming here today, and thank you very much for your studies. And basically, I understand that we want to work on the future generation. We, as a Sirius, wants to emphasize on working on the future generation for new human resources. And on the basis of the research which we have done, we would like to share a few information to you.
Ну и, соответственно, именно здесь я хотела бы обсудить и проинформировать про тот проект, эколого-биологического проекта, который Сириус сейчас запускает со своими возможностями абсолютно равно во всех регионах для того, чтобы была возможность с этими исследованиями познакомить и детей, и педагогов, и молодежь.
And here also I would like to add that Sirius itself is working on the ecological program, which is going to share with the younger generation. So, I mean, the program will be worked in different regions of Russia. So definitely the resources will be well equipped with it.
Соответственно, у нашей программы будет 3 обязательных компонента. Первое – это посещение молодым человеком или школьником компании нашего индустриального партнера. Второе – это прохождение эколого-туристического маршрута региона. И третье – это участие в научном исследовании, связанном с климатом и экологией.
So definitely there will be 3 points which the person participating will be going through. First part will be the ecological route. Second part will be the research part, and the third part will be
Третий элемент – это участие в исследовательской работе.
Taking part in the scientific research centers.
Таким образом, мы считаем, что задания от индустриальных партнеров, которые в том числе представлены здесь, будут разными, а экологи-биологический блок, он будет единым для всей программы.
So I understand the task given by the partners or the key players will be different, which are mentioned. I mean, the partners or the key players which are mentioned over here, but the target will be one.
Соответственно, старт и заявка на программу будет содержать некую аналитическую работу в ответ на задачу партнера и выбор до этого эко-маршрута и региона, соответственно.
So definitely the initial part will be, I mean, the research or the work done on the task given by the partner and the route set out of it.
Поэтому все уникальные объекты сегодня, национальные парки, заповедники, они все находятся внутри этой программы, они являются ее партнерами, и таким образом вот желание оказаться там и быть полезным для развития вот этого уникального объекта, наверное, будет основным. Ну и плюс отраслевая привязка молодого человека к той компании, которая тоже за это отвечает.
So definitely all the natural reserves, basically the reservoirs will be the part of this research. And the person who will be taking part in it will definitely be equipped with the well-informed knowledge of certain sectors.
Соответственно, да, вот эту заявку оценивает наставник, открываются после подтверждения результата рассмотрения этой заявки образовательные материалы, и по приезду этот молодой человек, оказывается, у этого наставника на 3-4-5 дней вместе с ним работает.
So the work result has been will be handed over to the partners, and they will be analyzing the work, and on the basis of the analysis, the student or the selective person will be given under a special to a special observatory person who will be working with him for the next 3 to 5 days.
Таким образом, мы считаем, что очень большой охват будет молодых людей по вовлечению вот в такую научно-исследовательскую работу именно по адаптации региона к климатическим изменениям или обсуждению и участию в мероприятиях, которые могут улучшить экологическое состояние наших природных объектов.
So we understand that working in such a way will, of course, improve the understanding of the younger generation in or the person who's the kid who's working in this task it will improve his ecological understanding of that certain region and of course to analyze what can be done for the future.
Ну, я уверена, что мы увидим очень интересные результаты, которые мы могли бы приглашать на нашу ежегодную конференцию ежегодную и давать обратную связь. То есть таким образом мы все время видим заинтересованных людей с обратной связью от наставников и от научных руководителей.
So of course, I can see that there's quite a bit interest in the I mean, I can see it over here. So if there is somebody or some organization willing to work with us in the scientific research sector, they are welcome to join us or give some idea or maybe direct us in the right direction.
Ну и вот я как раз хотела бы попросить и предложить подумать о научно-методической поддержке вот этой программы со стороны сегодняшних ведущихся исследований, научных руководителей и коллективов.
And of course, from the scientific side, I would like some kind of maybe a direction or the more proper way would say advice from the old-timers or the organizations which have been playing a long-time role in this sector.
И, конечно, я уверена, что таким образом собранные, обработанные результаты, их можно будет использовать и в той работе по государственным исследовательским программам, которая сейчас ведется. В случае, когда вот как сейчас мы обсуждаем совместно тематику, направления и приоритеты.
So I'm sure that the work done and the research done and the analysis outcome of that research can be used in certain events like today's event or any kind of platform where we can use this knowledge for the development of the sector basically.
Ну и мне кажется, что очень важным элементом поддержки молодых ученых является вот знакомство их с инфраструктурой, которая создается в разных регионах, в том числе в рамках карбоновых полигонов.
So for me, it's more important that the younger generation should be introduced with different kinds of construction or building sites which are taking place in the field of carbon footprint.
И я уверена, что вот такой подход, такая программа может стать значимым инструментом популяризации исследований, полученных и в рамках ВИП-ГЗ, в рамках ФНТП и в рамках программы Министерства науки по карбоновым полигонам, потому что таким образом как бы содержательные результаты школьники могут представлять на своих школьных конференциях, и это тоже первый шаг в науку.
So I'm sure these kind of programs can be well approved by the government sectors or the Ministry of Information Technology and Science and Technology. So definitely these projects can be, even the kids, they can represent these projects in the universities or in the institutions to introduce other children with it.
Мы примерно об этом говорили и в России, и вообще об этом говорим все 8 лет работы Сириуса, о таких инструментах, которые нам доступны. Но во время работы здесь стал очевиден еще один важная задача для нас всех. Мы должны, мне кажется, готовить ребят, которые потом станут значимыми помощниками в вот таком международном переговорном процессе, потому что они будут знать хорошо матчасть, и они будут сами от первого лица рассказывать, как ведутся и верифицируются исследования.
So one more thing which we have been working on it, but not in such highly focused on it, but currently in this summit I've noticed it, that we need to manufacture or produce good negotiators, good human resources, which can, of course, take part in certain events and can share their experience and can learn from these events as well.
Ну, конечно, очевидно, это начать такую подготовку с аспирантами, с молодыми учеными, с магистрантами. Ну, а школьники просто должны осознавать, что это очень важно, и что мы тратим много сил и времени для того, чтобы эти научные исследования выполнялись максимально обширно по всей территории России, и мы бы формировали вот подходы к климатическому образованию и просвещению таким образом.
So, of course, we understand that students studying in masters or doctorate or, of course, the higher qualification, it will be good for them, not neglecting the children who are studying in the school sector, I mean like basic schooling or undergraduation, so that they can, implement or they can apply these kind of, this old information in the daily life or in the regional part.
Да, спасибо большое. Ну вот это, наверное, общие контуры программы. И сейчас я, конечно, хотела бы очень, как сказать, предложить и принять участие и в обсуждении, и в дальнейшем в запуске вот этой программы. Но у нас есть действительно признанные ученые и эксперты, и те, кто такие программы сам делал. То есть люди, которые как бы считают, что это их миссия, развивать такие университеты. И вот Сергей Константинович развивал такой плавучий университет, собирал и собирает студентов со всей России и из всех как бы смежных областей. Сергей Константинович, что мы должны сделать, насколько опыт плавучих университетов здесь мы можем применить?
So I thank you all for being
Спасибо.
here. Пожалуйста.
Ну-ка, in which language should I continue now? Как говорить-то, по-русски, по-английски?
Как вам удобно? Как вам
Мне все равно. Okay, well, first it's a little bit not exactly true that I was a kind of founder of Floating University. My institution, indeed, my institution was a founder of Floating University, and I contributed very little, actually, to Floating University. Вы будете на русский переводить? Или давайте я буду говорить по-русски, а вы говорите по... Хорошо, да, это не совсем правда, что я был, значит, каким-то застрельщиком плавучего университета. Скорее, мой институт океанологии имени Шершова, да, действительно, мы начали такую программу плавучего университета, и много ученых из моего института вовлечены в, так сказать, в организацию работы плавучего университета, и это делается при поддержке Министерства науки и высшего образования, и там есть на самом деле большие успехи, потому что из студентов и аспирантов, молодых ученых, которые прошли через плавучий университет, пусть немного, но очень таких хороших потом появилось специалистов. Хотя, конечно, огромный захват людей там начинается с нескольких тысяч иногда аппликаций, и потом эти аппликации, значит, так сказать, там уменьшаются, но все равно, как бы, так сказать, эти жемчужины, они рано или поздно проявляются. Хотя, конечно, многие просто... Я не считаю, что это, кстати, бессмысленно, что многие просто знакомятся с морской наукой, с экологией моря, с физикой моря, с тем, как работать в море, попадают в итоге на последнем этапе этого дела, значит, попадают в экспедиции морские, где тоже работают. И, конечно, это полезно. Кто-то может покритиковать, и я сам даже, так сказать, таковым являлся, кто критиковал. Например, у нас много аппликаций от просто студентов-журналистов, которые хотят стать, которые надеются рано или, значит, взять ее, и поплавать, значит, на научно-исследовательском судне. Многим журналистам, так как их просто очень много аппликается, это в итоге удается, и, навряд ли журналист, поплавав приняв участие, да, в научной экспедиции, там, решит бросить журналистику и заняться, там, не знаю, исследованиями Атлантики или там Баренцева моря или еще какого-то моря, навряд ли. Но, тем не менее, значит, приходится нести этот груз, но зато эти журналисты, наверное, потом смогут писать или рассказывать своим слушателям, своим там читателям той медиа, где они работают, с лучшим пониманием, с лучшим таким профессиональным или полупрофессиональным хотя бы знанием того, о чем они пишут, потому что ведь если вы газеты, журналы там и передачи, особенно интернет почитаете, то вы увидите, что там такое пишут, что никакой правды, значит, к истинному положению вещей это не относится. Но в этом смысле, кстати, климатическая наука и мы в климатической науке действительно очень сильно зависим от... мы не зависим, как ученые, от медиа, но медиа, безусловно, оказывает влияние на степень достоверности, с которой наши знания, так сказать, воспринимаются публикой, потому что публика не читает научные журналы, публика не посещает там научные конференции, я имею в виду широкая публика, а публика узнает о науке из, так сказать, медиа. Поэтому как бы, если медиа начинает работать профессионально, то это становится полезно для ученых, потому что иначе, так сказать, результаты этих ученых, медиа часто перевираются до такой степени, что потом, как-то я отступил от общего, да. Но одним словом, плавучий университет – дело нужное, полезное. Я должен здесь поблагодарить Министерство науки и высшего образования, которое спонсирует это дело. Это очень серьезно. Вот. И, безусловно, вовлечение Сириуса и вовлечение инициативы, о которой Елена Владимировна говорила, в программу такого плавучего университета будет крайне полезно, и в той степени, до которой мы можем, мы обязательно это поддержим. Там, может быть, в меньшей степени, и я готов поддерживать, но у нас просто есть люди, которые систематически, профессионально этим занимаются, совместно с физико-техническим институтом, с нашей базовой кафедрой, там, совместно с Московским университетом и с нашим институтом. Это я вам абсолютно обещаю. Единственное, что хочу сказать, что плавучий университет, это там есть слово плавучий, да, он завершается этим floating, да, по-английски, floating university. Чтобы, значит, было floating, это должно быть судно, и на этом судне, ship has to sail, да, судно должно плыть. К сожалению, на Черном море у нас с этим, некоторые проблемы. Некоторые проблемы, потому что у нас есть, два очень небольших судна, не в очень хорошем состоянии, там для какой-то науки, которую, значит, такие энтузиасты развивают. Не энтузиасты, а куда им деться ученым? Это, нормально. А для того, чтобы там еще организовать образовательный процесс, это не очень нормально. Поэтому может быть, давайте совместно поработаем над тем, чтобы такое научное судно среднего размера, среднего, так сказать, среднего тоннажа, как мы, моряки, говорим, у нас появилось, и мы бы его, допустим, совместно использовали для образовательной деятельности, и для научной деятельности, потому что она... И потом мне очень понравилось, Елена Владимировна, что вы сказали о школьниках. Действительно, это всегда большая проблема, как привлекать школьников, потому что, понимаете, с одной стороны, школа – это то место, где начинается базовое образование ребенка. И когда вы учите детей этим, кстати, образовательные программы школьные, особенно на уровне secondary school и high school, в России отличаются от некоторых западных аналогов, в худшую, кстати сказать, сторону, что базовое образование в области математики, физики, географии, философии, филологии, литературы русского языка, как это по-школьному называется, оно достаточно хорошее, достаточно сильное. А такого междисциплинарного образования, какого-то такого понимания проблем мира, в том числе и проблем климата, а это, безусловно, проблема мира, как-то нету у нас такого. И поэтому вовлечение школьников в такую программу, это будет крайне полезно. Если вы сейчас отправитесь в любую страну европейскую, я не говорю, что там как-то пример даю, что обязательно поезжайте и спросите. Нет, но если вы спросите там школьника про то, как меняется климат, почему он меняется и так далее, вы получите вполне такие, простые, но вполне понятные и достаточно обоснованные ответы. Если вы спросите, я внука одного спрашиваю иногда, ничего не знает, географию знает, при этом неплохо, физику, может, знает неплохо, химию знает неплохо. Казалось бы, а эту проблему, допустим, не знает. Заставить его знать. И я думаю, что тоже вы делаете, особенно в таких блоковых курсах, тоже, наверное, на это будет работать. Но я занял очень много времени, я очень благодарен, что вы к нам пришли и все это рассказали, и мы надеемся с вами как-то посотрудничать. И я так понимаю, что Антон Павлович сейчас хочет что-то сказать.
Да, конечно, карбоновые полигоны, они могут и должны, в общем-то, использоваться как один из, в общем-то, элементов такого научно-популярного туризма. Тем более, что на ряде полигонов есть инфраструктура. А инфраструктура – это, в общем-то, ключевая вещь, которая должна быть, если мы говорим о туризме. Там, неважно, там, для школьников там, или для взрослых. Я приведу такой пример. Мы, допустим, на полигоне в Чечне что сделали? Мы собрали региональных операторов, привезли их непосредственно на карбоновый полигон, и теперь их туристические маршруты проходят через площадку карбонового полигона, где им, туристам рассказывают о работе, в целом о климате, просвещают. Но что там важно? Там есть два ключевых элемента. Первый ключевой элемент – это инфраструктура. Это, в общем, там в нескольких километрах от такого потрясающего бирюзового озера горного Кизиной-Ам. Там же, в общем-то, гостиничный комплекс, все это обустроено. И плюс к этому там рядом историческое место – это город мертвых, город Хой, на который тоже, в общем-то, все с удовольствием приходят и смотрят. Поэтому важно, в общем-то, найти вот эти вот такие исторические моменты, которые можно вместе с этим, в общем-то, рассказывать, и инфраструктурные. Есть еще один пример, когда мы уже, не выходя там на региональных туристических операторов, самостоятельно собрали научно-популярный маршрут в Екатеринбурге, под Екатеринбургом, который тоже проходит через территорию карбонового полигона. Там это идет несколько сложнее. Это я показываю как раз противовес, потому что там недостаточно как раз-таки исторического акцента и инфраструктуры. Он проходит через обсерваторию, поскольку полигон он захватывает часть обсерватории, которая под Екатеринбургом, но туристический поток там идет гораздо слабее. Третий вариант под Калугой на карбоновом полигоне Калужской области. Я надеюсь, в следующем году запустим такой полигон. Он будет больше такого рекреационного характера, то есть соединение с природой, что называется, да. Там есть площадки для глэмпинга, как сейчас модно там обустраивать. И в следующем году мы это сделаем. Но опять же там есть исторический акцент. Это стояние на Угре, где можно, в общем-то, это все показывать и рассказывать. Поэтому вопросы климата важно показывать не сублимированно все-таки, когда мы говорим о туризме. Надо захватывать и другие моменты. Еще один момент, который бы я предложил, у нас есть такой опыт. Мы в прошлом году делали научную экспедицию, но с молодежью. Помните, Сергей Константинович, мы на Камчатке проводили такую экспедицию. И такие экспедиции, они не только научные, естественно, они, в общем-то, и носят туристический характер, тем более, что мы там собрали молодежь не только из России, а и из-за рубежа. И мы им показали и, естественно, национальные парки Камчатки, и вместе с ним проводили научные исследования в морской акватории, бухта Саранная, где они, в общем, подбирали участок для будущего карбонового морского полигона. На следующий год, в этом, то есть году уже, мы проводили аналогичную экспедицию вместе с Русским географическим обществом по территории Самарской, Волгоградской и других областей, где они изучали вопросы опустынивания, тоже непосредственно связанные с изменением климата. Эта экспедиция была достаточно масштабной, многодневной, она делилась на два этапа. Первая часть была в апреле, вторая уже в сентябре, когда не так жарко. Поэтому я думаю, что вот такие экспедиции, в которые можно вовлекать и школьников, и студентов, и молодых ученых, тоже нужны. Их у нас в стране, на мой взгляд, недостаточно. Но за счет такого охвата, за счет, вернее, привлечения молодежи, они могут быть более содержательны, в том числе с позиции изучения нашей территории, нашей страны.
Спасибо большое, Антон Павлович. Сергей Константинович, коллеги, может быть, есть какие-то еще?
Да, я специально не стал говорить о карбоновых полигонах, отбирать хлеб у Антона Павловича, хотя тоже вовлечен в эту программу и проблему. Наш буклет вы на английском можете, там взять, а на самом деле он и на русском существует, с сайта можно сгрузить. Мы и сюда не привезли русские, вариант. Но я знаю, что Сириус, заинтересован в создании своего карбонового полигона. У нас есть ваша заявка, и мы ее, конечно, рассмотрим. Там будут какие-то коррекции, но Это, безусловно, очень интересно, потому что это столь же интересно, наверное, как и наш карбоновый полигон, который в Геленджике. У вас там есть заповедник, тоже интересное место. Так что я думаю, что и в этом направлении мы тоже можем посотрудничать.
Спасибо, коллеги. У нас есть...
Да, и, кстати говоря, по поводу Сириуса и карбонового полигона, ну, у вас, в принципе, уникальная там точка, да? Там столько всего можно смотреть. И буквально там 2 недели назад, когда был Конгресс молодых ученых, мы же проводили наш международный совет карбоновых полигонов, и приезжали иностранцы. Мы их специально повезли по олимпийским объектам Красной Поляны, и они, конечно, вернулись в полном восторге. Если мы захватим чуть больше территории, которую можно, в общем-то, из позиции климата показывать, ну, это будет просто супер, это можно будет как, в принципе, стартовую площадку всех полигонов, в общем-то, использовать, особенно для иностранцев.
Вы знаете, вот это вообще все переосмысление, то есть олимпийское наследие, которое теперь переделывается в кампус мирового уровня, углеродонейтральный, и мы делаем карбоновые полигоны, которые объединяют школьников, которые дежурят по планете в Сириусе все время, понимаете? Это вот, я понимаю, там, ну, не все в зале там помнят как бы советское время, когда вся страна строила ракету. А почему нет? Ну, вся страна дежурит по планете. И в этом плане, конечно, через практику намного легче рассказывать, вовлекать, удерживать, потому что задача удерживать тоже кадровая проблема, как никого не минует, и даже Росгидромет она не может миновать. И мы понимаем, что будет конкуренция за интерес, потому что мы предлагаем ребенку на 7, 8, 9 лет вперед определить свое будущее профессиональное. Это не просто. Коллеги, ну все, наверное, панель у нас закончила. Пожалуйста.
Спасибо. Заметила, что тут коллеги делятся опытом, да, о научных исследованиях и вовлечении молодежи в эти научные исследования, поэтому позвольте тоже немного поделиться. Я представляю компанию «Норникель», и мы в последние 2 года как раз в сотрудничестве с Сибирским отделением Российской академии наук проводим исследования биоразнообразия. Это не карбоновые полигоны, но тем не менее. После 1-го года, когда мы проводили общественные слушания, на них присутствовали студенты, пришли узнать, да, что происходит в 3 регионах. Это была Мурманская область, это был Таймыр и Забайкальский край. Также пришли волонтеры, и они попросили вовлечь их в эти исследования. Мы это сделали. В текущем году, когда мы проводили эти же исследования, также руководитель работ стороны СУРАН привлек и студентов, и взрослых волонтеров, которые хотели, ну, к сожалению, для школьников было рановато уходить так далеко в поля. И не могу не отметить положительный эффект. Во-первых, да, это было наставничество, это было сотрудничество. Всем очень понравилось, ну а кроме того, для компании тоже там, и для самой работы толк. Почему? Потому что трудозатраты уменьшаются, и есть возможность сделать гораздо больше исследований, когда есть много помощников. Ну, вот как-то так.
Можно еще?
Мне дайте микрофон. У нас есть полчаса обсуждать любые проблемы, любые вещи, которые мы обсуждали вот сейчас и которые мы обсуждали в течение всего дня. У меня вот только вопрос. Sorry, okay with the translation? Вы что? Chada, it's Chada. Oh, okay. Can you hand up who actually who is not okay with Russian? We have headsets. It's not a problem actually to supply headsets actually. We have 40, as many as 40 headsets. Okay, so okay, let's continue in Russian. Давайте.
Для того, чтобы представить результаты исследований в удобоваримом для непосвященной публике виде, мы разработали специальный сайт, в котором рассказываем про то, как проводились исследования, какие проводились исследования, какие проекты мы делали для сохранения биоразнообразия и результаты, то есть что мы нашли, какие животные, какие растения там обитают. То есть мы хотели, чтобы этот сайт был интересен взрослым, чтобы рассказывать детям, потому что там красивые картинки. Ну и в последующем собираемся его дополнять. Да. Вот. А кроме того, еще и особо охраняемые природные территории мы тоже вовлекли в этом году вместе с их волонтерами. Поэтому заходите на live.nornickel.ru. Думаю, это будет хорошая идея, как представить популярно эту тему.
Спасибо. Значит, поднимайте руки, кто хочет что-то сказать. И давайте ограничивать время выступления, 2-3 минутами.
Да. Елена Владимировна, очень интересная идея. Хотел бы ее немножко дополнить тем, что опереться можно на школьные лесничества. Они уже созданы и функционируют. И Воронежский государственный леснический университет, я являюсь ректором этого университета, разрабатывал как раз методики по преподаванию для школьников начального класса, средней школы и выше. И поэтому можно доработать эти модули, включая туда климатическую повестку, и эта уже система распространена по всей территории Российской Федерации. Опираясь на нее, можно, конечно, ребят, которые уже заинтересованы, мотивированы уже там, дополнить это. И мы, конечно, говорим о том, что когда говорим о профориентационной работе в области лесных дел, то как раз говорим, что будет спасать мир таким образом через климатическую повестку. Это очень важно. Поэтому принимается и можете на нас рассчитывать в этом направлении. Спасибо.
Хорошо, спасибо. Я сразу говорю, вот это микрофон, который профессиональный, это Stage Micro. И его надо вот так вот, как певцы, знаете, вот они прям вот его заглатывают, близко к рту держать, тогда вас будет хорошо слышно.
Спасибо. Елена Владимировна, я здесь представляю аграрный карбоновый полигон, это первый в России, это очень важно для сохранения почв. Надо таких полигонов создать больше, и на них площадки для детей. Мы, кстати, такой проект подавали вместе с Николаем Дмитриевичем в Сириус. Очень хотелось бы, чтобы вы его реализовали в жизнь. И еще мы в этом году запустили национальный конкурс «Почва. Жизнь» для школьников и студентов. И мы предлагаем, вот, чтобы Сириус вошел. Это Институт Докучаева почвы, музей Докучаева, Ассоциация почвоведов, Российское экологическое общество и Национальное движение сберегающего земледелия. Мы тогда обратимся к вам, если вы поддержите, это будет очень здорово. Спасибо.
Спасибо. Кто еще? Так, сначала вы, потом вы.
Спасибо большое, Ирина Гайда, Сколтех. Как вопрос для обсуждения или комментарий, предложения, безусловно, мне кажется важным интегрировать образовательные программы в области климатологии и природных экосистем. Но вот вопрос, а не надо ли также посмотреть в сторону новых технологий для создания зеленой экономики? Тем более, что задел и в Сириусе, и в Сколтехе уже есть, и очень серьезный. И это могут быть области, связанные как с применением искусственного интеллекта для всех этапов, так и новые материалы, так и новые энергетические системы.
Спасибо, да. Ну и ректор ваш Саша, он крайне заинтересован в этом, насколько я знаю.
Добрый день, Ирина Ахмедова, Югорский государственный университет, карбоновый полигон Мухрина. Мы тоже понимаем, что нужны специалисты и работать нужно начинать с детьми. Поэтому в прошлом году мы провели онлайн-олимпиаду для бакалавров, в том числе приглашали принять участие старшеклассников «Старт Карбон». Мы охватили 35 регионов, у нас было 90 участников. В принципе, обкатали программу, она получилась неплохой. Плюс разработаны модули тоже для школьников разных возрастов. Создаем инфраструктуру для школьников, потому что у нас сложная логистика на полигон, но мы понимаем, насколько важны прикладные исследования, да, и что-то сделанное своими руками под как раз наставниками, да, наставничеством. Поэтому тоже готовы включиться. и даже в методологическом плане поучаствовать и поделиться тоже опытом. И с коллегами готовы сотрудничать, и в том числе, вот вы говорили про технологические проекты, у нас была идея создать что-то типа акселератора и сделать именно проекты технологичные в области решений там, климатических, адаптационных и прочих вещей. То есть не просто мониторить климат, а именно вот некие такие школьные стартапы. Спасибо.
Спасибо, да. Елена Владимировна с ее энтузиазмом, мотивацией и авторитетом поломала всю повестку нашей дискуссии. Да. Я к чему? Что, в принципе, не обязательно дискутировать только проблемы того, как вовлечь молодежь в научную деятельность в области климата или около климата. Пожалуйста, можно и это рассказывать, но можно комментировать и все остальное, что мы обсуждали сегодня, а мы много чего обсуждали. Я вот воспользуюсь привилегией ведущего и скажу, что вот Саша сидит здесь, тоже не даст соврать. На самом деле, очень важная проблема. Вот я просто такой совет бы мог дать. На самом деле вы, может, и не знаете об этом, потому что это такая рутинно идущая уже лет 40, наверное, даже больше, 45 лет, и очень профессионально сделанная программа. Это школа, трехлетняя школа для школьников 7, 8, 9, там, ну, 8, 9, 10, сейчас там не знаю, как 11 классов на геофаке. Она называется «Школа юного географа», где преподаватели геофака систематически каждую неделю собирают школьников, которых также отобрали, и которые просто читают им лекции, проводят занятия, там есть программы и летних практик, и вот оттуда получаются потом лучшие студенты геофака на самом деле. Вообще говоря, ну, всегда эту штуку рассматривали как такую расширенную подготовительную программу к поступлению. Ты не кончал, Саш? Я кончал. Вот. К поступлению на географический факультет или на родственные факультеты Московского университета. Но то, насколько это здорово сделано и здорово работает, а главное, что это работает уже 40, там, 50 лет еще. Вот. Ну вот я был там школьником, это 70-е годы, а я уже в этом участвовал. Вот, поэтому просто свяжитесь, я смогу связать с деканом, вы его наверняка знаете, который тоже окончил эту школу, вместе со мной учился. Вот, и это хорошая вещь, и там многое можно перенять. Хорошо, извините, что я это захватил. Кто еще что-то хочет сказать? Давайте еще раз.
Раз уж было дано разрешение комментировать другие темы, кроме взаимодействия с молодым поколением, мне кажется, я, безусловно, не имела возможности послушать все утренние лекции, но мне кажется, вот было бы интересно, и, может быть, уже у присутствующих есть ответ на этот вопрос, а каков в относительном выражении потенциал дополнительных сокращений углерода от природных экосистем России, какая степень уверенности относительно возможности получения этого потенциала?
Спасибо. Я вот попрошу Александра ответить.
Можно немножко больше сразу скажу? Вот прозвучало слово вот углерод. Вот все вот почему-то вот к углероду все связывают. В общем-то, мы говорим про климатически активные вещества и газы. Потому что углерод, в общем-то, в разную функцию. Кстати, вот недавно на Европейский университет организовывал мероприятие, конференцию, и там как раз тот же самый алмазную пыль пытались использовать в качестве как охлаждающего элемента для атмосферы. Алмазная пыль – это тоже тот же углерод. Если прекрасный, например, эта алмазная пыль посыпется на мне кому-нибудь на голову, особенно если много карат будет, ну, в общем-то, наверное, это можно рассматривать тоже какую-то как осаждение, секвестрацию. Но это все-таки мы говорим немножко шире. Здесь, мне кажется, надо говорить более... Да. Я вот поэтому в этом контексте, наверное, вот ответил бы, что здесь надо брать очень более широко эту тему. И рассматривать действительно, если мы говорим уж про климате, в общем-то, потому что многие современные проекты, которые климатическими называются, они, в общем-то, далеко совсем уже не климатические. Это бизнес, это экономика, это лесное и так далее. Вот кто-то мне сегодня даже говорил, что это 90%, по-моему, это уже не климатические проекты, а это бизнес-проекты. А климат как-то вот стоит где-то там в сторонке и вот тихо хлопает глазками и смотрит, что же там со мной сделали. Поэтому вот мне тут кажется важным вот именно вот не забывать про то, чем мы все-таки занимаемся, не сводить наши проблемы вот именно к решению тех задач, которые, вот, например, нам интересны вот в настоящий момент. Потому что та же самая зеленая энергетика, она, в общем-то, далеко не зеленая, к сожалению. Даже те же самые ветряные двигатели, которые, в общем-то, считаются зелеными, они являются очень-очень с большими последствиями для климата.
Спасибо, Саша. Я абсолютно согласен с тобой, потому что многие проекты, они даже не всегда индустриальные проекты, они часто такие инновационные есть. Есть просто такие вот именно бизнес-проекты. Они часто пытаются представить себя как такие зеленые проекты или там zero carbon, как это говорят. Вот я на утренней сессии упоминал, сейчас могу, коль скоро время у нас есть, повторить за 1 минуту по-русски. Вот здесь вы находитесь, в этом городе, если у кого есть время, то можете съездить, есть такой Дубай-ски. Вот в этой пустыне, вот при 39 градусах летом и 30 зимой, тут есть горнолыжный склон, 2000-метровый, он был там 1000, потом. Я вот с ними общался лет 10 назад. Вот, там вот такой огромный купол сделан, там температура 0 градусов, там -1, там альпийские деревушки стоят по склону. Вот. Это самый большой потребитель энергии, вот, energy consumer per capita in the world, вот самый большой. Но они утверждали, что они вот стремятся к zero carbon, причем, вот я говорю, как посчитать? Они утверждали это следующим, что, говорит, а вот если вы посчитаете всех, кто живет вот в этих всех окраинах, вот вокруг пустынных странах, сколько они потратят на air-трафик, летая, кататься на этих лыжах там, в Швейцарию или куда-то там в Солт-Лейк-Сити или, значит, в Австрию, вот тогда, говорит, мы фактически, значит, много чего поглотили. Но хотя это мне казалось всегда безумием, вот держать, значит, не с искусным, а с они научились производить натуральный снег, значит, вот здесь, вот в этой пустыне. Вот, абсолютно, значит, экологическое и даже человеческое безумие, но тем не менее это существует и приносит большие деньги на самом деле, потому что действительно дешевле покататься здесь за большие деньги, чем лететь в Австрию, тем более там бизнес-классом. Вот, так что правильно, как посчитать? Это вот очень важный момент, как посчитать. Вы опять хотите сказать что-то? Ну, давайте.
Уже не про проекты компании. Я хочу сказать, что исходя из того, что климат формирует не парниковые газы, а климат формируется как раз-таки природой, и в частности той природой, которая еще не преобразована человеком, исходя из этой точки зрения, любой проект, связанный с восстановлением естественной природной среды, будет считаться климатическим. И если экономика готова поддерживать все, что имеет в себе слово carbon, climate и так далее, то почему бы не называть климатическими любые проекты по восстановлению, естественному восстановлению природной среды и, в частности, применению экотехнологий. Единственное, чего нам не хватает, это методической базы. По сути, а финансовая сторона и регуляторная уже развиваются вовсю.
Спасибо, я полностью соглашусь со второй частью вашего выступления, но не соглашусь с первой, потому что изменение климата, климат формируется, естественными экосистемами, но изменения климата, те, которые мы наблюдаем на коротком масштабе, формируются в том числе и в значительной степени за счет деятельности человека. Ну, видимо, вы это имели в виду, просто как-то так вот получилось. Хорошо, кто еще что-то хочет сказать? Экономисты, может быть, что-то хотят сказать. Ну, я хотел навязать дискуссию Андрею про зависимость успешности краткосрочных прогнозов погоды как задачи на начальное значение, вот в решении задачи Каши фактически, от изменения климата. Но, наверное, мы это опустим, потому что у нас как-то аудитория немножко не там, мы с тобой можем где-то в другом месте на эту тему поговорить. Но это интересно. Если хочешь, скажи что-нибудь.
Я бы призывал не забывать математику при вот всех этих разговорах про экологию, там, про карбоновые полигоны и так далее, потому что все-таки инструмент у нас моделирования, он такой один из основных. Поэтому какая-то там должна присутствовать составляющая И такая тоже. Нет, я общество призываю не забывать математику.
Так, кто еще хочет что-то сказать, чем-то поделиться? Александр? Да, давайте.
Нет, ну, коллеги, я просто хочу сказать, что климат – это уникальная история, которая позволяет нам, в общем, по-другому взглянуть на научную жизнь, в том смысле, что обычно мы смотрим, ну, у нас есть некоторое туннельное зрение, да, экономисты занимаются экономикой, океанологи – океаном и морями. Ну, нет, не только, на самом деле, физика, там, математика. Вот. Но, в общем, работаем мы изолированно, честно говоря, чаще всего. А здесь это уникальное место, где, в общем, каждому из нас находится свое применение. И, в общем, вот этот вот опыт общения, значит, с коллегами из разных научных областей здесь, он, в общем, на самом деле, очень серьезно двигает вперед не только наше понимание того, как устроен мир, но, я бы сказал, институциональное управление всей научной деятельностью в нашей стране. И образовательной в том числе, да, потому что вот мы на примере Сириуса видим, что, значит, образование сюда подтягивается. И, в общем, это такой пилотный проект, который, как я уже вот тут говорил несколько раз, нужно тиражировать, безусловно. Мы вот этим тиражированием можем добиться серьезных продвижений не только в области климата, но и многих других направлений научной деятельности. А это будет уже иметь прямой экономический эффект. Спасибо.
Ну да, спасибо, Александр. Действительно, мультидисциплинарность очень важна. Вот примерно 25 лет назад, точно в 1999 году, Ханс фон Шторх, известный немецкий климатолог, он написал в МАМСе, это Bulletin of American Meteorological Society, такую статью, это Climate Science as an example, as a canonical example of post-normal science. То есть вот тогда он впервые произнес эти слова, что климатическая наука становится фактически постнормальной наукой. Не в плохом, а именно в хорошем смысле. И вот все эти последние 25 лет мы наблюдаем, как действительно климатическая наука движется в сторону вот, постнормальности. Вот в английской коннотации это звучит гораздо более, ну, в этом нет ничего отрицательного, когда она начинает консолидировать вокруг себя, так сказать, интересантов из других областей наук, социальных, там, полусоциальных, экономических и так далее и тому подобное. И вот в этом смысле, конечно, нам нужны такие вот места, где люди бы могли, и места, и форматы, где люди бы могли говорить друг с другом из разных областей. Но вот опять я начинаю узурпировать. Кто еще хочет что-то сказать? Никто не хочет. Ну, давайте смелее, что уж так вот. Хорошо, Елена Владимировна, все, хорошо, увидимся. Ну, хорошо. Елена Владимировна нас покинула, может быть, это вас немножко, так сказать, рассвободит ваши мысли и языки. Давайте.
Да, еще раз Ирина Ахмедова, Егорский университет. Я хотела бы сказать, что нужно работать не только с детьми и междисциплинарно, но еще и работать с людьми, принимающими решения, вот с органами исполнительной власти, например. Да, и у нас какая ситуация возникает? Иногда чиновники более высокого уровня, они более просвещенные в вопросах климата и его, чем, например, муниципальные чиновники. Да? То есть и они очень слабо связывают изменение климата с их реальными текущими задачами, например. Да? Допустим, ветхое аварийное жилье, допустим, там, дороги и прочее, прочее. Поэтому нужно работать, мне кажется, и в этом направлении тоже. Спасибо.
Спасибо, хорошо. Есть еще комментарии? Александр, я повторяю свой вопрос, просто там все было в суете. Но вот действительно, нету возможности, вот я про экономику спрашиваю, нету ли возможности нарисовать вот такую вот карту стран, а может быть и территории России, которые вот количественно больше или меньше зависит от экономики которых per capita зависит от климата, от климатических изменений. Потому что я вот как-то мне, как обывателю в этом смысле слова, ну вот мне не очень верится, что что климат является главной проблемой для таких стран, как там Россия, Китай даже, Соединенные Штаты. Ну потому что у них очень много своих проблем, и у них вот экономика как-то она по-другому вот живет. Вот мне казалось, это маленькие какие-то должны зависеть.
Ну да, я же там сказал, что крупные страны, на мой взгляд, от климата страдать будут больше. И per capita тоже на самом деле. В том смысле, что, значит, ну вот сейчас в Министерстве экономического развития вроде бы есть такое понимание, что фокус климатической политики в России, да, должен постепенно смещаться на адаптацию, с митигации на адаптацию. Потому что с митигацией, ну как вы нам много раз показывали и доказывали, значит, безусловно, мы можем, конечно, бороться с выбросами, но вот это вот потепление и на 1,5, и может быть даже больше градусов, оно неизбежно как наступление коммунизма, да, как говорили в советские годы. А раз так, то значит негативные климатические явления все равно будут нарастать. У нас большая страна. В этой большой стране есть мерзлота, огромные территории, которые ей подвержены. Есть зона опустынивания, есть зоны, в которых, значит, большое количество пожаров. И это требует и будет требовать все больше и больше ресурсов. А проблема еще и в том, что эти ресурсы, значит, если по митигации у нас в основном отраслевой принцип, да, мы по видам деятельности действуем, там, энергетика, ЖКХ, транспорт и так далее, то вот как раз на адаптацию у нас в основном ресурсы региональные, а таких ресурсов у нас недостаточно, механизмов нет. И вот тут как раз у нас могут быть проблемы. И, кстати говоря, это не проблема, еще раз, России. На мой взгляд, и Соединенные Штаты, и Бразилия, которую я называл, это вот те страны, которые в этом смысле должны очень активно выстраивать экономическую политику. А мы ее сейчас вот глобально пока не понимаем, как выстроить, крупные страны. Да? И вот эта вот гонка за снижением выбросов, в том числе в рамках глобальной климатической повестки, она за собой заслонила вот эту проблему, которая в ближайшие годы довольно серьезно по всем будет, как бы, так сказать, негативно влиять на этих страны. И да, и правильно вы пример приводили, что возьмем какую-нибудь маленькую страну, которую там будут затапливать, или где там будут какие-нибудь, значит, проблемы с рыболовством и так далее. Да, конечно. Но если мы возьмем, опять же, глобальную историю, то наибольший ущерб, наибольшие проблемы и наибольшие требования к изменению экономической политики возникают как раз именно в крупных странах. А крупные страны к этому не готовы, потому что они занимаются сейчас другим пока. Вот в этом проблема.
Ну да, правильно, потому что ведь маленькие страны, вот, например, такие, так, там не выговоришь, вот они очень, на самом деле, обвиняют большие страны, что вы главные эмитенты, с одной стороны, а с другой стороны, мы-то страдаем больше всех. Если у тебя есть вот страна, в ней живет там 180 тысяч человек, а самая высокая точка этой страны 24 сантиметра над уровнем моря, вот то, что я говорил в своем докладе, то, да, пожалуйста.
Да, Сергей Константинович, я добавлю вот, Александра Александровича выступление по поводу адаптации. Попробую на ваш вопрос так коротко ответить. На самом деле такие исследования, безусловно, есть. То, что вы спрашиваете. Есть глобальные модели FUND, DICE, RISE. То есть там задачи эти решаются. Решаются они, понятное дело, на уровне крупных регионов, а не стран. Но тем не менее решаются. И там тоже множество факторов рассматривается. Там, подъем уровня воды, инфекционные заболевания, там, стоимость жизни, то есть масса всего. Поэтому нарисовать это можно. Но, например, в этих моделях нет деградации многолетней мерзлоты, что для нас актуально. И вообще это довольно сложная тема. Вот, допустим, у нас в России это такой серьезный топик. У нас, значит, есть проблемы. Большая территория покрыта вечной мерзлотой, извиняюсь, многолетней мерзлотой. Тает. Вот. Получается, что мы очень подвержены. Но тут же сразу возникает следующий тезис. А мы подвержены ровно настолько, насколько субъекты, которые ведут там деятельность, безразлично относятся к этой проблеме. И есть примеры конкретных компаний, которые, вообще-то говоря, строят свою инфраструктуру с очень большим запасом прочности. То есть они смотрят климатические сценарии на десятилетия вперед, множат вот эти риски там, на x сколько-то и строят свою инфраструктуру так, чтобы точно их проблема многолетней мерзлоты, ее таяние, не волновала. Поэтому все очень сложно. Всегда все складывается из множества отдельных кейсов.
Спасибо. Ну, давайте коротко.
Безусловно, просто как небольшой комментарий по поводу приоритета адаптации и митигации. Понятно, что моделировать убытки от траектории глобального потепления достаточно сложно и большой разбег оценок. И это неизбежно, в том числе потому, что социальные системы тем и отличаются от инженерных, что читают прогнозы и, глядишь, таки начинают действовать как-то иначе. Вместе с тем, давайте все-таки не забывать, что цель там 1,5 или 2 градуса определена, исходя из как раз точки наименьших совокупных расходов на адаптацию и митигацию. И что в ситуации, когда мы идем по траектории, отличающихся от 2 градусов, мы по совокупным расходам адаптации и митигации, вообще говоря, попадаем в менее комфортную зону, в существенно менее комфортную зону. Безусловно, при этом проблематика того, что, ну, условно, вредят одни, а ущерб от митигации вполне вероятно наступит, ну, как бы не только там, где вредят, вот, эта проблема не решена. И, на мой взгляд, один из ключевых моментов, почему она не решена, связан с тем, что мы пока считаем вклад в антропогенные выбросы преимущественно по произведенным выбросам. А считать нужно, на мой взгляд, по потребленным и, возможно, с поправкой на удельное потребление.
Понятно, спасибо. Но что у нас, в общем-то, дело идет к концу. Я вот, может быть, попросил бы Антона сказать не только о полигонах, но и в целом о проблеме климатических и экологических исследований вот с точки зрения того, как ну, правительство, фактически правительственные структуры, министерство ответственное это видит. Ну и на этом, наверное, завершим. Антон Павлович, пожалуйста.
Конечно, там, дело не в карбоновых полигонах, а дело в том, ну, как мне видится, да, там, как одной из частей там, всех этих правительственных структур, которые есть. А дело в том, чтобы... Еще ближе, вот так, да? А дело в том, чтобы наши измерения, наши предположения, они были достоверные, чтобы они, в общем-то, воспринимались всеми объективно и так, как они представляются. Поэтому важно не только там строить эти полигоны или еще какие-то станции мониторинга, заниматься детьми. Самое важное, на мой взгляд, это, в общем-то, добиться того, чтобы наши измерения были, ну, что называется, там, необходимыми и достаточными, там, как в математике говорят. Для этого нужно оборудование, для этого нужны специалисты, методики. И тогда, в общем-то, проблемы климата, они окажутся более близкими к каким-то предположениям или к каким-то мифическим размышлениям о том, что есть ли там изменение климата или нет его. Поэтому я думаю, это первое. А второе, в продолжении это обеспечение достоверности измерений, это, собственно, как вот правильно было отмечено, что мы сейчас замыкаемся сами в себе во всех этих вопросах. Нам нужно как можно больше развивать международную повестку наших измерений, то, чего, в общем-то, у нас сейчас, к сожалению, пока недостаточно.
Ну, спасибо большое, Антон. Действительно, мы понимаем, насколько важно для нас, для ученых и для людей, которые с учеными работают, для преподавателей вузов, насколько важно, что Министерство науки и высшего образования, так сказать, вот последние, по крайней мере, там 5, больше лет, наверное, вот удивительным образом почувствовала, так сказать, важность исследования, ну, не только климата, на самом деле, природы и так далее. И те инвестиции, которые оно осуществляет, это вещь, ну, на самом деле, незаменимая для ученых. Росгидромет ничего не хочет сказать, насколько я понимаю, вот Татьяна и утром не захотела нас поприветствовать, и сейчас, наверное, не захочет, да, вот мотает головой. Ну тогда что же, я хочу всех поблагодарить за, по-моему, очень интересный день мы провели. Мы его еще не закончили. Я объявляю сейчас перерыв порядка там 5, 7, 8 вот так вот минут. чтобы дать возможность людям подготовиться к презентации плейстоценового парка. Никуда не уходите, это будет очень интересно. И там очень интересные люди будут, и очень интересная презентация. После чего я должен быть уверен теперь, значит, после этого кофе, что нам ресепшн накроют. Это еще один, значит, мотив никуда не расходиться. Все, спасибо большое. Спасибо большое всем.
О, получилось. Здравствуйте, дорогие коллеги. Hello, everybody. We have to start our final part of this day. That was a long day. So let's go for work, and then there will be some reception. Вот это вот сейчас уберем. Убрать посуду. Хорошо, я всех буду звать. Да. Я всех буду звать. Да. Так, Никита здесь. Все. Так. Я буду говорить по-русски. Мы все будем говорить по-русски. И у нас есть переводчики. Если кому-то нужен перевод, то берите, пожалуйста, наушники. Кто-нибудь не говорит по-русски? Поднимите, кто не говорит по-русски, руку. Please raise your hands who don't speak Russian. Okay, you can get the equipment for the translation. Thank you very much. Thank you. Все. Хорошо.
Нет, нет, что? Ну что? Извиняюсь. Ну что, начинаем? Но опять же, я повторяю вопрос. Вот я вижу, вы надели headset. Есть у нас желающие, чтобы это продолжалось по-английски, или мы будем продолжать? Я извиняюсь. Или мы по-русски будем работать, как мы работали последние полчаса. По-русски. Все-таки по-английски хотите? Ну, давайте проголосуем. Какие проблемы? Ну вот, идет синхронный перевод. У нас есть хедсеты. Их достаточное количество. Уж точно их окажется достаточно для людей, которые не понимают русский. Вот я вижу, по крайней мере, 2 коллег, которые уже ими воспользовались. Вот. Так что давайте по-русски. Хорошо. Хорошо, мы начинаем заключительную часть нашего, извините, Дня науки. Частично об этом Никита сказал в начале сегодня в своем докладе. Это проект, который называется «Плейстоценовый парк», который создан в Якутии усилиями, в общем-то, таких вот, как это лучше назвать, как? Энтузиастов, да, вот хорошее русское слово, энтузиасты, вот, и которые инвестировали вот этот свой энтузиазм, вот так можно сказать, профессиональный энтузиазм, в создание, ну, в общем, вот такого проекта, который может нам продемонстрировать один из аспектов влияния на ландшафты, может быть, не самого дешевого, но, тем не менее, достаточно многообещающего. У нас здесь, значит, есть гости, да? У нас есть Айсен Николаев, его нету, да, вот, значит, invited, но absent, да, который возглавляет Якутию. У нас есть Никита Зимов, собственно, главный мотор этого проекта. Илья Типулин здесь есть, да, значит, есть, ну, я вот веду это событие, и Игорь Акмеров, который возглавляет вот некоторую финансовую компанию, значит, Да, очень хорошо. Ну, в каком порядке, Никита, давайте? Ну, наверное, вы начнете, да? Вы начнете, обо всем расскажете, потом как-то кратко поименованные коллеги выступят, а потом будут, наверное, вопросы. Хорошо?
Is this one working? Excuse me. Yeah, do you hear me? I will have to wait until they open my presentation. Excuse me, can you open the presentation? Okay, we'll start that. I will ask to excuse me that I will probably try to speak English in international conference, and I think that's the right way to do it. And it's maybe a bit hard to follow my speech by the simultaneous translation. All right. Is it the right one? Let me see. One sec. Right? Oh, yeah. Okay, thanks for inviting here and giving the opportunity to talk. That's a great kind of honor. So I will start. I came here from the very remote Arctic Research Station, which is located in the high Siberian Arctic in the northeast of Russia. And I will be talking about our experiment, one of the main experiment of our research station, which is called Pleistocene Park. The experiment was started back in 1980s. The first experiment started and was founded by my father, Sergei Zimov. And since that time, we have developed quite a lot, both scientifically and practically. So we'll start with some background. Just 15,000 years ago, the world's largest ecosystem was the ecosystem called Mama Steppe. It was spanning from France to Canada and from Arctic islands to China. And unfortunately, when Ice Age ended, very quickly this ecosystem vanished and left no present-day analogs. And many scientists assumed that this ecosystem was like a polar desert. And this was done mostly on intuitive level. Okay, if in the Ice Age, right now these places are very low productive, and back in the Ice Age it must have been even colder and drier, so probably there was no way to have many animals at that time. And my statement that, it's sometimes intuition is not the best way to do science, because out there, you see there with this dark orange territories, territories where the soils of this ecosystem persisted in the permafrost. And this place is called Duvany Yar. That's permafrost exposure located 120 kilometers up the river from us. And here you can visibly see how the sediments look like. So back in the time, there was sedimentation. And when this ecosystem was existing, they were forming soils. And soils were continuously burrowing. And so these sediments are pretty much showing the kind of remains of this ecosystem. And first of all, want to note that these sediments also contains lots of ice. That's why it's actually quite dangerous in terms of degradation, because these sediments are usually a subject of so-called abrupt thaw, when decomposition is very rapid. First thing, as I said, this ecosystem was forming soils, and these soils were burrowing. First of all, these soils contain lots of organic carbon. So you see there is this fine little roots of grasses, and those roots of grasses were feeding mammals back in the time, and they still persist in the permafrost. And the volume of this carbon is actually enormous. So just now, a small state of Yakutia, there is more carbon in the permafrost than in all above ground vegetation of the planet. So it's a huge reservoir. Moreover, there is also lots of nitrogen in this permafrost, and the soils are very fertile. So you will be surprised to know that this is actually an open-cast gold mine. So the gold miners excavated sediments looking for gold, and already next year the sediments got overgrown by this very fertile grasslands. Approximately half of this permafrost already been reprocessed over the course of the last 10,000 years by so-called thermokarst lakes. And because of the lots of ice in the sediments, sometimes on the flat surface, if permafrost starts to degrade, it's forming those little ponds which are expanding and migrating. And the issue that underneath these lakes, there is lots of methane getting produced, which is quite a noticeable portion of the global methane flux. And when in the winter, this, you see those methane bubbles which are getting trapped by ice. And if you come a bit later in the winter, there is possible, let me see if I can play that. Sorry. Can someone help play this video? No, not. No. Ой-ой. Excuse me.
Я готов.
So yeah, you see what it means that it's methane is very dangerous greenhouse gas. So yeah, first takeaway: permafrost contains lots of carbon and it's going to be trouble in the future because of the ability of carbon debt and this, emissions of greenhouse gases. Okay, apart from having lots of carbon there is also lots of remains of animals which used to live in this ecosystem. And these remains can actually give us insight of how this ecosystem was functioning in the past. So this is once again this permafrost exposure, the 1 year up the river. And here, back in the time, there was no rocks, no trees, so all the solid particles which are in this ecosystem are bones of animals. And the river is eroding these shores and washing away all the silt. And the only kind of heavy particles which are not getting washed away are bones of animals. So all of them project at the shore. And if you walk along the shore, you can actually find lots of bones. And by lots of bones, I mean this. This collection, we gathered walking about 3.5 kilometers along the shoreline and just picking up everything we could find. We put all the bones of animals according to their position and skeletons of different animals. So what we had mostly mammoths, bison, horse, and reindeer, and smaller amounts of wolves, lions, muskox, and woolly rhinoceros. They're not presented here. Okay, the very first thing which we noticed as we walked along this shore, that the bones of horses and bison and reindeer we were finding just randomly, and we couldn't see any patterns. But with mammoths, it was a different story. You walk for, let's say, for about 100 meters. You don't see even a single mammoth bone. And then you encounter, one bone, another one. And you see that there is like accumulation of maybe 5, 10, 15 bones at the same time in one, relatively small radius. Then you walk another 50 meters with no bones, and then another accumulation. And in such matter, we walked this 3 kilometers, and we saw 29 accumulations, and we never saw like just a single bone. And in every accumulation, the size of the bones, the quality of the preservation was indicating they could belong to one animal. And from that, we actually concluded that we basically found 29 dead mammoths in the shore. And then very simple math come in hand. We know the area of the shore which we scanned. We know how long it took these sediments to accumulate from radiocarbon dating. And this already gives us the number of, let's say, dead skeletons per square meter. Per square kilometer in this landscape. And then we also, by separate studies, know the average lifetime of mammoths. So mammoth tusks, same as trees, have rings on them. So if you cut the mammoth tusk, you know at what age the mammoth died. And there is, commercial collections of ivory, of mammoth ivory. And they were studying that and figured out that on average, mammoths died at the age of 50. So that's what we accepted, that average. So if they died at the age of 50, it means that for every mammoth which died this year, 50 others are roaming right now. So from that, we actually estimated that on average, we have 1 mammoth per square kilometer. And that's in the North Siberian kind of plains over the duration on average over the 30,000 year period. So 1 mammoth. But was the mammoth the dominant species in this ecosystem? That's a question. And actually this collection gave us the answer to that as well. We found a very good dependency between the size of the bone and the probability of this bone to preserve in permafrost. So what I mean, take a look at the bison skeleton. You see we have enormous amounts of legs, probably enough for like, I don't know, seven full bison or even more. At the same time, the ribs, we have, let's say, for 1/4 of a skeleton at most. And the reason for that, ribs are thin, and it's very, the chance that they will preserve until they are buried in the permafrost are extremely low. So predators eat them, they're getting weathered, and bones, like a solid, big, like a junk, and it just have much higher chance to preserve. And following this kind of logic, we found kind of connections between the bones of different animals, and we estimated that there is relative kind of abundance of species in this ecosystem was like that. So for every mammoth which roams, there is 5 bison, 8 horses, and 15 reindeer. And this is about 10-ton biomass. And that's kind of huge biomass of animals. And we see that kind of it was extremely productive ecosystem, which was limited pretty much mostly by precipitation. So that's the thing that was limiting this ecosystem. And right now, there is no wild ecosystems which can be as productive as this one. And only kind of in Africa you can see densities higher than that in the wild nature. And the question which people often ask, okay, like right now there is like barely anyone in the Arctic. How come there could be such a huge number of animals out there if now those places are so low productive? And the question is actually very simple. How can you provide enough forage for animals? If you want to have high productivity, productivity consists of 2 branches. First of all, everything should grow rapidly. So photosynthesis should be active. So photosynthesis should be strong. And photosynthesis, it's a photochemical reaction. It's mostly dependent not on temperature, but on duration of vegetation cycle and how long the sun is up the horizon. In our region, in June, sun doesn't set. We have photosynthesis almost 24 hours a day. So duration is 3 months. So it's somewhat lower, of course, than in temperate climate, but still quite active. At the same time, another branch, which is also possible, everything should grow quickly, but everything should decay quickly. So nutrients are returned back in the cycle. And that's where it's a huge difference. In the Arctic, decomposition is extremely, extremely slow, and everything is decaying for a very long time. So if, for example, a grass or tree grew up, picked up nutrients, and then it's dead, and it takes quite a while. For grass, it takes a few years to decay. For trees, it can take up to a century to decay. And all the nutrients are lost for the ecosystem, and growth is very slow. How do ecosystems with animals change that? Well, the composition of organic matter in this ecosystem is happening in the stomachs of animals within, let's say, 24 hours versus several years. So you have much faster circulation of nutrients, and you indeed can provide much more forage for animals compared with what modern ecosystem can offer. All right, if this ecosystem was so awesome, and we know that it's sustained for hundreds of thousands of years, different glacial, interglacial cycles, but why did it entirely disappear 10,000 years ago? So the question is, first thing which we are saying, this ecosystem, so mammoths lived in Spain and in New Siberian Islands. I don't believe that the climate back then was so similar that in Spain and the New Siberian Islands was the same environment. It must have been different. So mammoths can live, and this ecosystem could sustain in different climates. And we, moreover, know that many animals of this ecosystem lived in the modern, already Holocene climate for thousands of years. And there is a map where kind of bees, bison, horses, mammoths, where they found remains which lived in the Holocene already. And based on that, we can conclude that it's very unlikely that it was climate that destroyed this ecosystem. And well, what could be that? And for that, we did some more analysis. We gathered, at that time when we published this paper, we gathered every single radiocarbon dating of all animals which we can find paleontological, and gathered the database. And we saw that by the abundance of remains of different ages, that actually after the climate warmed up, density of animals rose. For the first few centuries, there was more animals. And this kind of reason is simple. There is more precipitation, more sun. It's warmer. So more productivity is possible. So more productivity, it's possible to have more animals. At the same time, the collapse happened when there was the first evidences of humans, ancient humans entering the Arctic. And here, kind of, we are getting to the point that back at the time, in the place in now Siberia, there was no humans. And then climate became warmer, and it became favorable for humans. So there was, it was flat landscape without trees. And no humans could survive at that place. When it got warmer, chances for human survival increased, and people started to migrate. So basically from Europe, they started to go to the Arctic, then through Bering Strait they entered the United States, well, North America and then South America. And the further they went, the deadlier were the consequences. So this is the number of animals, how kind of the extinction happened in Europe. In our region, out of all species, we have only wolves and reindeer left. In North America, I think only bison was left. And in South America, there was, 50 species with body weight over 44 kilograms, every single one went extinct. And in the Arctic, it's very hard to believe that humans could kill every single mammoth. However, it's not even needed. The sad reality that grasses and herbs cannot compete, at least in the Arctic, against most shrubs and trees without support of animals. So animals are accelerating nutrient cycle, they're trampling down the grass and herbs enemies, drop down number of animals, and slowly your pastures will just disappear and degrade and be replaced by other vegetation. And several centuries and 1,000 years later, mammoths couldn't just find a place. Like a small number of mammoths cannot live in a kind of bad quality pasture. You know, it's Arctic. We have nine months of winter. You need to like something very good underneath the snow in order to survive. And these conditions just disappeared. And kind of the sad logic which we have here is that apparently the wild nature, which used to be back then, is way more effective in terms of managing our planet than our current civilization. Because back then this kind of civilization of nature, using only non-renewable resources of the sun, managed to have higher biomass compared with what we now maintain by burning oil, gas, and getting fertilizers out of the ground. And from one point of view, that's kind of sad. That's showing that we are not very effective. From the other point, it's actually showing that we do have ways to improve our management of the planet, and we do have I believe we do have hopes for the sustainable kind of existence in the future. All right, if this ecosystem was kind of existing in the past, can it help us in the future? And that's kind of why we are here at COP talking about climate and why we are saying about Pleistocene Park, is that we say that these ecosystems in the Arctic, high productive ecosystems in the Arctic, can be beneficial for us in the future. And there is several phenomena how this might help. And I will start explaining all of them. So first one, grasslands are lighter than shrubs and forests. And the lighter the surface, the higher portion of energy it reflects back to space. And especially this effect is pronounced in our region in April, May, when we already have enormous amount of sun energy entering the atmosphere. But pastures are staying white because they're still covered with snow. And all the trees are having dark stems and they're getting heated by the sun enormously. And that's actually quite a strong effect. And we did some measurements and we see that over the course of about 6 weeks, we have an average 160 watts per square meter emitted by pastures at that time. And 160 watts per square meter, it's like, having 10 electrical heaters turned on in this room. So that's quite a massive effect. All right, second, we've been showing you, I will be showing you permafrost. Permafrost, huge reservoir of carbon, it's getting warmer, climate's getting warmer, in the Arctic especially. When permafrost degrades, we are all doomed. Well, exaggerating, but still. How to protect permafrost? We need to kind of find solutions for that. And actually this ecosystem can offer some help. So temperature of permafrost is about 5 degrees warmer than temperature of outside air. And the reason for that is that in the summer, sun is heating up the ground without any barriers. And in the winter, when the ground have to cool, the snow is not allowing that to happen. And ground and permafrost is staying warmer. If you get rid of the snow somehow and allow deeper freezing, the temperature of outside air and temperature of permafrost will be the same. Of course, we cannot get rid of all the snow, but if you have pastures, if you have something tasty underneath the snow, and if you have animals, they will come to this place, they will excavate snow, looking for food. By that, they will compact the snow quite dramatically from that to this. And at that, the snow will lose most of its heat insulating abilities, and you can get 2 to 3 degrees cooling of permafrost, which is, quite a lot. So that will save a lot of permafrost by the end of this century. And here we have some data showing that indeed on our pastures where animals been present, we have much deeper freezing of the ground. So we didn't have samples in the permafrost, but on average, you see, we in the Pleistocene Park we do have like 2.5 degrees cooling effect on the pastures. Okay, third effect. There is 2 greenhouse gases, CO2 and methane. Methane is much worse. Methane is produced in anaerobic conditions And if you can avoid anaerobic conditions, you can much lower the methane emissions. Right now, Arctic, even though mostly in the Arctic, in many places in the Arctic, climate is arid, we do have very kind of moist conditions. There is permafrost underneath, which doesn't allow drainage. There is moss on the surface, which doesn't allow evaporation. And so we have water saturated. Wetlands, lakes, and just the soil is safe, is always water saturated. You cannot walk without rubber boots in our region, really. If you have high productive grass and herbs in arid climate, they will drain and evaporate all the water, which is all precipitation, very rapidly. So you can get aerated soils instead of water saturated. And all your carbon will be converted into CO2 rather than methane, which is what, 25, 30 times worse? So, and the last thing, when people talk about nature-based solutions, what's the main nature-based solution out there? It's planting trees. And that idea do work in the tropics where it's warm and trees grow fast and tall. However, we go to the Arctic, our trees are very miserable. They are small, sparse, and growing for the very, very long time. So, and it's impossible to store any substantial amount in the above ground vegetation in the Arctic. However, we do have one reservoir which have potential to have lots of carbon in it, and that's called Arctic soils. Our soils are frozen most of the year. That kind of summer, short summer when it's thawed, temperature in the soil is still extremely cold. So if you have any carbon input go into the soil, it will stay there for centuries/millennia. And what we propose to do? Right now, most of the Arctic is having ecosystems with little to no deep root system. So mosses and lichens don't have any roots at all. Trees, large trees, have all the roots only along the surface. So all the organic matter is just in top 10, 20 centimeters of ground. You replace that with grass and herbs who need lots of water. Where they look for water? Down there. So they're growing deep root system. So basically they're picking up CO2 and bury it in the ground, deep in the ground. And unlike forests, which been burning super intensively in Siberia in the last years, that carbon is not a subject of forest fires or any fires. And that's kind of making a quite sustainable thing. And we did some measurements on that. And we did very intensive drilling in the park. And we compared what we have in the park, what we have in productive ecosystems without animals, and what's out there in the mossy forest. And we indicate that in the mossy forest, there is like at least 2.5 times less carbon compared with what's out there in the places with grasses, herbs, and willow shrubs. And on top of that, if you introduce animals to that place who accelerate nutrient cycle, there is even more carbon going to the ground. And here is how it's kind of varying with depth. So the blue line, it's a profile of carbon in the forest. So you see there is some carbon at the surface, and then it goes down, it declines rapidly. If you have vegetation which is growing deep roots, the green line, let's say, then you have kind of much more carbon. And if on top of that, you're introducing animals, and which accelerate the cycle and allowing grasses and plants to grow more rapidly, there is even an increase of carbon content with depth. And that's pretty much, see the difference between the green and the right line, that's about 15 years of our activities within the Pleistocene Park, which gave us around, I think, 3.5 kilograms of carbon per square meter, which is quite substantial. Okay, I will miss this one, where I was showing my personal carbon footprint versus what we have sequestered in the park, and switch to our activities. Okay, right now that's how the Arctic look like. So that's a low productive ecosystems with little to no animals, and only creatures which live there in abundance are mosquitoes. And that's not the most pleasant creatures I want to see, and not the creatures I want to see in the Arctic in abundance. However, the reverse shift, which happened 12,000 years ago, is also possible. If in the past, humans managed to destroy this ecosystem by reducing the number of animals and keep it at low for extended period of time, we can do the opposite. We can artificially increase the number of animals and maintain them in high density long enough so animals actually by grazing, allowing grass and herb take competitive advantage against other plants and establish pastures where these animals will already have ability to live on their own. And that's pretty much what we do. So back in 1996, Yakutian government gave us a relatively big piece of land and we fenced part of it and start to introduce animals. So first we start with animals we could find locally, like moose. Then there is, if you go at about 500 kilometers west of us, there is some Yakutian people who herd horses, Yakutian special kind of cold adapted breed. And that's animals which we introduced many, many years ago. Then there's reindeer, also kind of local creatures. And unfortunately, that's all with animals you can find locally, and for some other animals we had to make complicated expeditions. I will show some pictures. Oh yeah, without saying you how we got those, but we have even Bakshin camels for 3 years already. Super awesome creatures, we love them a lot. Then our kind of one of the most rare and wanted animals we ever had are muskox, and we had 2 expeditions so far for them. And the first one was in 2010. I will show you some pictures from that expedition. So we had to go around 1,000 kilometers along the Arctic Ocean and to this isolated island. And that was the ocean-class cruise ship which we used. So it took us about a week to get there, and we saw quite some wildlife along the way. And it was a very tough route because there was lots of floating ice, and we had to go, hundreds of kilometers trying to get passage to the island. And when we finally got to the island, it took us about maybe 10 days to try to capture baby muskox. And you have to find the herd, kind of surround it, and tranquilize babies. And when they're asleep, it was, it was extremely cold and windy, and I was spending my time there hugging with baby muskox just to keep myself warm. That was our catch, which we later put into the deck of our boat. And on the way back, there was no ice, but we got a horrible storm, and we were, for 2 days, we were in the open ocean, and it was quite a nightmare. But finally, we reached the shore, and then finally got to the park. Everybody got safe in. That's them in the quarantine, and that's them already several years later. Unfortunately, at that time, we didn't manage to establish population of muskox successfully, because probably theory of probability was against us quite badly. We found 6 muskox, and out of 6 muskox, all 6 were males. So that was a horrible bummer, and we didn't manage to get any females, and for many years we couldn't succeed. It was, let's say, one-time expedition. I didn't have motivation to go on that again. So I think I used up all my luck during this expedition. And then finally this year we actually went to Yamal Peninsula, and there is a national park out there, and we made an agreement with them that we brought them bison. And we introduced them 12 bison, and in exchange they allowed us to catch some muskox at their territory, and that's what we did. So we transported kind of the last path of bison coming to the national park was by this crawling transporter. Then we released the bison, and in exchange we were, oh yeah, that's them out there in Yamal. And in exchange, we were following the herds of muskox which they have in their national parks, and also found some babies, and also using this tranquilizing gun. And that was one of the babies in quarantine. And then we got those muskox into the truck, and they were going from Yamal Peninsula. They went all the way to Arkhangelsk. Arkhangelsk is a town at the White Sea. It's a river port, very west, north of Russia. Yeah, that's them in their cages. And out there, these cages were put on a big ship, and the ship was going along the Arctic Ocean all the way to our local seaport. So that's them already somewhere along the way. It was actually taking quite a long time for them. It's taking forever to be loaded on the ship and go. And finally, this September, they came to a local seaport and put in a small barge. And from there, we took them already all the way to our placing park, where we got them and put them in the quarantine. And now they're happily roaming in the placing park for 2 or 3 months already. And we have 9 females, 5 males. Hooray. I hope it will help to establish population. All right, then we had 3 expeditions with bison to the placing park, and bison are the most effective and successful animals we ever did. And it may sound weird, but the bison we are taking from Denmark, and there is a very lovely steppe bison farm where they kept for meat, and we were buying them 3 times already. And they have a different route. So first through Europe they're going on the scout truck, and then That's them. Then at the Russian border, we kind of switched them to our own transportation, where we already prepare special cages, because you know, it's taking forever to drive through Russia. I think it's about, on average, we were making the road trip in about like 25 days. So for that, you need like a special kind of cages where you can get them enough space, they can move, they can have enough air, they get enough food and water. So that's kind of the critical for if you want to make sure that your super precious animals are making it kind of alive and healthy during the trip. So unfortunately, as you go east, it's very, the quality of roads in Russia is getting lower, and we had to take ferries and go through mountain ridges and dirt roads. And finally, we're reaching the small river port very up the Kolyma River, where the animals were put on the small barge. And the last 1,500 kilometers, they are making along the Kolymar until they are finally reaching the placing park and released straight away. So that's them. That's just released young bison. Then there is this already more adult couple years later, some of them. So as I said, we had 3 expeditions, and the very first expedition, 2019, is already giving birth like 30 years in a row, and they're living entirely without any support from us. So we are super happy that, you know, it's another proof that it wasn't the climate which killed these animals. All right, so I think here I will be kind of saying my last, kind of show my last slide. I'm quite proud to say that this year we start to get quite a big support from the Andrei Melnichenko Foundation, which allows us to substantially accelerate our activities in doing rewilding. And within the next few years, we are planning to expand territory which we have right now at least 10 times and build a big fence. And we do that because we want to have more animals, and we are hoping to get up to 2,000 animals. Mostly we want to focus on muskox and bison, and we plan many, many expeditions in the next few years, and so it's a big plan. And the reason why we want that, because we are sure that we cannot make sustainable ecosystem without any predators. So grazing ecosystems without predators are not operational, and to have predators, we need to have enough, kind of established population of bison, muskox, and other animals which could support some predators. And also our plan is to do all sorts of research related to ecology, rewilding, kind of ecosystem management, and support the idea that, which I said that how this ecosystem beneficial, and that's kind of the goal for the next few years. And the ultimate, that create ecosystem which we will be able to expand, started in new places, and eventually get ecosystems, so create world's largest wild ecosystem, which will be the richest ecosystem, and the ecosystem which will be capable, which will be capable of influencing the global climate. So that's ambitious, but you know, only the person who tries to do something achieves. Thank you very much.
Thank you. Thank you, Nikita. Very interesting. Before I pass this mic to people who want to comment upon this, if there are any questions, Nikita, you can stay actually on the stage because there will be questions. Yeah, please.
Pardon?
Use mic, please.
Hi, I'm Martin from the Dutch newspaper Trouw. How much greenhouse gases could this idea save in the long term?
I think our rough estimates showing that we can sequester just by this root system, kind of developing root system. I think we can get between 100 to 500 grams per year. So, accounting that the territories which you have in the Arctic is very big, so it have quite a big potential.
Thanks. Any other questions, please?
What type of predators do you think would be introduced?
Well, the most simple and basic, it's wolves, who are there in the region. That's the simplest one. And we are thinking about introducing some big cat. It's the Amur tiger, who are now really under threat of extinction in their original habitat because there is not enough food for them. So there is population of deer and boars are in decline at the southern part, at the border with China, let's say. And another idea which we have, we are not sure we will be implementing that, but back in the time, we had this so-called cave lion, But geneticists who kind of studied, no, not saber-toothed tiger, just like, it was called the cave lion. But first of all, we don't have any caves. And secondly, and we never had caves. And secondly, geneticists will reconstructed the genome of this cave lion and appeared that this genome is 100% identical to the genome of the African lion. And our African lion is called African only because they now live only in Africa. Back in the present time, they were living like absolutely everywhere. And I believe that there is actually some zoos in Siberia where there were lions living outside in Novosibirsk. I think at -40 and like for 50 years already, I think they have a population of lions living outside for many years. So maybe we can try to get some lions from them. But that's a kind of still a theory. I'm not publicly stating that yet.
So I have one other question before you go on. So is the mammoth critical to the ecosystem, however?
I think that, I think that predators are way more critical than mammoths. Mammoths, first of all, indeed, in every pasture ecosystem worldwide, and historically it was like, would always be a place for elephant. So in Africa it's African elephant, Asian elephant, in America it was straight-tusked elephant, in the mammoth steppe it was mammoth. So these animals always had niche. And I believe that with mammoths our ecosystem will be better. So let's say it's kind of like having a right fist. So mammoths make this ecosystem way more aggressive because they can kind of knock down trees and they can invade new territories much better. It's like, can you live without a fist? Yes, you can. Maybe you're not as effective, but you can. And predators, it's like a liver. You cannot live without a liver.
Thank you.
How many people currently work at this park, and how many would be needed to extend it?
Coming, very few. So the lack of people is very serious kind of problem with Playson Park for sure, that we are now continuously attracting and inviting scientists. If you have any idea, if you watched the presentation and you have some scientific ideas in your head which you want to test, then definitely contact us and I'm sure we will be able to accommodate research. So we are really looking forward to accommodate research. We need many people and the more the better.
Thank you. Are there any more questions on the floor?
One more question. I'm not sure if this is true, but I heard at the technology hub there's like a huge experience like about this park, and someone told me there that it might be possible to get back to mammoths someday. Is that true?
The last and also the Colossal, the company which is led by George Church, the geneticist from Harvard University, they are trying, but they're not like really making a mammoth. They are tuning the genome of elephant to make it more cold adapted. I think the last there was like in the news a couple of weeks ago that they promised the first mammoth by 2028. Do I trust that? I don't know, but I would say that's not the work we do, but overall we are supportive of the activity, and if they will succeed, we would, of course, happy to facilitate mammoths.
Well, thanks so much. Are there any more questions here? No, okay, I don't know how to behave actually. I have two provocative questions to you, but since I have to also be part actually of the statements following up by your talk, I will probably do this later on. Ilya, please. So we have a comment from Ilya Tipulin, who is director of Andrei Melnichenko Foundation. Which mic do you want to use?
I can say it here. Hello, dear friends. Thank you that you joined to our discussion. I want to make a short note about the role of our foundation in this story. We believe that mitigation of climate changes are impossible without nature-based solutions, and we see the mission of one of missions of our foundation in support projects like this and to help them to become adult and to support themselves. But at the early stages, we support projects themselves and scientific researchers that can prove the results of such projects. So we see that the best development of the story with solutions like Nikita Todd, that they become a technology that can help us to mitigate climate changes. Yeah, that's all. Thank you.
Thanks so much, Ilya. Very good. So now it's now my turn. Actually, I was listening with a great interest to this presentation, not the first time, and thanks again, Nikita, for presenting this. I would say I will probably say some provocative things actually here. First, good things, good news that projects like this is what is called nature-based solutions. Actually, I learned this term from also Nikita and from Melynchenko's foundation. It's a great thing. It's a great thing, and this is a great thing not only for mitigation of climate change, but also for science, because actually through these projects we, I would say that probably it is, no, it's the first provocative thing I'd like to say. Probably it is less important what we learn, what we earn now from this fascinating project, but it is more important what we don't or didn't learn yet, and what we can generate in our mind with respect to what can be done here and what are the consequences. In this respect, what I think that your project might be really enriched if you provide actually concurrently with these activities by placing these interesting animals in a very specific environment, precise measuring of carbon budget and methane budget, and actually integrating then estimates provided by these precise measurements. And it is, to some extent, it is very unfortunate that it hasn't been done before, actually, over the whole evolutionary history. What has happened during the last, I don't know, 35 or 40 years, you are doing this. This would be a really invaluable thing, actually, for us, for climate scientists, thinking about the evolution of carbon budget and how we can not mitigate, but just impact on this budget. The other thing, also provocative a little bit, think nothing wrong about your project. You can comment then upon if you like. For instance, okay, we know, and we really know that, for instance, but you said 50,000 years ago, these animals were just okay, very comfortable there in the place they are now, in a few of them. But for instance, 82,000 years ago, in southern part of UK, British Islands, there were animals like hippopotamus and also crocodiles and so forth. So provocative question is what will happen, what will happen if we now populate this place with hippopotamus and crocodiles? Whether anyhow the landscape will change actually of this Southampton and Reading and some other small nice cities actually in the southern UK. I don't know, and whether this will change and the extent to that this will happen. It's whether it's rephrasing this in the context of your talk, whether it's really a local hotspot we can do this, or it's kind of a conceptual approach which can be distributed and which can be applied to other places in the world. It's interesting. And the third thing is that besides the climate change, what we consider here sustainable development, and climate change is only one, not climate change, but just okay, somehow accounting for climate change is just one of many 17 actually targets and tasks, whatever, of sustainable development, and there are many others. And if we do this, as you suggest, and it's interesting and probably it's regionally, local, whatever, but whether we are, this is invasion to the ecosystem, in fact. And do you know, or are you going to study how this invasion of this new piece of new animal sector, I don't know how to say this, how do they interact with the existing ecosystems, and how the extent of that existing ecosystems can change? It's also interesting. It's also a question. So I pose 3 questions for you. In your concluding remarks, you may probably respond to them. And now, having said this, I give the floor to Igor Akhmetov. Akhmerov, and he can introduce himself. If you like, you can use this mic. You have to be trained a bit because you have to put it close to your mouth.
Good evening. My name is Igor Akhmerov. I'm a professional developer of first renewable energy projects. I started working with solar back in 2006 when this was exotic. And I am also a professional developer of nature-based solutions. I worked with peatlands, I worked with animal manure, and we're now looking together with the Melnichenko Foundation at a very interesting question, which is how we can make sure that this project becomes self-funding and expands itself. Because there are facts that you saw. Fact number 1, there is potential substantial danger in what sits underground in the permafrost area. The fact number 2, it's extremely complicated to apply industrial solution to a thing like this. It has to be something inventive, creative, and attractive for those who undertake to travel to those places, live in those places, and perform the task. And some of it can be carried by the philanthropic activity, and we should all thank the Andrei Melnichenko Foundation for launching this. But at the end of the day, it all has to become business. And in order for this to become business, there's a very simple path that people have in other nature-based areas have followed. And this path is, let's make a standard out of it, let's register this, and let's create sufficiently attractive price for this particular type of molecular, so that people would have, the capitalism would take over, and people would, for their own cost and for their own benefit, send the bisons, take over the land, maintain the land, and travel to those places in order to work. So we have started dissecting those 4, I'll remind them, those 4 areas that Nikita has spoken about, which is the permafrost, thawing, albedo, the accumulation of soil, and the methane. And we have now applied science in order to measure those things precisely. And in the next 2 years, what we're trying to do is to come up, basically follow the path of similar Verra and Gold Standard and Plan Vivo and other standards. We need to choose which one we're going to use. But to follow the scientific path of establishing an unbreakable link between the result of this activity and the carbon accumulation. Once we do that, and we have a probability curve and the certainty curve that we're following, once we are at a certain level of this curve, so that this becomes industrial, we will approach major standards, and maybe by the time the 6.4 will come in force, and propose to make this one of the lines of business, in which case, at least, there will be a product. It will then be a very interesting question, who would be interested in purchasing this particular type of molecule? And we do believe that in the next 3 years, which it will take for us to arrive at a reasonable claim on a standard, the danger that we're trying to prevent with this will overcome the politics, which would inevitably stand in a way today between running a large-scale project based in Russia in a voluntary market in Europe and in the United States and in somewhere else. This is an issue now. We hope this will be resolved in a short period of time, and we hope that mankind is rational and will take a decision to accept this type of product, obviously subject to scientific proof, even above and beyond what Nikita has already demonstrated, and will be able to find a market for this molecule, in which case the acreage of what Nikita is managing now will multiply, and we'll have a reasonable chance on slowing down what may be quite a big danger in sitting in a permafrost. Thank you.
Thanks so much. If still there are any questions, if no, I can give. Yep. Yes, sure. Yeah, it's that what I want to suggest. Actually, if there are no questions actually on the floor, I would ask Nikita actually to say some concluding words and probably some conclusive statements. And if you like, you can answer my questions actually, but not necessarily indeed.
Yeah, I would like to answer your question. Probably I'm not the best person for the conclusive word. When you say that about competition against existing ecosystems, the ecosystems we want to make, you have to understand that climate change is so real and so bad. And in terms of numbers, permafrost, which have enormous amounts of ice, so my town where I grew up is standing on this ice. My ecosystem, the Pleasant Park, is standing on this ice. Research station is standing on that ice. And when I was a kid, temperature of this ice was -6 degrees. Now it's -2.5, -3. Average rate of warming of this ice is 0.1 degree per year. So on average in 30 years, all this ice will melt and all the ground will collapse by at least 15-20 meters. And everything that's standing on this permafrost, on this ice, will be destroyed. So it's not a question. I'm not kind of trying to kill the ecosystem which will kind of be sustainable, flourishing, I know, millennia ahead. No. I'm trying to it's already not a question. Will we be able to save it? It's a question how, what it will be replaced by, either by useful ecosystem or by ecosystems which will be helpful for us in the future and for environment. So it's, I don't see any kind of, moral difficulties with our work. Plus, just in terms of, competition, even imagine that these ecosystems would last longer. Right now, these ecosystems, it's not the natural ecosystems. The ecosystems were created by man, who destroyed the original ecosystem. And the large forest, for example, it doesn't carry any goods neither for humans or to animals. None of my animals want to eat large trees. I tried very hard to force them to eat it. They don't want it. Okay, and I think, I don't know if anybody's going to say the conclusive word, but thanks everyone for joining, thanks for the question, and I hope it's been an interesting evening for you. And, yeah.
Thanks so much again. This optimistic point, we came to a point when we should somehow stop our activity here, at least our business activity. Thanks everyone for coming. Different actually stages of this session. It was really a very nice session. And I do hope that our reception will be served, but at least they called me and said it will. Let's make a break for another, for instance, 10 minutes. And I'm very much hopeful that during this 10 to 15 minutes, the reception will be served and we will start informal part actually of our presence here. Well, thanks again. Thanks again for coming. And have a very nice evening and very nice the rest of this conference. Thank you very much indeed. Thanks. Я объявил об этом. Не надо? Ну, давайте мы объявим об этом. А что такого? Не хочет Сибор, да? Сибор не хочет. Ну, давайте, давайте. Конечно, давайте. Да.